Good morning, sir. Principal, sir. I think principal has joined.
Yes, sir. Yes, joined, sir. Good morning, sir. Your audio is in mute, sir. Yes, sir. Good morning, sir.
Good morning.
Yeah, good morning.
Good morning, sir. Good morning.
Good morning. Okay.
Dr. Pari, your audio is in mute. Please unmute your audio. Good morning.
Mr. Ravichandran.
Yeah, good morning. Yeah.
Good morning, everyone. We welcome you all for the Science Academies virtual lecture workshop on recent developments in classical, quantum, and condensed matter physics, organized by PG and Research, Department of Physics, National College, Tiruchirappalli. Now I invite Dr. S. Pari, Associate Professor and Head, to deliver the welcome address.
Video. Good morning, everybody. Today, who are all linked with this?
Dr. Pari, your voice is not clear. Please.
Hello. Good morning, everybody. Wish you Happy New Year. For this, am I audible?
Yes.
Yes. Yes. Good morning.
Yes, it is clear. Please proceed.
Welcome who are all linked to this great workshop. I welcome the eminent illustrious veteran scientist Bhatnagar awardee Dr. M. Lakshmanan, Professor of Eminence, Department of Nonlinear Dynamics, School of Physics, Bharathidasan University. He is the convener of this workshop. I welcome you, sir.
Thank you.
I welcome our beloved principal, Dr. R. Sundararaman. National College is the president of today's workshop. I welcome you, sir.
Thank you.
I welcome our secretary, respected secretary of this great college, Sri Raghunathan, sir. I welcome you, sir. I welcome sparkling, knowledgeable scientist Ganapati Bhaskaran. He is an Indian theoretical physicist who is the recipient of Shanti Swarab Bhatnagar Prize for Science and Technology in Physical Sciences. I welcome you, sir. I welcome Professor V. Balakrishnan, is a P.Man in the present time. Balki infuses rigorous mathematics and institution in an amusing manner. The sheer number of topics he has worked on and offered courses in the field is very amazing. Dr. V. Ramakrishnan, sir, who got a Commonwealth Academic Fellowship UK and Japanese Society for Promotion of Science, JSPS. I welcome you, sir. I welcome Dr. K. Jagannathan, Professor, Department of Physics, Bharathasan University, Tiruchirappalli, who is an augmented scientist. I welcome you, sir. I welcome lively, intelligent, and witty Professor Dr. Shankar Narayanan, Associate Professor, Department of Physics, National Institute of Technology, NIT Tiruchirappalli. I welcome you, sir. I welcome Dr. A.T. Ravichandran for coordinator of this event, great workshop. I welcome you, sir. I appreciate Dr. A.T. Ravichandran and great Professor Dr. Lakshmanan for their untiring effort taken in this workshop very high. Once again, I thank you and appreciate you, both of them, sir. In this great moment, my sincere and special thanks to great Professor Dr. M. Lakshmanan for organizing this wonderful workshop. I thank to the Indian National Science Academy in New Delhi, the National Academy of Sciences, Allahabad, Indian Academy of Sciences, Bangalore, for sponsored 3 days virtual workshop, lecture workshop. I welcome my dear colleagues, my dear students, scholars, various professors from all over the globe of great for coming this linked here for this great college. In this occasion, I thank our college management, secretary, and principal for having given all support and help in organizing this wonderful workshop. Once again, I welcome one and all. Thank you.
Thank you, sir. I request Dr. R. Sundararaman, Principal, to deliver the presidential address.
Today's resource person, Professor M. Lakshmanan, Head of Department of Physics, Dr. Pari, Coordinator, Dr. A.T. Ravichandran, Dr. V. Hariharan, learned professors, research scholars, and my dear students. Good morning to everyone. First of all, I thank Professor M. Lakshmanan for accepting our invitation. Even though he is a busy person in the academic field, he has accepted our invitation. Thank you very much, sir, for accepting our invitation.
Thank you.
And I also appreciate Dr. A.T. Ravichandran for arranging this useful workshop on science academics, virtual lecture, workshop on recent developments in classical, quantum, and condensed matter physics. I think it is very useful for the research scholars, those who are pursuing research in physics. It will be very much helpful for them to do research. I request all the research scholars and PG students, please closely follow the lecture of eminent professors and use them and make this workshop a grand success. I wish the workshop a grand success. Thank you very much.
Thank you, sir. I invite Dr. A.T. Ravichandran, Associate Professor and Coordinator, to give a brief introduction about the workshop.
A warm welcome to everyone. The Indian National Science Academy, New Delhi, the National Academy of Sciences, Allahabad, Indian Academy of Sciences, Bangalore, sponsored this 3 days virtual lecture workshop on recent developments in classical, quantum, and condensed matter physics, organized by PG and Research Department of Physics, National College, Tiruchirappalli. The primary aim of the workshop is to provide an exposure of the recent advances in different aspects of theoretical physics and related topics to the students, researchers, and young faculty members. Fellows of National Academies of Sciences, experts from well-known institutes and universities will deliver lectures, and participants will have an opportunity to interact with the experts and to get acquainted with the theoretical knowledge about the various aspects of physics. Learning physics helps us to understand how the world around us works. The knowledge of physics is the very essential for most modern technology, and studying physics strengthens quantitative reasoning and problem-solving skills that are valuable in areas beyond physics. Majoring physics provides the graduate students an excellent platform to train the mind in all branches of science, engineering, information technology, computer science disciplines. It is also useful to pursue interdisciplinary program in life sciences, earth sciences, atmospheric sciences, and even economics, public policy, and journalism. All the corporate recruiters recognize the value of analytical brains developed through physics. And this workshop provides a wonderful opportunity for the participants to interact with the distinguished resource person. Professor Lakshmanan is the convener of this workshop, and his wide experience and excellent guidance helped us to choose the topic and eminent speakers. I request you all to utilize the platform to enrich your knowledge. Thank you.
Thank you, sir. I request Professor M. Lakshmanan, convener, to give a brief introduction about the Science Academies.
Good morning to all of you, and thank you very much for the invitation. So I'm really honored to be associated with the National Science College and the Department of Physics in helping to organize this lecture workshop at Tiruchirappalli. So to start with, I would like to thank the management, the principal, and the head of the department, Dr. Pari, and Dr. Ravichandran, for taking so much interest in the organization of this meeting. I thank all the distinguished scientists who have agreed to lecture in this meeting. Professor Bhaskaran, Professor Balakrishnan, Professor Ramakrishnan, Professor Jagannathan, and Professor Sankaranarayanan. All of them have immediately accepted our request to lecture in this workshop. As all of you know, that this meeting is being supported jointly by the 3 National Science Academies. And at least for the information of the PG students and young researchers, that there are 3 science academies, National Science Academies in this country, which were started at different stages. The National Science Academy, Allahabad, which was originally started under the presidency of Professor M. N. Saha in early 1930s. And the Indian Academy of Sciences, Bangalore, which was started around 1932 by Professor C.V. Raman. And the Indian National Science Academy, which is situated at New Delhi, which was started, I think, originally in the 1950s under the presidency of Professor P.L. Bhatnagar. And all these three academies have the main motivation and aim of propagating scientific thoughts and inculcating the scientific spirit among young students, researchers, and faculty members throughout the country, and bringing in scientific information, scientific knowledge, and spread of scientific knowledge among the society. So they have been following different ways and means of fulfilling their aims. I can mention some of the common aims or common activities of these academies, like publication of scientific journals. For example, the journal Pramana, which I'm sure all of you are familiar, is being published by the Indian Academy of Sciences, Bangalore. Similarly, the journal Resonance is published by the Bangalore Academy. There are many other journals which are published by Indian National Science Academy, New Delhi, and National Academy of Sciences, Allahabad. So that is one of the important activities. The other main activities that is by all these three academies is annually they elect new fellows and honorary fellows and sometimes associates to honor their active research over a period. So everybody, every scientist feels honored when they are elected to these academies. And these academies also hold annual or mid-year meetings or many other meetings every year on special topics, and so that the scientists, the fellows and other scientists can participate in these meetings, and so that the whole scientific academy can get benefited from this. And they also have a repository of publication of fellows, and they also have lots of chair professorships and so on. But above and all, they also have science education program. From 2007 onwards, I think, all the three academies have joined together, pooled together their resources, and they help to organize several science education programs. I can cite some of these programs. For example, participation of college and university teachers in academy annual meetings, summer research fellowships to students and teachers. I think jointly they award around 100,000 or more summer research fellowships for PG students or even third BSc students, third year students, to pursue a small research project under the mentorship of a fellow of any one of the academies or professors recommended by the fellows of the academies. So that's a very important activity jointly carried out by all these academies. And they also support summer schools for students and teachers on specific topics, refresher courses for teachers two weeks or 3 weeks refresher courses, which are organized in different universities and colleges and national institutes on specific topics in all areas of science, engineering, and technology, and including medicine and so on. And finally, the most important aspect is helping the organization of lecture workshops of the kind that which National College has organized here today for the next 3 days. So either 2 days or 3 days lecture workshop to help young students, particularly PG students and the research scholars, as well as teachers, to listen to experts on specific topics. So the present lecture workshop, as Dr. Ravichandran has pointed out, is going to be on some of the recent developments in classical, quantum, and condensed matter physics aspects. So like that, lecture workshops are being held all over the country in different subjects, different disciplines, and different topics all through the year, so that young students and researchers can be benefited by the organization of these workshops. Besides this, the academies have several other functions like specific programs for women in science, oral history archives, generation of oral archive histories, and history of science, and so on and so forth. So the science academies have been playing a very important role in the propagation of scientific culture in this country. And it's very commendable that National College has been approved for the organization of this lecture workshop, this 3-day lecture workshop in physics. And I once again thank the management, the principal, the head of the department of physics, and in particular, Dr. Ravichandran, for taking all the efforts to organize this lecture workshop for the benefit of young students, research scholars, as well as teachers. And I do hope that the lectures during the next 3 days will be of useful use to all these young people. I wish the workshop a grand success. Thank you very much for your attention. Thank you. Thank you.
Thank you, sir.
Thank
Now
you,
I
sir.
invite Dr. V. Hariharakrishnan, Assistant Professor, to deliver the vote of thanks.
Dr. Hari, your voice is not clear. Unmute. Good.
Good morning, everybody. It gives me immense pleasure to propose vote of thanks for the inaugural function of the 3-day virtual workshop on recent developments in classical, quantum, and condensed matter physics.
Sir,
On behalf of the-
sir.
On behalf of the organizing committee, I express my sincere thanks to the Indian Academy of Sciences, National Science Academy, and the National Academy of Sciences for their financial support to conduct this event. I extend my sincere thanks to Dr. M. Lakshmanan, convener, Professor of Eminence, Bharadasan University, for his support to organize this function. I thank all the distinguished speakers, Dr. G. Bhaskaran, Dr. V. Ramakrishnan, Dr. V. Balakrishnan, Dr. K. Jagannathan, Dr. R. Sankar Narayanan, who are going to deliver their lectures on these 3 days. My sincere gratitude goes to Sri K. Raghunathan, Secretary, National College, and Dr. R. Sundarraman, Principal, National College, for their constant encouragement to organize such types of meetings. I will fail in my duty if I forget to thank Dr. S. Pari, Head of the Department of Physics, Dr. A.T. Ravichandran, Local Coordinator of this function, and all the teaching staff members of the Physics Department for their fullest cooperation to conduct this function. I thank all the participants like academicians, professors, research scholars, and students all over the India from Kashmir to Kanyakumari who are going to participate in this function. I extend my thanks to the support staff of National College for all their timely help. Finally, I also thank the press and media people who are here to cover this event. Thank you, one and all. Thank you.
Thank you, sir. Now we'll start the session. I invite Dr. T.V. Sundar, Associate Professor, to introduce our speaker.
Oh. Yeah, very good morning to all of you. It gives me pleasure and I'm immensely happy to introduce the speaker of the session, Professor Dr. M. Lakshmanan, who is going to give the inaugural lectures in this 3-day program. Professor Muthuswamy Lakshmanan is a specialist in the area of nonlinear dynamics with a special reference to solitons, nonlinear evaluation equations, and chaos. He has made varied in-depth contributions in these areas of physics. He has written over 400 research articles in internationally reputed scientific journals and many conference proceedings, and he has himself organized many such events. He has published over 10 books through reputed publishers in the area of nonlinear dynamics in theoretical physics area. He has over half a century of research experience, including over 4 decades of teaching experience, and has so far guided about 33 research scholars, and currently 4 students are pursuing the doctoral program under his very fortunate guidance. And many postdoctoral fellows are working under him to contribute to physics and as well as to science. He is the recipient of very famous and honorable awards at the national level. To cite a few, UGC's Hari Om Trust Memorial Lecture Award, then Meghanath Saha Award, then SS Bhatnagar Prize in Physical Sciences in the year 89, then Distinguished Scientist Award from MKU, then R.D. Birla Award of Indian Physical Society, then G.N. Ramachandran Award in Physics, and above all, recently, the government of Tamil Nadu has bestowed upon him the coveted Dr. APJ Abdul Kalam Award for his scientific contributions. Professor Lakshmanan is also a recipient of many fellowships of very famous, world famous academic bodies. To mention a few on this occasion, he is a fellow of Dr. DST Raman Fellow, then INSA Senior Scientist Award, then NASI Platinum International Fellowship, then Alexander Wall Humboldt Foundation Fellowship, and many others in the list. He is the fellow of all the 3 science academies of our country, and is also elected as a foreign member of Royal Academy of Sciences, Uppsala, Sweden. He is also an elected fellow of the Academy of Sciences in the developing countries, FTWAS, in the year 2009. He has visited many prestigious institutions all around the globe including Bulgaria, Canada, China, France, Finland, Germany, Greece, Holland, Italy, Japan, Poland, Spain, Soviet Union, Ukraine, UK, and USA. So, right from east to west, he has traversed many parts of the world to share his academic contributions. On the biographic side, 1946 born Professor Lakshmanan comes from a humble agrarian family in Coimbatore district of Tamil Nadu. He had his schooling at a government school in a neighboring village at Negamam. Then he did his BSc and MSc courses at NGM College Pollachi and Madras Christian College respectively. In 1974, he carried out his doctoral program in the Department of Theoretical Physics of University of Madras under the able guidance and the supervision of Professor P.M. Matthews. For students, probably you are very familiar with the quantum mechanics book by Professor P.M. Matthews and Venkatesan. So, Professor P.M. Matthews was the research supervisor of today's speaker, Professor Dr. M. Lakshmanan. After a few years of postdoctoral research in Germany and Holland, he joined as a reader in the Department of Physics, then the Autonomous Postgraduate Center of University of Madras at Tiruchirappalli, which later became Bharathasan University in 1982. He was promoted as a professor in the year 84, and he then served as the head of the department during 94 to 2006 in the Physics Department, School of Physics, Bharathasan University, and as a head in the Center of Nonlinear Dynamics from 92 to 2006. Right now, he is working as a professor of eminence and holding the prestigious position of DST Sub National Science Chair at Bharathasan University. And to note, I am also feel honored, and he gave me an opportunity during his headship to pursue my PhD program under the guidance of Dr. V. Parthasarathi at the University Department of Physics, Bharathasan University in the year 2003. So, Professor Sir, we are very much fortunate to hear your expertise, and definitely it is a very good platform for the students and even the staff members to get the expertise and the use of theoretical physics from your able experience. So I once again thank the for the opportunity given by the organizers to introduce the speaker of the session. Thank you all. Let me hand over the session to Professor M. Lakshmanan sir, and invite him to share his expertise in the prescribed topic, namely NLD topic. Over to Professor Lakshmanan, please.
Thank you. Thank you very much, Dr. Sundar, for a very long and kind introduction. So let me start sharing my screen. Start with. So are you seeing my slide?
Yes, sir.
And I will now go to the full view, full screen mode. Yeah. Yeah. So in this set of 2 lectures, I will be trying to make a brief introduction to some of the basic concepts underlying the field of nonlinear dynamics. In particular, I will try to introduce the notion of chaos, the underlying area of chaotic dynamics, at least some basic ideas. And then in my second lecture tomorrow, I will give a brief introduction to integrable dynamical systems and the notion of solitons. So let me start discussing the topic of chaos and chaotic dynamics. So in this first lecture, my major aim is to give an overview of the basic concepts of chaotic dynamics and probably discuss some of the important consequences ensuing from this notion of chaos. So the basic plan is to give a brief introduction to the topic of dynamics and then nonlinear dynamics, some basic ideas of nonlinear dynamics. What is nonlinearity? Why the dynamics becomes nonlinear and what is so significant about nonlinearity? Why should a physicist worry about nonlinearity? So I will try to introduce, starting from one of the basic building blocks of physics, namely the linear harmonic oscillator, one-dimensional harmonic oscillator, which is the basis of all our physics, I would say. Then from this linear harmonic oscillator, I will first point out why it is linear, and then where does nonlinearity comes? When does nonlinearity comes? So I will introduce a brief modification to the linear harmonic oscillator, introduce the notion of nonlinear oscillators. And once you have nonlinear oscillators, you have the possibility of integrability. You can integrate and discuss all aspects of these oscillators in some cases or under certain circumstances. But more importantly, once you have a nonlinear oscillator, as you change some of the parameters, which I will call as control parameters, because these parameters can be externally controlled, they lead to the phenomena of bifurcations, qualitative changes in the dynamical behavior from one type of behavior to another type of behavior, suddenly at a critical value of the control parameter. So bifurcations, and ultimately chaotic motion, complex motion. So I have to define what is chaos. So that is the main motivation of my lecture. And the underlying chaotic structures, which is predominant in the physical world in which we live. So I will try to introduce in some of the basic systems which we very often use, the possibility of bifurcations and chaos and underlying chaotic structures. Then I hope to very briefly introduce the notion of combining many such oscillators and then introducing the notion of synchronization, synchronized motion, and collective dynamical states. So I do hope that I will have time to at least very briefly mention what kind of collective dynamical states can emerge when you consider a large number of such nonlinear oscillators interacting with each other, coupled to each other, and so on. And before I conclude. So let me start with the very basics. And as students of physics from the high school onwards, school times onwards, we hear this great name, Isaac Newton. And Isaac Newton, of course, we all know that he is famous for his three laws. Three laws of motion. And if you look at these laws of motion, then these laws of motion, something moves, something changes. And then if you look at the nature around us, in this universe, in this world, then you find things change. The most common feature of nature is that impermanence. Everything, anything changes. Animals are born, they grow and die. So do plants. Planets move around, chemicals change, chemicals interact, crystals grow, clouds move, water on the surface of a pond changes. Everything changes. Nothing is permanent. Even the building in which you sit, the classroom in which you sit, if you wait for sufficiently long time, 10 years, 50 years, 100 years, everything would have changed. So change alone is unchanging, which is the most common feature of nature. As Lord Krishna tells to Arjuna in the battlefield, Matram enbade maradavun. So we consider Isaac Newton is perhaps the greatest physicist, greatest scientist to be ever born on this earth, because Newton essentially extracted the basics of nature in the form of the three laws, which we have all studied, gone through in your from our high school days onwards. And these Newton's laws ultimately leads to the equation of motion. So you know that the three laws, every particle continues in its state of rest or of uniform motion unless acted upon by force. There is no force, no change. The second law, which is the most crucial, change occurs. How? Why? The rate of change of momentum, the state variable, position and momentum. The rate of change of momentum is directly proportional to the force acting on it, on the system, external and internal forces. So when force acts, change takes place. And there is a rate at which change takes place. So if you observe the universe, if you look at things around us, try to look at the nature of forces acting on them. I think one can conclude that there exists no physical system which is not being acted upon by one or more kind of forces. Whether it's a pendulum or a Kepler particle, a planet moving around the sun, or a spinning top, or atoms moving in this room, everything is being acted upon by one or more forces. So planets move around the sun in elliptical orbit because of the gravitational force. Of course, there are other forces simultaneously present, but we talk about the most dominant force. So Newton said the rate of change of momentum is directly proportional to the force acting on the system. And Newton didn't stop with these three laws. He went on to identifying an appropriate language with which these laws can be represented in a very logical way. And he invented the differential calculus. Calculus, the art of calculating the changes. Of course, there are simultaneously with Newton identified calculus with and there has been literally an academic war during the 17th and 18th centuries. Who invented calculus, differential calculus? So German mathematician Gottfried Leibniz. Also, now everybody agrees that Leibniz and Newton simultaneously established the differential calculus. So let us not go into those details. Leibniz. Okay. So with the aid of calculus, differential calculus, then you can represent how the changes take place in the form of a differential equation for the state variable, the momentum P, the vector P in a three-dimensional coordinate space. The observer sitting at the origin, and he makes an observation of a particle moving, whether it's a pendulum or a Kepler particle, etc. So you represent from the origin by a vector, a position vector R, a three-dimensional entity, which has not only a magnitude, but also an angle. So you have a vector, position vector, and correspondingly the rate of change of position, the velocity dr by dt, which we can represent by the vector v, vector v equal to dr by dt. So you can define the momentum as p equal to mass into velocity m into v. So the rate of change of momentum is directly proportional to the force acting on the system. Force is now a vector without loss of generality, taking the proportionality constant to be unity. So you have the equation dp by dt equal to f, which when you substitute p equal to m into dr by dt, you get a second order vector differential equation to describe the motion of a single particle represented by the position vector r and the velocity vector dr by dt, or the momentum vector p equal to m dr by dt. Okay. Now the force F, on what quantities the force can depend. The force can depend on the position of the particle, its velocity, and also any external influence, which is represented by the time. So now you have a second order differential equation, vector differential equation, for the dependent variable, the position vector r, and it depends on the time t. So time is independent of our existence. From the time of Big Bang, when time started evolving, it keeps on increasing in the forward direction. So you have a second order differential equation representing the motion of the particular particle whose position vector r, which is being acted upon by the force F. So the physical motion, the evolution, can be represented in a very logical way in terms of a mathematical differential equation. Okay. So you can explore how this association with the physical system with mathematical representation, why these two are intimately connected, and so on. Okay, so I'm not going into the details. But in particular, if you want to associate a specific pendulum or a specific planet, etc., you talk about the initial value problem. Because this is a mathematical entity, this differential equation, vector differential equation. But when you associate, when you make an observation at a predetermined time, which I call as an initial instant, which I represented by time t equal to 0, just for representation. So I make an observation at that time, I measure the position and the velocity, and so momentum. So given this information, which comes from physical experimentation and the law of motion, equation of motion, the second order vector differential equation, the problem is to solve this differential equation subject to this initial condition and find r of t for all future instant of time, for all t greater than 0. At t equal to 0, the initial information is given. So the problem of solving or finding the evolution of this physical system starting from the initial condition is essentially to solve this differential equation. So this evolution the problem of evolution is nothing but dynamics. Dynamics which evolves with changes. Okay. And this change is represented for a single particle system for an observer sitting at the origin, measured by the position vector r and the velocity vector dr by dt is essentially given by the second order vector differential equation. So, given this statement on the initial condition, you solve this differential equation and you find r of t and so dr by dt. So, you can find the state of the system for all future instants of time given this information. Yep. And this is how we find that a two-particle system, a Kepler particle under inverse square law of force, the particle, the smaller small mass particle moves around the larger mass particle in an elliptic orbit as the Earth moves around the sun in an elliptic orbit and so on. The two-body problem can be effectively reduced under central force field to a one-body problem, which one can solve and you can get the Kepler's 3 laws of motion and so on. So that is why I call it Kepler particle, Kepler problem and so on and so forth. So you have a single particle system which has the position vector r, the components x of t, y of t, z of t. So 3 components in the 3-dimensional physical space. And so you can represent the evolution in terms of appropriate differential equation once the force, the form of the force is given, which you have to find essentially from physical observation again. Okay. You can extend this analysis to an n-particle system and you have essentially a system of n-coupled second-order differential equations for the position vectors r1, r2, rn and the corresponding velocity vectors and then the time. So the Cauchy initial value problem is essentially solving this system of coupled n-coupled vector differential equation subject to appropriate initial condition and solving this and finding the position Ri of t for all future instants of time t greater than 0. So in principle, towards the end of 18th, 19th, beginning of 19th century and so on, people believed that in principle, everything about the evolution of physical systems in this universe is essentially known, subject to solving the underlying system of differential equations. Okay, and this is what made the great mathematical physicist Pierre-Simon de Laplace, the French mathematical physicist, to proclaim at one point of time that for a super intelligence, the future is as clear as the past. But of course, we now know that there are a lot of limitations, quite a bit of limitations on Newtonian description in this particular manner. For example, if you want to consider the dynamics of 10⁻23 particles in this room, and why there is this, at this point of time, the temperature is this 32 degrees centigrade, or the pressure is such and such, and so on and so forth. So if you want to analyze this kind of problems, you have to solve very many number of such differential equations, coupled differential equations. Their study is extremely difficult and so on. Though in principle, Newton's description says you can do that. But, and moreover, we are not interested in the individual properties of these 10⁻23 particles, but we are interested in certain macroscopic observable quantities like pressure, temperature, entropy, and so on and so forth. So you can develop an average mechanics, a statistical mechanics, so development of statistical mechanics to deal with very large number of systems, and in particular, for example, condensed matter system and so on. So that is one aspect. Even when we have very fewer particles, fewer number of particles, even 1 particle or 2 particle and so on, when you go to microscopic world, like when you consider the dynamics of proton or neutron or photon and so on and so forth, And now you know that the beginning of 20th century that the end, towards the end of 19th century, several experiments have come up, and to explain all of them, you have to introduce the notion of uncertainty in measurements. Measuring the position very accurately can lead to large errors in the measurement of and specification of momentum and so on. Canonically conjugate variables. So Heisenberg uncertainty principle. So observing or measuring the values of canonically conjugate variables with infinite accuracy is almost impossible. So you have bounds, and so you have the Heisenberg uncertainty principle. So you incorporate the Heisenberg uncertainty relation into the dynamics, and you have to modify the description. You require quantum mechanics. And similarly, when you consider the evolution of such physical systems, so in this Newtonian description, you don't put any limitations on the values of the possible values of the position and the velocity. Of course, the particle can live anywhere in this three-dimensional space, which is infinite in extent. But what about velocity? Albert Einstein, in 1905, in his special theory of relativity, and then later on, general theory of relativity, and so on. So he came to the conclusion that no material particle can travel with velocity, which is the velocity of light. Light alone can travel with the velocity of light, c. When material particles can travel with velocities, they can approach the velocity of light, but never reach the velocity of light, and so on. So there is an upper bound on the magnitude of the velocity. So you require to describe that kind of particle motion, relativistic mechanics, and so on and so forth. But during the past 4 or 5 centuries, people have also started looking up at what about the nature of the forces that is acting on this system. So that can lead to the notion of linearity and non-linearity. So essentially, I will be trying to point out what could be the consequences of these forces being linear and non-linear. Okay, so I will try to explain what does this linearity or non-linearity means. Essentially, I say this dynamical system is linear if the forces are directly proportional to the dependent variables. So you have a system of differential equations, and you have the dependent variables, the position vector Ri, and their derivatives. And then the independent variable, which is the time. Okay. If the force is linearly proportional to the state variables, the dependent variables, Ris and dri by dt's, there is a one-to-one correspondence in the form of force and the relation between the force and the state variables. Then the force is considered to be linear because the underlying differential equation is a system of linear differential equations. But if not, then you have nonlinear forces and you have nonlinear differential equations. This can make enormous changes, is what I would like to point out. So, in order to explain this, let me consider first the case of linear harmonic oscillator. I think this is perhaps you may not see F equal to minus kx. So the force F is directly proportional to the displacement x, okay, with a minus sign, and k is the proportionality constant, spring constant. So the Newton's equation of motion in the one dimension is md square x by dt square equal to minus kx, which you can rewrite as d square x by dt square plus k by m into x equal to 0. I call k by m as omega naught square, the natural frequency for the reason I'm going to point out. So you have x double dot plus omega naught square x equal to 0, where dot means, of course, d by dt. So double dot means d square x by dt square. So simplified notation to represent this second order differential equation. So the problem, the physical problem is you solve this linear harmonic oscillator. You ask the question, what is the general dynamics of this linear harmonic oscillator once the initial value is given. So you have the pendulum, you pull it apart and allow it to oscillate. So you pull it apart. So at the time of releasing, you start your time. So take it as time t equal to 0. So you have the maximum amplitude capital A, and at that point of time, the velocity is 0. You can solve this second order. Of course, you know this is a linear differential equation for the reason I'm going to point out quickly. Okay. So this equation you can solve, and you can find the general solution is x of t equal to a cos omega naught t. So at t equal to 0, cos 0 is 1. And so x of 0 is maximum amplitude A. And as t increases, then this solution shows that this pendulum or the linear harmonic oscillator will exhibit periodic motion. And this is what I represent schematically in a diagram. Yeah. A phase trajectory, a diagram representing the temporal evolution, time evolution, x versus t. Okay, so you see that if suppose capital A equal to 1, then its maximum value at t equal to 0. And as time progresses, time increases, the value becomes 0 and it goes in the opposite direction, -1, and then again it comes back to 0 and then reaches maximum value 1 and so on and so forth. And so this keeps on occurring repeatedly. And the original motion gets repeated after capital T equal to 2 pi by omega naught. So that is the period of oscillation. Okay. And I represent, for example, this red, I start from an initial value corresponding to the red curve. And then you have a closed orbit like this here, an elliptical orbit in the xx dot plane, the phase plane, the phase trajectory in the xx dot plane. So I call this as a phase trajectory because it can, from x and x dot, you can write down the phase phi as tan phi equal to x dot by x or whatever it is. So you can, from x and x dot, you can find the phase. And so this phase point, and so you have phase trajectory. Now, if I change the initial value slightly, that is corresponding to this blue curve, slightly above 1, and then I ask the question, what is the period? You find again it's periodic and with the same period, only the amplitude changes slightly. So you have a different orbit in the phase plane. So that is the structure of the underlying problem solution as far as the harmonic oscillator is concerned. Now to this harmonic oscillator, so this I call linear harmonic oscillator because it's one dimensional, because dynamics vector R has 3 components, x, y, z, and I assume there is no motion in the y and z components. So y equal to 0, z equal to 0 always. So only x varies. So that's why it's linear harmonic oscillator. Now I add or modify the force as F equal to minus kx minus lambda x cube, x power 3, and lambda is a parameter. So that the equation of motion again, rate of change of momentum m d square x by dt square equal to F. F equal to minus kx minus lambda x cube, divide throughout by m, and I call k by m as omega naught square, lambda by m, which is new lambda or lambda prime, and I drop this prime for convenience. So I get the equation of motion x double dot plus omega naught square x plus lambda x cube equal to 0. Now this equation is much more difficult to solve. Your standard methods will not work to solve this problem. You can try. You require new kind of functions, unlike these harmonic functions. Okay, you require the so-called elliptic functions, which is doubly periodic. Well, I will not go into the properties of this elliptic function. So instead of cos omega omega naught t, you have A, C, and capital omega t. So now you see the frequency omega, angular frequency omega, is not just omega naught, the natural frequency, but here it is square root of omega naught square plus lambda A square. In addition, this elliptic function is also parameterized by a parameter called modulus square. Unfortunately, this I have used the same notation as k, but this is not the first constant, but modulus parameter, which you may also represent as m. Some people use the notation m square, equal to lambda A square by 2 into omega naught square plus lambda A square. There is no, this is unharmonic force. The force leads to a solution which is not harmonic type. So this is unharmonic force. So if you put lambda equal to 0, k becomes 0, k square becomes 0, in which case capital omega is just omega naught and Cn becomes cos. Hello. Hello, Dr. Ravichandran.
Yes, sir. It is audible.
Yeah.
It is audible, sir.
Was there a break?
Yes, sir.
Yeah, and the power had suddenly gone, so I have gone to another mode. Okay. Sorry about it. So let me again share my screen. Is it, are you seeing my screen?
Screen is not visible, sir.
Not visible. Yeah, I will come back.
Okay, sir.
Where is it? Yeah, I think I have to again share my screen.
Now it is visible, sir.
Yeah, I will go to the full mode, full screen mode. No. Where is it? Full screen.
It is available in the view edition.
Yeah, but it's not
No,
showing.
sir. Yes, sir. No, it's not.
No, what's the problem? More.
So please check the window, sir. The next.
It says Zoom.
The
Zoom, will it work?
oh,
Sir,
yeah.
no, sir, no, sir. Sir, press Windows and L key, sir. Windows
Window?
L and L. Windows L, sir. On the keyboard, sir. Window key and L key, sir. L letter.
Window key and L. Or I will just proceed this way. I think you are able to see.
Yes, sir. Yes, sir.
Okay.
Yeah. Yeah, sorry, but so I was pointing out that you will have the solution in terms of this elliptic function, but which will depend on this nonlinearity parameter lambda. But when lambda becomes 0, the frequency, angular frequency is just omega naught, original omega naught, and the function Cn will become cos. Similarly, there are other elliptic functions, Sn and Dn, etc. I will not go into the details. But the one important thing you observe is that the frequency now also depends on the initial value, the amplitude, initial condition amplitude. Whereas in the case of the previous problem, the harmonic oscillator, whatever be the frequency, whatever be the amplitude, the frequency is not changed. Frequency remains always the same, independent of the amplitude, independent of the initial condition. But once the nonlinearity, the unharmonicity parameter is introduced, the force, the frequency now starts depending on the amplitude, the initial condition also. So there is a dependence, a qualitative dependence on the initial condition. Now, under certain circumstances, this can become very critically dependent on the initial condition or the amplitude. Sensitive dependence on initial condition can arise when this kind of unharmonicity, which I will call as shortly as nonlinearity. So that makes the problem quite different. Correspondingly, you see in the time trajectory and in the phase space, you find for one particular initial condition, this red curve, you have periodic motion. And when you change the initial condition, in this blue curve, you start, then you find the period is slightly different for this value. And the next, they are not following as in the previous case. The blue, red and blue curve, they do not follow on the same way, same phase. So the phases start differing. Correspondingly, the frequency, angular frequency, and the period also going to depend on this amplitude A. And this is what you see in the phase trajectory. There is a slight deviation in the nature of the phase trajectories. Now, all these things can be related to what is known as superposition principle, the linear superposition principle. For the linear harmonic oscillator, if you consider this dynamical equation, second order differential equation, I said I have written the solution as cos omega naught t. You can also write a solution sin omega naught t. Substitute sin omega naught t, take the two derivatives, and you see that that is also a possible solution. And then you can also make a linear combination of cos omega naught t and sin omega naught t. A cos omega naught t plus b sin omega naught t, where a and b are some arbitrary constants. That is also possible solutions. So if x1 is a solution and x2 is a solution underlying the dynamical system, their linear combination, linear superposition, superpose, add one on the other in a linear way. That is also a possible solution. But now a cos omega naught t plus b sin omega naught t, using the simple trigonometric addition formulas, you can rewrite that as capital A cos omega naught t plus delta, where delta is the phase and capital A is the amplitude. A is you can write down the form for capital A in terms of small a and small b. So when I say that this is the general solution of the differential equation, the solution of the Cauchy initial value problem is that at t equal to 0, x of 0 equal to capital A, the initial amplitude, and x dot of 0 equal to 0, the velocity, initial velocity is 0. So take this general solution x of t equal to a cos omega naught t plus delta, apply the initial condition, then you will get back the solution of the initial value problem, x equal to a cos omega naught t. On the other hand, When you go to the unharmonic oscillator problem, this cubic oscillator is an example. You can have quadratic, you can any other such powers you can have. If you take such an oscillator, unharmonic oscillator, and if I have a solution x1, and if I have a second solution x2, and take the linear combination and ask the question whether this linear combination is also a solution, while x1 and x2 are individually their solutions, but their linear sum will never be a solution unless and until A and B are simultaneously 0, which leads to a trivial solution x equal to 0. Any non-trivial solution you can never obtain by linear superposition. So for nonlinear systems, the linear superposition principle fails, and as a consequence, all the methods and techniques which are used for linear differential equations, for example, the Fourier series, the Fourier transform, the Laplace transform, the Green's function techniques, various spectral techniques, which were all developed over the past 3 centuries and so on, will fail to solve such nonlinear differential equations because of the fact linear superposition principle fails. Because all the methods and techniques which you normally learn in your mathematical physics course is based on this linear superposition principle. When it fails in most nonlinear systems, you are left with no method to find exact general solution. And in fact, you find essentially each nonlinear system is a class by itself. And so the study of such nonlinear systems lead to this new field of nonlinear dynamics, because the study of each of these equations can lead to novel results. Very quickly, I will point out these aspects in the next 20 minutes or so. Again, I come back to the linear differential equation, dynamical equation for forced LCR circuit. You know, the LCR circuit, the inductor, capacitor, resistor. So all of you know LCR with a external forcing represented by F sin omega t. So you have a differential equation which after scaling, after redefining the constants, you can write as a second order linear differential equation with an inhomogeneous term. d square x by dt square plus alpha dx by dt plus omega naught square x equal to F sin omega t. Now this equation, if you solve, you know how to solve this method, this equation. The homogeneous part you can solve using the writing down the auxiliary equation and finding the roots and so on, and then the complementary function and adding these two. So this is the solution part coming from the without forcing, and with forcing you have this complementary integral part. So the sum will be the general solution of this damped forced oscillator. So you find in this equation, alpha is the damping, because the damping term is proportional to the velocity dx by dt. And this is the external forcing term. External forcing term is periodic with its own frequency, omega. So ultimately you find that there is two terms possible. One term has a form e power minus alpha t and then a periodic solution. But because of this exponentially decaying one, if you wait for sufficiently long time, this term will die down. What you are left with a term, a specific term, AP cos omega t minus some constant. So observe this omega is the frequency of the external oscillation. So what happens in this damped forced harmonic oscillator is that the system ultimately, under appropriate choice of these parameters alpha and omega naught, so-called underdamped oscillator system, executes resonant periodic motion, okay, with the period equal to the period of the external forcing. So this is the principle behind our radio or television reception and so on. Okay, so this is the standard one which we are all familiar. So this is the phase plane, phase trajectory, how the phase trajectory looks like for a purely damped harmonic oscillator. So whatever be the initial condition, wherever you start in the x dot plane, the trajectory ultimately end up in the equilibrium state, which is the origin. Even if you start from a different initial state, that is also going to end up in the equilibrium state, which is the origin. So there is not much deviation from the two initial conditions. So ultimately, the final condition, they are approaching each other. Similarly, in the case of forced damped harmonic oscillator, I said you have resonant periodic oscillation. So wherever you start, whatever the initial condition, there will be initial transients. If you wait for sufficiently long time, the system starts oscillating with a period which is exactly equal to the period of the external forcing. Resonant periodic oscillation, or in the phase plane, wherever you start, ultimately it ends up in a closed periodic motion, limiting periodic motion, namely limit cycle motion. So the most general periodic motion you can think of for a forced damped harmonic oscillator is this limit cycle or limiting periodic motion, which is a period which is equal to the period of the external forcing, capital T equal to 2 pi by omega, the external angular frequency. So that is the general nature of the linear dynamical system, linear harmonic damped forced harmonic oscillator. Now to this damped harmonic oscillator, linear damped harmonic oscillator, now let me add this nonlinear forcing term, nonlinear force term also. So to start with, I have already pointed out that in the case of the unharmonic oscillator, I have just pointed out in the case of this unharmonic oscillator with nonlinearity parameter lambda, now the solution is given in terms of elliptic function. Fortunately, even though this is a nonlinear oscillatory equation, nonlinear differential equation, because the linear superposition principle fails, you can generalize these functions, trigonometric functions, to these elliptic functions, Jacobian elliptic function. You can represent these functions in terms of appropriate mathematical representation. Okay. Hereafter, I will change this lambda to beta for certain reason, because I will reserve lambda for what is known as Lyapunov exponent. So I have changed the parameter lambda to beta. So beta is the nonlinearity parameter. So and the frequency, angular frequency, is square root of omega naught square plus beta a square, as I have pointed out. If I add damping, in general, you cannot solve this equation except for two parametric choice of alpha and beta, but I will not go into the details. More interestingly, I'm asking the question, if I consider the most general damped forced oscillation with this nonlinear force beta x cube, I've chosen in front of this harmonic oscillator with a sign minus for convenience. You can also have plus sign, because when I have minus sign, you will have three equilibrium points. The origin, the left side of the x-axis, there will be one equilibrium point. Right side, you will have another equilibrium point given by x equal to square root of omega naught square by beta plus or minus square root of omega naught square by beta, because you can equate this to 0. From that, you will have a fixed point on the left side of the x-axis and the right side of the x-axis and 0. But you will soon find this, the origin, the equilibrium point is unstable. So you start the initial condition somewhere in the left half of this phase plane. You'll find the system will ultimately, when there is no external forcing, F is 0. In that case, the problem is that you cannot solve this differential equation with all the advancements in mathematics even today. So no amount of mathematics analysis will help you to solve this equation exactly. So only through numerical analysis you can solve this differential equation. But numerical analysis in some sense is approximate, because you have to discretize these differentials d by dx by dt and d square x by dt square in terms of discreteness, and you have to introduce a discreteness parameter and so on. So you can get more and more accurate results, but it will be limited. So you can use, for example, Runge-Kutta fourth order method. So normally one uses Runge-Kutta fourth order method. By fixing these various parameters in numerical analysis, you have to fix all these parameters, which are all external parameters. So they are in your control. So they are control parameters. There are actually 5 parameters: alpha, omega naught square, beta, f, and omega. But you can, with some arguments, so-called scaling arguments, you can fix 2 of them. So that you will be left out with 3 parameters which you can change. For example, alpha, beta, f, or omega, whatever it is. So in general, it's rather difficult to change the nonlinear strength of the forcing parameter or the damping, etc. So in general, it's much more easier to change the strength of external forcing. So as an example to study the underlying dynamics, let me change this f starting from 0. So for 0, for suitable initial conditions with this negative sign, if you have a positive sign, you will have the equilibrium point is a stable one, and you will get similar results, but it's a little more difficult to analyze. But with this double well problem, it's much more easier to understand. So when I have f equal to 0, you'll find that ultimately the origin will be the trajectory will reach the equilibrium point. But now I start increasing f. I give a periodic external forcing with small strength. You find, as in the case of the force damped linear harmonic oscillator, you will have a limit cycle limiting periodic motion, leaving out all the transients. The final motion is a closed orbit. Closed orbit means it's a periodic oscillation. And now it's a limit cycle with a period equal to t equal to 2 pi by omega. Period t or period 1t oscillation. And this goes on as you increase f. It goes on until f equal to 0.35. And suddenly you find that it takes twice the earlier time. You get 2 curves and come back and they join at one point. So this corresponds to a periodic motion which takes twice this previous time at sudden critical value f equal to 0.35. And this goes on if you increase further. Now you have to change f in the second order, in the second decimal or third decimal and so on. This goes on. And now at f equal to 0.357 or so, you have, instead of period 2 motion, 2t, you get 4t, 2 power 2t. And then if you increase f further, you get 2 power 3, that is 8t, 16t, 32t, and so on. So period doubles with a small change in small alteration in the strength of external forcing and so on. Ultimately, at f equal to 0.365 for some finite value, you find it takes infinite such motions, infinite time to come back to the original state. And at this stage, the system becomes extremely complex, complicated, exhibits extreme sensitivity to initial condition. And this is the point at which chaotic motion emerges. And I can succinctly explain this in terms of a bifurcation diagram in which I have shown the dynamics as a function of the external forcing strength F, okay, which originally I call as capital F. Capital F divided by M is mass is small f, okay. And what I have plotted is the maximum value, maximum amplitude of this periodic motion, of this motion. So as long as f is small, for small values, you have one periodic motion. So you will have one extreme value, and that is I call as x1, x. And now suddenly at critical value, f equal to 3.345, something like that, you get, instead of one extreme value, you have two extreme values because of this period being increased So this corresponds to period 2, 2t motion. And then you have 4t motion, you have 8t, 16t. All those things occur in a narrower range. And it follows a geometric progression, the value in which the nature, qualitative nature of the motion suddenly changing from one periodic motion to period 2 periodic motion, period 4 periodic motion, period 8 periodic motion. Bifurcations occurs. Period doubling bifurcation occurs. And suddenly, and then at a critical value f equal to 0.365 or something like that, you get infinite such points. So that means it's completely a periodic motion. That is chaotic motion. And then if you increase f further, suddenly you get finite number of points, periodic windows, and then other kinds of bifurcations, again chaos and so on. Now you find the system enters into complex motion and with very many other kinds of bifurcations, etc. occurs. The study becomes extremely difficult, extremely complicated. The motion is extremely complicated. And in these regions, the system is extremely sensitive to, shows extreme sensitiveness to initial condition. By which, what I mean is, let me start plotting the time trajectory x as a function of time, starting with some initial condition. So x of 0 and x dot of 0. So I choose some value, okay, and then plot how this oscillator, this cubic oscillator and harmonic oscillator behaves. So I plot, and it doesn't show periodic motion because it's at some point it increases and then it comes down, it then again changes. So it doesn't exhibit periodic motion, it exhibits aperiodic motion. So the first curve I show in the blue lines, okay, the blue line. So aperiodic motion, but it's bounded because this is a physical system. It's bounded. So it's bounded between, say, here in this picture, between 1.5 and minus 1.5. So it exhibits aperiodic motion, okay. Now I change the initial condition. Initial condition, very in a small, by a very small magnitude, change the initial value, x of 0 and x dot of 0. Okay, even third decimal, even fifth decimal. So with such a change in initial condition, I plot the trajectory in terms of this pink color. I plot it. Then I find for short duration up to some 30 normalized time unit, etc., I cannot distinguish the pink and the blue colors. They follow each other. But then once you reach certain finite value, you see these two trajectories deviate. You can you can find the differences. But then again, they have to come back because they are bounded motion. But if you wait for sufficiently long time, say 45 time units and so on, you find these two trajectories deviate, and this deviation is as large as the system size itself. Okay, the system is between plus 1.5 and minus 1.5, and the deviation is as large as the system size itself at some point. But since it has to be bounded, it after executing a periodic motion, again they approach each other, but then again deviates. But if you take the average deviation, you will find that they deviate exponentially as a function of time. So this exponential deviation in time is the hallmark of this sensitive dependence on initial condition, complexity, chaotic motion. So all these things can be expressed again in terms of these bifurcations. Complexity can be expressed in terms of a quantity called Lyapunov exponent. So whenever you have bounded a periodic motion, the Lyapunov exponent will have negative values. But when it exhibits chaotic motion, it will show positive exponent. You see, wherever you have this chaotic motion, you have positive exponent. But in between, you have windows of periodic motion. Then at that point, it comes down. So you can quantify this by defining the Lyapunov exponent, etc. So there are various means of explaining this. And you can also show that in this chaotic region, it exhibits self-similar nature of the attractor. So this is a fractal dimension, but perhaps I will not go into the details. But most importantly, this sensitive dependence on initial condition, this complexity has been envisaged by this great mathematical physicist, Henry Poincaré, in the beginning of the 20th century, in his studies on the three-body problem. You know, if you have sun and earth, the problem you have solved in your classical mechanics paper, converting that into an one-body problem under inverse square type force, and you get the Kepler's laws and so on. Now the solar system, sun and its 8 planets, it is a much more complicated system. So take the motion of sun, earth, and another planet, Mars, for example. So I asked the motion, what is the combined motion of this three-particle problem? So that was a problem, and you can consider the n-particle problem and so on. So the three-body problem, for example, Henry Poincaré, he tried to solve this problem during the beginning of the 1900s and so on. And then he came to the conclusion that that problem cannot be exactly solved. And more so, he pointed out that it may happen that small differences in the initial conditions produce very great ones in the final phenomena. A small error in the former will produce an enormous error in the latter. Even an extremely small error or a small change in the initial condition can lead to a very large change, very large error in the final phenomena. If you observe the difference between the pink color and the green and the blue curves, you see the difference is as large as the system size itself. So he said, a small error in the former will produce an enormous error in the latter. Prediction becomes impossible, the consequence. You see, I have considered only a harmonic oscillator, linear harmonic oscillator, a damped force linear harmonic oscillator, to which I added a nonlinear force, a simple nonlinear force. Even that, such a simple single system represented by a nonlinear differential equation exhibits this remarkable property that prediction becomes impossible in the study of such simple systems. Okay. That was in the beginning of 19th century. So in his book on science and hypothesis, for example, he had expounded this problem of when you consider appropriate nonlinear systems. It's not that every nonlinear system under every circumstance will give rise to such sensitive dependence. So here all you have period 1 oscillation. Though you cannot find exactly this form of the solution, you can approximate, you can find approximate solution by treating this as a small perturbation. You can find approximate form of this solution. You can, again, you have periodic solution, period 2 solution, period 4 solution. It's only when you come to the external forcing strength of this particular range and beyond and so on, you get this extreme complexity. Okay. So you can have regular or periodic motion, which will not show sensitive dependence on initial condition, but there can exist form of the force of appropriate strength and so on, or appropriate nature of nonlinearity, for which a small error in the former can produce an enormous error in the latter, for which prediction becomes impossible. The consequence of which, for example, predicting weather may not be exactly possible. This is what Edward Lorenz, in his study on atmosphere, Edward Lorenz was working at MIT in the United States, Massachusetts Institute of Technology. He was an atmospheric physicist. He was working on the weather dynamics. Weather dynamics, people essentially solve Navier-Stokes equation, complicated Navier-Stokes partial nonlinear partial differential equation in order to understand how the climate changes, etc., even today. And he reduced this Navier-Stokes equation under appropriate circumstances, a very minimal form to a minimal form, in the form of a system of 3 coupled first order but nonlinear differential equations in 1960s, early 1960s. And again, in his study, again, it cannot be exactly solved. The computers were started coming into usage by academicians, and he analyzed through a simple computer. And then he came up with a result which he wanted to explain in a dramatic fashion. And in order to show, in order to tell what his results say, he said that as small a perturbation as a butterfly fluttering its wings somewhere in the Amazons in the South American forests, a butterfly fluttering its wings, such a small, minute change when you consider the atmospheric weather dynamics. So here the butterfly not flutter its wings, then the weather can grow after a few days' time into a normal weather in the state of Texas. Where is Texas? It is in the North America, in the United States, state of Texas. But because of this butterfly fluttered its wings, because the initial condition had slightly changed and the weather has changed dramatically in a few days' time, the weather has grown into a tornado. Just a couple of weeks ago, we saw in television and all what kind of damage a tornado, cyclone-like situation inside the landmass can cause, I think, in the state of Tennessee or something like that. So he said as small a perturbation as a butterfly fluttering its wings somewhere in the Amazons can in a few days' time grow into a tornado in the state of Texas. So what does it mean? Prediction of weather becomes extremely impossible, extremely difficult. Okay. For a few days, yes, as we have seen in this picture. So if you consider this as a few days, now you can make a prediction that because the change in the initial condition doesn't affect much, etc. But then after a long time, there could be very large deviation. So prediction might become impossible over a long period of time and so on. So like that, physical phenomena, study of physical phenomena, when you incorporate nonlinear force, and nonlinear forces are in general, they occur. Linearization is only an approximation and so on. So in general, then the study of these nonlinear forces can do dramatic new consequences. And these consequences, some of these consequences are contained in this diagram, for example. So you have, when you consider in this complex region, all kinds of complexity, this is one kind of bifurcation, period doubling bifurcation, inside which many other kinds of bifurcations do and can occur. Now, this is only against one parameter. If you change the other parameters in the problem, like beta or alpha, and change all of them simultaneously, the problem becomes, even now, I will say that this problem is not completely understood. So any of you can take up this problem and explore, and you may get into new results, and you can see these self-similar structures, etc., etc. So, for example, there is one oscillator about which I will mention tomorrow, I think, a bit, Matthews-Lakshmanan oscillator with external forcing and additional damping again shows this period doubling and so on, or a rotating parabola with additional damping, external forcing where the sign has been changed again. It shows all kinds of complexity, etc. Very recently, we have studied a Lennard type oscillator in my group. So which is again, this is a nonlinear oscillator of that form which I mentioned, but then there is a position dependent damping. Okay, instead of alpha x dot, I have alpha x dot, but this system has enormous importance, and this shows even much more interesting bifurcation structures, complexity, and so on, extreme events, etc., etc. they occur. And very recently, people have been studying this kind of systems. Well, nonlinear oscillators, for example, Murali Lakshman Chua circuit. So just LCR oscillator, LCR circuit I have mentioned with an external forcing, to which I add a nonlinear resistor of a particular form. You can actually design this. And in fact, Murali, Dr. Murali now is a professor at Anna University. He is the head of the Department of Physics at this point of time. And Murali, when he was a PhD student with me, and Leon Chua at University of Berkeley, we studied this simple dynamical system, just a forced LCR circuit, which I pointed out is represented by a second order linear differential equation, to which I add this nonlinearity. It's a piecewise nonlinearity that again leads to all kinds of bifurcations and chaos. So this is numerical, this is the bifurcation diagram. This is the CRO picture. So period 1, period 2, period 4, chaos, two-band chaos, and so on. So they are numerically studying this. You get all these pictures. So there are many, many such systems which exhibit this kind of structures. I think my time is running out. So I will very quickly wind up what I wanted to say. I cannot go into the full details. So you can ask the question, what happens if you consider 2 such coupled oscillators, 3 such coupled oscillators, n such coupled oscillators? So you can ask the kind of motion, collective behaviors the systems can exhibit. They lead to the notion of synchronization. Even though individual systems exhibit periodic motions, here I have plotted the phase trajectory, the time trajectory of 2 of these variables, x1, x2 of coupled Duffing oscillators, and the anharmonic oscillator I pointed out is also called Duffing oscillator. The dynamics in general, if you plot x1 versus x2, they do not show, they show some deviation. But for appropriate choice, they will show a 45-degree diagonal line. So that is synchronization, synchronized motion. But even when they exhibit chaotic motion, they can show a synchronization. So chaotic synchronization, synchronized chaotic motion. So that is a very interesting, very novel kind of collective behavior, generalized synchronization, functional dependence. So different kinds of synchronizations are possible. Unfortunately, I will not be able to go into the details of these studies. So you can consider many, many complex systems which occur in nature, which exhibits all these kinds of, their structures, their patterns, etc. So, or for example, our neuronal, the study of our brain, which consists of very large number of basic entities called neurons, which they are connected in a very complex way. And you can study them. Similarly, you can consider ferromagnetic systems and so on and so forth. So all of them, they exhibit very complex structures. So the study of collective dynamical states and what kind of ultimate structures they exhibit, you can study under different couplings. So they lead to what is known as incoherent, coherent chimera, a single group of randomly distributed oscillators and the remaining oscillators exhibiting incoherent states, etc. So multi-chimera, breathing chimera, cluster states, etc. So like our Darasuram temple nearby Tanjavur, so you can find an entity with the lion's head, the goat's head in the body, and the snake's tail, and so on. So collection of incongruent parts of different subjects. So they can be quantified and so on. So there are many, many novel, interesting properties that come about. So I will only conclude by stating that the study of nonlinear dynamics continues to be challenging and fascinating. Many novel problems in physics and associated mathematics remain unexplored. So as I have had quickly run through, so many problems being explored in recent times. One can only look for continued progress. I can already see Professor Bhaskaran appearing so for his next lecture. So I think it's high time for me to stop, except that giving some general references for some of the phenomena I have tried to point out. This Encyclopedia of Nonlinear Science, Scott Encyclopedia of Complexity and System Science, which shows, for example, tsunami or other complex behavior under what kind of nonlinearity, or a general introduction to nonlinear dynamics, integrity and chaos by Rajshekhar and myself, the chaos and nonlinear oscillators, controlling and synchronization, including electronic circuits by Murali and myself. And recently, the dynamics of nonlinear time delay systems with Sendil Kumar, etc. So these references will give you some idea of some of the recent progress that has been made in this problem. I think with this quick introduction, unfortunately, I could not cover a major portion of what I wanted to discuss, but still I do hope that I have tried to give you a very brief overview of the subject of chaos, and I do hope that it will be of some use to you. And if you have any questions, comments, anything, you can ask me, or if you have doubts, you can contact me at any point of time through email, or even in person. If you want, you're always welcome to visit our department. So thank you very much for your attention. Thank you.
Thank you, sir.
Yeah. So any questions, comments, anything? Well, many things may be unclear, as the latter part I had very quickly gone through. But students are welcome, students or scholars, they are welcome to ask any questions that they have in mind. So, Dr. Ravichandran, any questions or comments anybody wants to ask?
In the chat box,
No, sir. Actually, hello.
Yeah.
I myself, Hemant, sir, I put in chat box, I put some question. If Newton's first law is special case of Newton's second law,
Yes.
why Newton coined 3 laws, sir? What is the real need of first law? Since you talked about Newton's law first at the beginning, I'm asking.
Yeah, that's a very good question. But perhaps Newton had gone from simple systems. Newton said, standing on the shoulders of the giants of the past. So probably he had tried to understand how natural systems behave, coming from the simplest of the situations. So obviously, the simplest situation, ideal situation you can think of is that when no force acts. So you ask the question, what could be the nature of motion? So he came to the general conclusion that as long as no force acts on the system, then the system remains as such, or it moves with uniform velocity. Okay. So he came to that conclusion. So he formulated this law, and then he generalized this under the action of the forces by looking at different physical phenomena. For example, the motion of planets and other things. And then he came to the second law. So at that point of time, probably it looked natural to have a law without force and with force. Okay, asking the question of how the systems behave when there is no force, and how the systems behave when there are force acting on the system. But now, after formulating the of the necessary mathematics and so on. Now we find that perhaps the first law can be subsumed in the second law. Okay, but I think it's always convenient to start from the simplest of the picture. So I think that's what Newton had done.
Okay,
Yeah.
okay, sir. He was not aware of Galilean relativity then.
Pardon?
He was not aware of Galilean relativity while postulating, while coining these three laws.
Yeah, I think that it was all very early times. So the notion of relativity, etc., they've started emerging in due course. Yeah. Yes.
Okay, sir. Thank you.
Yeah. Any other questions? Yeah.
Sir, there is one more question in the chat box, sir.
Chat box, where do I find? I think there is some problem in my thing.
Shall I read it out, sir?
Just a moment. Yeah, I can.
What are the initial conditions for origin of universe? Can be butterfly effect applied in the origin of universe?
Yeah, initial condition of the origin of the universe, I think it's the Big Bang. I do not know whether one can specify the initial conditions for the origin of the universe. I do not know whether Bhaskaran, do you have any answer to that question? Is the initial conditions for the origin of the universe? I do not think that anybody can with definiteness tell the initial conditions for the origin of the universe, the Big Bang. So what was there before the start of the point of time, starting of the time, what was there, nobody knows. Okay. So I think I will not be able to answer that question. Yeah.
Thank you.
It's an extremely difficult question. What was the origin? Because the structure of the universe at that point of time itself is extremely fluid. So probably that cannot be exactly given, I think.
Thank you, sir.
Dr. Bhaskaran, unmute. Muted சொல்றாரு Dr. Ravichandran.
Yes, sir. Do it, sir. Sir, we will unmute Dr. Bhaskaran, sir.
Thank you. So,
Yeah.
Mr. Kannan, please unmute Professor Bhaskaran.
Yeah, I am unmuted. Do you hear me?
Yes.
Yeah.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Fine,
Oh,
sir.
wonderful,
Fine, sir.
wonderful.
Good morning, sir.
Yeah, Bhaskaran.
Very good morning.
Yeah, good morning. Good morning, Bhaskaran. How are you? You are in Los Angeles. So
Los Angeles, that's
I
right.
hope things are fine there.
Things are fine, yeah.
Yeah, there is an interesting question by a young student. He says,
this is about the origin of the universe. And
initial conditions of the universe. So
it's
my answer is that I really do not know, because that's too.
Yeah, I also do not know, but I have been mystified by the mathematics.
Yeah.
Because people tell me that before that singularity,
yes,
the notion of space and time does not exist mathematically.
Yeah.
Because according to our intuition and experience,
yes,
there is the notion of past and there is notion of space around us.
yes,
Apparently, if you look at the mathematics of Big Bang theory and the Big Bang solution,
yes,
there is nothing like a space and time before that.
yeah,
So many things become more mysterious than what people think.
yeah. So the question, what was there before that, I think nobody knows, and why there was nothing before that, etc. So these are all, in my point of view, is also a question of philosophy, and so yeah. I think I have no answer for that. So that's a very difficult question. Okay, then. There are no more questions, so let me thank Dr. Ravichandran for giving me an opportunity. And yeah, there is also a question, sir. What are your thoughts on cosmic censorship hypothesis? What is that cosmic censorship hypothesis? Well, I'm not aware of. I really do not know much about that. Perhaps, yeah. Perhaps I can think and answer later on. Okay. Censorship.
என்ன இதுல வந்திருக்காருப்பா?
In what is that cosmic censorship? I'm not aware of it. Okay. So
I have heard the name, but I really don't know what it is.
Yeah. Probably I have also heard of it, but yeah, I'm not a cosmologist. Unfortunately, I cannot answer that question. Yeah. Okay, then I think at this point of time, I will close my lecture and I will give my lecture tomorrow afternoon. Okay. Thank you very much.
Thank you, sir.
Yeah.
We'll start the next session. I invite Dr. R. Ramasamy, Assistant Professor, to introduce our speaker.
So let me unshare. I think I have to unshare or have to leave.
Yeah, you have to unshare.
I have stopped, sir.
Yeah. How do I do that? Where is it? I do not find. So I think I will just leave and then I will come back.
Good morning, everybody. I am Dr. Ramasamy, Department of Physics, going to give brief profile of Professor.
Sorry, sir, no sound, sir.
Sorry? Sound is there. No sound.
So shall I start sharing the screen?
Sir, please wait, sir.
Okay,
One of our
okay,
staff member will introduce you, sir. Dr. R.R., your mic is unmute. Now it is unmuted. Okay.
Good morning, everybody. I am Dr. Ramasamy, Department of Physics, going.
Sir, your voice is not audible, sir.
Your voice is not audible.
Sir, check your headphones, sir.
Still not audible.
Dr. R.R., your voice is not audible.
Maybe I will introduce myself.
No, please, sir. Let you have the pleasure of introducing yourself, sir.
Now it is audible.
Remove your headphone, then pin the same, sir.
Okay, now it is audible.
Slightly, we are hearing your voice.
Barely.
Hearing.
Sir, now it's audible, sir.
I am Dr. Ramasamy, going to give brief profile of Professor Bhaskaran, sir. Professor G. Bhaskaran is a theoretical physicist at the Institute of Mathematical Sciences, Madras. He is a distinguished professor at IIT Madras and distinguished visiting research chair at Waterloo, Canada. Professor had his school. The name of the school is St. Mary's High School, Madurai. College, he did both UG and PG, Tyagaraja and American College at Madurai, and completed his PhD at the famous Indian Institute of Science, Bangalore, in 1975. In 1983, Alfred Kessler Award in Physics was awarded to Professor Dr. Bhaskaran sir, and in 1990 and 2019, he received Shanti Swarup Bhatnagar Award and the Shastra G.N. Ramachandran Award, respectively. He writes articles and gives lectures on popular science in Tamil. I hand over the section to Professor Dr. Bhaskaran sir. Thank you.
Thank you very much, Dr. Ramaswamy. So am I audible?
Yes, sir, audible.
Okay. So I will start sharing the screen. So is my slide visible?
Yes, sir, visible, sir.
Okay, wonderful. So
Is it
thank
possible to
you.
go for slideshow, sir? Is it
Yeah.
possible to go for slideshow?
Oh, is it not slideshow yet?
Yes, sir.
I see. Okay, I will. That's what I am going to the slideshow mode. In my screen, it is slideshow.
Yes, sir.
Start
For the
from
first
first slide.
Is
Is it slideshow mode now?
Not yet activated, sir.
So there is a problem. Let's see, edit view. Slide. So I'm asking for slideshow. Is it still non-slideshow mode?
Yes, sir. It is not available.
Okay. So what I will do is I will try PDF file.
Okay, sir.
Okay. Is it clear? Is it a slideshow mode now? Hello?
No, sir.
No.
No, sir.
No. Slideshow is there. Sir, there is a slide in the top, sir. Please try to click on that. Before the slideshow, there is a slide
I'm
option.
trying that, but what I see is not what you see.
Yes, sir. Yes.
Sorry.
Okay, sir. If it, no problem, sir. I think this will be enough. For,
So 1 minute. Just pardon me. I will stop sharing and then start sharing again.
Oh, yes, sir.
I'm not able to come out of.
Very well, sir.
1 minute. Yeah. So let me. Do you see my?
Not yet, sir.
Not yet. Sorry. Do you see it?
Yes, sir.
Okay. So I think there is a problem with the slide mode. So shall I proceed?
Yes,
with
sir.
this?
Please carry on with this, sir.
Okay. I'm very sorry, extremely sorry for this mess up.
Nothing, sir. Don't do this, sir, please.
It's not new to me. It has happened before. So I am yet to learn.
Okay, sir.
So thank you very much, Dr. Ravichandran and Professor Lakshmanan for inviting me to talk to this young audience. So today I am going to talk about quantum materials. And so before I begin, it's a difficult time for us. So I wish you and your dear ones a very happy New Year 2022. So this is what I plan to do in the next an hour or so. I will just try to convince you that the world is quantum. Then I will discuss briefly the world of materials and phases of matters, and then talk about remarkable future prospects of quantum computers and like issues of matter in biology and living matter. So I'm going to be very sketchy and very brief in whatever I'm going to say. It will be like storytelling. It's like you come to Trichy and you have half an hour and you show that this is Malaikote, this is the cathedral, and this is the Kaveri River, Kollidam, and so on, and then go. Then it's for you to come later and visit places one by one and enjoy. That's what I'm going to do because the time is limited. So I plan to give 2 lectures. In the first lecture, I will talk about quantum matter. So in fact, it's an opportunity to be very happy that most of us are practicing physics as our profession. And physics is very powerful indeed. And it deals with subquarks or the structure of quarks, what is inside quarks too, the very cosmology. In Professor Lakshman's talk at the end, there was a question about the beginning of the universe, Big Bang, and so on. So physics is so powerful, it addresses a wide variety of questions: atoms, molecules, fluids, rocks, minerals, metals, magnets, planets, nuclear fusion, lightning, corrosion, nature of space-time, birth and death of the universe, photosynthesis, star formation, superstrings, color of butterflies, life processes, and so on. It's amazing that with the physics that we have learned in the last couple of centuries, we are able to answer meaningfully some of the questions. Still, the nature is inexhaustible, but as humanity, we are making slow progress, and it's very enjoyable. So physics addresses things small, big, and complex. So please don't be apologetic that you have taken physics as your master's or you have taken a research career, because this is what I find whenever I meet students, when I give college lectures in colleges. I ask the students, are you happy? They said, no, sir, I'm not happy because I wanted to go to engineering or computer science. I didn't get it. I have taken physics. In fact, there is no reason to be apologetic like that at all, because the physics that you have taken is powerful and it gives you power. And of course, jobs, good jobs, if you only tackle the problems properly. So matter is quantum. There is no question about it. For example, if you take a hydrogen atom, if you think about a classical proton and an electron orbiting around each other, classical electrodynamics and the classical Newton's laws tell that eventually the electron will get attracted and the orbit will fall into the nucleus, and there will be nothing. Whereas in quantum mechanics, we have so-called stationary states or orbitals. So the ground state is a stable thing. So stability of atom comes from quantum mechanics. Similarly, when you form a H2 molecule or water molecule, the basic binding is quantum mechanical. We talk about covalent binding. Similarly, the van der Waals forces, for example, between two graphene layers in graphite or hydrogen bonding in water is very quantum mechanical. And even the hardcore repulsion between molecules, you can't push two H2 molecules closer than some distance. There is a strong repulsive force. It comes from Pauli exclusion principle, because you are forcing an electron into the same quantum state as another electron. So there is an effective repulsion. So hardcore repulsion comes from Pauli principle. And even more remarkable is, this is something that we don't learn in our curriculum, even though it's there, oxygen molecule is not a spin singlet molecule. In fact, in the ground state, it's a spin 1 system, to the extent that if you take a liquid oxygen at very low temperature and then bring a magnet, the liquid will be pulled towards a magnetic pole, because the magnetic field of the magnet will polarize the spins of the oxygen molecule. So the very air that we breathe, which contains oxygen molecule, is a quantum object. And the spin 1 character of oxygen is very fundamental in in oxygenation of our, because these oxygen molecules get absorbed by hemoglobin molecule proteins, heme proteins, and there the binding of oxygen molecules to the heme group is very quantum mechanical. It sensitively depends on the spin 1 nature of oxygen molecules. So everything is quantum. But of course, when we do physics, we conveniently separate it into quantum physics and classical physics, because it turns out for many of the descriptions, depending on the energy scale and time scale, a classical description is sufficient. But there are situations wherein it's not sufficient. In fact, that's what we will focus on. For example, if you talk to Professor Lakshmanan, he will talk about beautiful phenomena in quantum magnets, soliton dynamics, soliton collision, and magnetization dynamics. Basically, it's a classical set of equation using some variable called magnetization. But the origin of magnetization may be quantum mechanical, but the mathematics we use is basically classical. But this situation dramatically changes in many situations. Okay, and it's a fact to realize, which is what we all learn in our BSc and MSc, that matter is quantum even at room temperatures. For example, Einstein worried about a very simple experimental observation, that specific heat of a solid disobeys de Long-Petit's law, or classical thermodynamics. The specific heat per degree of freedom is not constant. It's not kb, but instead it starts deviating and vanishes at low temperature. So Einstein worried about it, and he brought he gave birth to what is called quantum theory of solid. He said that every atom is sitting in some kind of potential well provided by the neighbors, so it's undergoing harmonic vibration. So he calculated using quantum laws of this harmonic oscillator the specific heat, and he found deviation from classical law. So if you take diamond, the Debye temperature is about 2000 Kelvin. If you take sodium chloride, it's about 300 Kelvin. So even at room temperature, there is strong deviation of specific heat that you could measure in the lab from classical values. So that's quantum mechanics. Now, if you take any body at room temperature or slightly above, it emits radiation. And if you look at the distribution of the radiation as a function of frequency intensity distribution, it's a Planck distribution where Planck's constant explicitly appears. So black body radiation can be given only by a quantum object. So it's a quantum phenomenon. Similarly, if you take a very simple metal like copper and calculate the electronic specific heat and separate it from the lattice specific heat, and it's almost a constant. And similarly, if you measure magnetic susceptibility of copper, or let's say silver, the electronic susceptibility is paramagnetic. Similarly, if you measure resistivity of metal, it has some characteristic behavior as a function of temperature. Now, all these simple looking experimental facts are deeply quantum mechanical in origin. For example, without the notion of Fermi C, that is electrons occupying some states in momentum space up to some energy level, and the excitations thereof, they alone can explain all these very elementary facts. So we say that matter is quantum even at room temperature. But the important point is, can we make use of it to our advantage? Because we have been mostly using classical physics and classical phenomena. It turns out some of these excuse me, beautiful quantum phenomena can be made use of. We will see slowly. So as I said, materials are quantum, be it gas, liquid, polymers, smart materials, shape memory alloys, everything is quantum. And a staggering variety of phenomena, processes and occur in material science. And even more fascinating is biological matter and living matter, which is very mysterious. We understand very little about it, but slowly understanding is growing. So what do we do in condensed matter physics or in solid state physics or in quantum material? Firstly, there is extensive exploration of material, minerals and around. The old material is graphite, and it has been explored for decades. And in the last couple of decades, there are fascinating new understanding that we have got. It's a very thriving and growing field. And based on that, there are phenomena called 2D materials. Similarly, inspired by various experiments we do and inspired by theories, we synthesize new materials. In fact, if you go to any labs in Tamil Nadu or in India, anywhere, very often people synthesize and characterize new materials. They grow new materials, they grow single crystals and so on. So there is and because the periodic table is very rich, there are many atoms and many atoms. So there are many possibilities, exponentially large number of possibilities. And what is remarkable is they come with their own signature and own properties. And in the last 15-20 years, there is a new development called quantum simulators. That is, the materials that we see in nature or we make are very complex. They're too complicated. There are so many factors. Is it possible to create synthetic solids? For example, you can take atoms and cool them down to nanokelvin temperature and make them travel and dance in the presence of some optical traps. So they could weakly interact and form solids, liquids, Fermi liquid, and so on. So they are called synthetic solids. Excuse me. Sorry, let me drink some water. I'm having some cold. So extensive exploration of materials and minerals around us and synthetic novel materials and quantum simulators of solid state quantum phenomena. In fact, this is a very attractive and emerging field. Cold atoms, ion traps, optical tweezers, and so on. So some of you young people, who are listening to my lecture, please take note of these names, because there is Google. It will give you all information that you wanted about all these things. But these are all very fascinating developments. Quantum simulators of solid state. In fact, they also have started becoming a substrate for future quantum computation. Lots of works are going on using ion traps as quantum computers, cold atoms as quantum computers. Excuse me. I caught some cold yesterday and so experiments in condensed matter physics or in materials is our ultimate guide. We theorists make statements sometimes that they are false. So finally, we have to answer nature and we have to understand experimental results. There may be surprises. And the experiments start from a very simple one that we learn in our high school or in colleges: calorimetry, resistance bridge, magnetic electric susceptibility, strength of materials, synchrotron radiation, muon factory, and a variety of spectroscopic techniques, visible spectroscopy, infrared spectroscopy. Professor Ramakrishnan will talk about it, NMR, NPR, and so on. And then fascinating transmission electron microscopy, scanning electron microscopy, atomic force microscopy, scanning tunneling microscopy, scanning tunneling spectroscopy, and so on. So there has been remarkable progress in the field of experimental material science. And they are giving us many new insights. Okay. And theoretical, and one thing about condensed matter is it seems to be inexhaustible. Like, Professor Lakshmanan, I believe, talked about chaos. See, chaos occurs in many places, in many condensed matter phenomena. If you focus on chaos alone, there are so many organized phenomena, surprises, fractals, collective phenomena, and unexpected regularities in one nonlinear mathematical system. And you can imagine how it's going to be in condensed matter. So there are theoretical methods, which is system-dependent models, mathematics, phenomenological, microscopic, and so on. And what is important is, in condensed matters, phenomena emerges, and there is a hierarchical structure. There is a small story I will tell. I think there is a book, I believe, by name End of Physics, because some group of people started saying that now that we know the Schrodinger equation and also Dirac equation and about quarks and standard model and so on, there is nothing more to be understood. Everything else is chemistry. And P.W. Anderson, a famous Nobel laureate, responded to this kind of attitude in 1972 in a very famous article called "More is Different." I strongly encourage you to read this article. It's a very delightful, simple article. And in fact, there is a nice article on this paper in memory of P.W. Anderson by our friend Rajaram Nityananda in the journal Resonance. We will also want to point out that it's very important for young students to read popular science articles. There are very good, outstanding like Science Today, or Physics Today. Then Resonance is a beautiful magazine published by Indian Academy of Sciences. You see very readable articles by students, and +2 students, MSc students, BSc students, and so on, and then faculty. Try to have a look at it regularly. It's meant for students and faculty, and it's open access and free. So, and if you go to this special issue, there's a beautiful article by Rajaram Nityananda about more and different. So what Anderson says is, I think Niels Bohr gave a beautiful example long back. He was talking with a very distinguished biologist who was talking about emergent phenomena in biology. Because at the end of the day, we are made up of atoms and molecules. They combine together to form some amino acids. Amino acids combine to form proteins. Nucleic acids combine to form DNA, and then they combine and continue to give cells life and so on. So they call it as hierarchical phenomena and emergence. And Niels Bohr is supposed to say, physics is full of emergent phenomena. Let me take turbulence phenomena in water. Where did it begin? You start hydrogen atom, there is no turbulence there. You take oxygen atom, there is no turbulence there. Put them together, you form a water molecule. Then bring some more water molecules, you start hydrogen bonding. You bring more of them, there are new things emerge in terms of structures. And then you get water and there is turbulence. And turbulence is one of the most fascinating and still unexplained phenomena. So as things are added in condensed matter, new things continue to emerge. So that's what Anderson said, more is different. That is, when things are more in number, there are symmetry breaking phenomena, novel rigidity, and a variety of things happen. So what is remarkable is that you cannot predict what will happen in the second level. You'll have to, together with experiments, look at it and formulate laws for every stage. So I suggest that please have a look at this article, More and Different, which I believe is reprinted in this issue with commentary by Rajaram Nityananda. Okay, so I wanted to tell you that there are staggeringly wide variety of methodology in condensed matter physics. It may be intimidating sometimes it may be boring. For example, there are, we learn statistical mechanics, mean field theory, and so on and so forth. And then there are very profound new mathematical, non-commutative geometry, K theory, category theory, and so on. And various things are there. But the most important thing I keep telling young MSc physics students and research scholars, both experiment and theories, is that you can't ignore quantum mechanics, mathematical physics, and books like Kittel. Because coming from Tamil Nadu, I know that there is an aversion or fear of quantum mechanics or fear of mathematical physics among students. I can tell you, as my friend Rajaya Simon regularly says, quantum mechanics is very simple. It's just matrix manipulation. If you take a system and focus on the core quantum state, it is described by some finite dimensional matrix. So the whole of quantum mechanics can be described as playing with matrix algebra. Excuse me. So, and associate mathematics like calculus, differential equations cannot be ignored. And many students, including theory students, try to ignore it. And I also want to talk about solid state physics book by Kittel. I remember when I was first exposed to solid state physics, it was one of the most boring subject, even though I had good teachers like Professor Balasubramaniam teaching me in Madurai Kamaraj University in the MSc extension course. It was very boring because if you take Kittel, it has a lot of phenomenology and very elementary mathematics. And it's not attractive. There is no Lorentz invariance. It's not a very fancy mathematics. But if you look at carefully what Kittel does, he goes a long way by using simple mathematics, phenomenological arguments, and so on. So I keep saying that please don't ignore Kittel's book. Once you master Kittel, you can go to quantum theory for solid. Incidentally, I had the pleasure of meeting Professor Kittel in California many years ago when he was 93. So he was actually, I was asking him, what is he doing these days? He says, I'm editing my 7th edition of my book. And also I'm enjoying growing vineyards in my garden. So he was living about 50 miles away from Berkeley. And then he used to do gardening. And in fact, he lived up to a ripe old age of 102. Anyway, this is about Kittel and methodology. Now, when we talk about quantum materials, immediately what comes to our mind are the phases. For example, if we learn the gas, liquid, solid, plasma, and phase transition critical phenomena, then when you look at solids, you have metal semiconductors like diamond band insulator, then so-called Mott insulators, excitonic insulators, ferro-antiferroelectrics, charge density waves, spin density waves, ferromagnetism, antiferromagnetism, superconductors, superfluids, and so on. Slowly, over years, new phases have come. Each one of them is intricate and beautiful, and their macroscopic behavior can be described in terms of classical equations like Ginsburg-Landau theory or Landau-Gilbert equations with using magnetization or order parameters variable. But at the fundamental level, it's quantum. So topological insulators is a very fancy thing these days. Quantum spin liquids, light-induced transient superconductivity at room temperature in cuprates, cold atom simulation of solid state physics, and so on. So there are order parameters, topological orders, quantum. So there's a wide variety of phenomena that are associated with quantum materials. I'm sorry to be giving you many names, but as I said, please make a note of it, or you can look at it after my lecture is over and go to the website and look at, for example, if you look at topological insulator, there are beautiful recent developments, beautiful articles on that. It connects to very unexpected things like Witten effect or theta term that appears in quantum field theory. Beautiful connections are made through this simple looking condensed matter phenomena. Now, one thing that you would have noticed is that when we do condensed matter physics, we are not just after numbers. For example, when you look at specific heat of solid, it's not that we are interested in fitting the experimental results to a theoretical curve. We are interested in the overall behavior, like what Einstein worried, that a specific heat which is constant comes down exponentially to low value at low temperature. So that was a qualitative change. So he brought in the notion of an oscillator being part of a solid. At each atom is like an oscillator. Then Debay's theory came, coupled oscillators and so on. So what we do is we create and look for new notions and concepts. So these are all not the precise numbers. These are all the meaning of real understanding. So opens new windows, shows the next step for basic science and technology. Just to give you an example, as band theory was being developed, it became very clear there are filled bands and empty bands. You can add an electron in the empty band and you can create a hole. So this missing electron in a valence band called a hole and the electron in an empty band became fundamental in the discovery of transistors in the hands of people like Bodin and others. So semiconductor revolution began with a very elementary notion which we take for granted. Similarly, the concept of gauge invariance, which is very fundamental in electromagnetism, Anderson localization in disordered electronic system, became fundamental in understanding quantum Hall phenomena, which led to new standard for resistance and all kinds of beautiful things. It's like a room temperature quantum effect. And the concept of linear superposition and quantum entanglement, that's very basic in quantum mechanics, is going to help us in building future computers. Similarly, sharpening the concept of phase in a BCS superconductor theory led Josephson, Anderson, and others to phenomena like Josephson effect, metrology, quantum switches, and quantum computers, and so on. So this is something that's very important. We are not interested in understanding or fitting curves to experiments precisely. We are interested in qualitative behavior and concepts behind them. That's very, very important. So in fact, in some of the examples that I'm going to tell you, it will come out hopefully. So please remember this. So right and new concepts to describe a wealth of phenomena are more important than getting things right in terms of number. In fact, P.W. Anderson in his book Concepts in Solids has a section called Quantum Chemist's Fallacy. It's a lesson to many of us, because these days there is a lot of people who do very detailed calculations and finally bring out a curve. We do not know what has gone inside to giving this curve. So there may be very simple concepts behind these curves which we are missing. So emphasis on numbers, quantitative understanding is different from first qualitative understanding and then going quantitative. Okay. Finally, if you come to solid state physics or quantum materials, it boils down to the following. It uses non-relativistic quantum mechanics, many body theory, sometimes relativistic effect or spin orbit coupling. Then it uses electrostatic forces. They are the building block. And then, everything can be described in terms of this fermion, boson, Pauli principle. And as we know, we using brick, stones, and mortar, we can build Taj Mahal or make the finest sculptures. In the same way, using this basic building block that you learn in Kittel, all the things that I'm telling is there in Kittel. You can build theories and understanding and new devices, which are currently part of nanoscience and all these modern developments. Okay. On another front, study of materials has been a source of deep and profound ideas. There is a famous quote by Byron, I think, seeing the universe in a drop of water. Now, I just flashing a few remarkable developments historically. Superconductivity theory was given by Bodin, Cooper, and Schiffer. And then while trying to understand it from the symmetry breaking point of view, Anderson discovered a phenomena which is called Anderson-Higgs phenomena. And that gave an idea as to the origin of mass of elementary particles like electron, quarks, and so on. So there is a superconductor like lead, a piece of lead in the laboratory, and quarks. So at the level of mathematics and physics, there is a deep similarity. So a good understanding of superconductor gave Anderson-Higgs phenomena and Higgs Nobel Prize some years ago. Incidentally, Peter Higgs was the collaborator of Professor Lakshmanan. I think Professor Lakshmanan was a postdoctoral fellow with famous Peter Higgs. Now, then liquid crystals. You know what is a liquid? You know a liquid crystal. If you take a liquid made up of molecules which are rod-like, for example, or banana-like, they give you phases which has liquid character and crystalline character. And there are fascinating defect structure like dislocations, but more profound one. And who expected that some of these things will become a laboratory testing ground for cosmological models? How in cosmology, as the universe began after the period of inflation, how condensation took place, how large structures were formed, can be studied in the laboratory, thanks to my friend Neil Turok, and many fascinating developments have taken place. Similarly, in fact, in the next lecture, I will elaborate on this. Studying copper or silver containing a small amount of parts per million impurities of manganese or chromium gave ideas, profound ideas, which has come to new ideas in the field of neural network, deep learning, and so on. In fact, it led to Paris's Nobel Prize last year. So I will talk about it in detail next. So, for example, if you go sit on a beach, or if you go to a beach, or just look at a pile of sand, and then try to put sand on top of other, they will organize in a pyramid form, and the sand particles will keep falling down. And looking at it carefully, people like Purbach and Deepak Dar introduced the notion of self-organized criticality, which has implications well beyond sand piles. And fractional quantum Hall effect has implications to the origin of fractional charges, of course, and gauge theory and so on. Similarly, new developments, for example, two-dimensional materials, electrons confined to 2D sheets, these are all quantum materials, have given profound implications, like connected to Knott's theory, Jones polynomial, Chern-Simons theory, and Ed Witten's fields modeling winning work is rests on some of these understandings. So it's amazing that a dirty condensed matter phenomena can have profound implications at scales which are farther removed from our day-to-day scale. Okay, this already I have. This is something, since it's close to home, I should mention it. Chandrasekhar, the famous Chandrasekhar, was a student at Presidency College. He learned about Pauli pressure from Sommerfeld, because Sommerfeld was visiting Presidency College before he went to Calcutta to give a series of lectures. So he learned about Pauli degeneracy and Pauli pressure. And then at that time, he came across a paper by Fowler about stability of stars. So he worked on it as a undergraduate PhD, as a BSc student, and applied relativistic correction, and said that a gravitational pressure in a falling star, collapsing star, can be held by Pauli exclusion principle and a Pauli Fermi degeneracy pressure, which is working outwards. So that led to Chandrasekhar's mass limit and white dwarf theory and so on, and the beginning of black hole physics. So a down-to-earth understanding of metals like copper, silver, and so on gave rise to wonderful phenomena that's happening elsewhere in the stars. It's again a power of condensed matter. Now, if you look at elementary particle physics, when you learn it, you talk about electron, positron, proton, muon, and so on, and then bosons, photon. Now, similarly in condensed matter system, dirty condensed matter system, as I said, there is electron, hole, and composite fermion, phonon, magnon, resonance, and a variety of quasi-particles. And in fact, it's very laudable, and it's very likely that future quantum computers will be based on some of these things like spin-ons or holon or Laughlin quasi-particles. So emergent particles in condensed matter physics have very profound consequences. And also, material science is vital in engineering science, like transistor technology and semiconductor physics, electrical, civil engineering, mechanical, chemical engineering developments all depend on memory star, nanomechanics, and so on. So there is a fantastic interplay between material science, quantum materials, and modern technology. I need not emphasize that. So before I have about, I think, 30 minutes or 20 minutes, I will touch upon few examples of very simple looking condensed matter system, but that teaches a lot. For example, if you take carbon, one of the lightest elements, and a large part of us are carbon. Carbon in its stable form is a diamond, but it occurs also as graphite. And then it was discovered not long back, thanks to astrophysics, because people doing astrophysics found through spectroscopy evidence for presence of molecules of carbon containing tens of carbon atoms. So chemists worked hard and found that C60 or fluorine is a very stable molecule. That began the revolution of carbon nanotubes and so on. That is, 60 carbon atoms can form a stable, nearly sp2 bonded structure, or C70, then carbon nanotube. And now, to understand all this physics, there's a very simple, delightful tight binding model that you can work it out. What you do is, you say, okay, finally, what is graphite? A single layer of graphite is graphene. So there is a famous sp2 bonding you all have learned in quantum chemistry, that carbon has 2s electrons and 2p electrons. There are 4 electrons. So 3 of the electrons hybridize, according to Pauling, into a so-called sp2 hybridized state contain at 120 degree and form beautiful honeycomb structure. Then you are left with a 2pz orbital, which is coming out of this plane, and it contains 1 electron. So all the physics of graphene, graphite, carbon nanotube, and so on is governed by this valence electron, which forms a honeycomb lattice. This valence electron hops from one side to another side, which is described as a quantum mechanical hopping. So as I said again before, please don't be intimidated by whatever I say. It's very simple. This is again some matrix manipulation at the level of 1 particles. You can do it yourself, and in fact find the band structure of graphene, which was found several years ago by Wallace. Okay, now it's kind of ruling the game in graphene structure. Now, for example, if you take a graphene sheet and cut it and roll it, you can, depending on how the tailor cuts it, you can have what is called a chiral nanotube. In a chiral nanotube, if you go around, there is a helicity, whereas in an armchair nanotube, non-chiral, there is no helicity. So that makes a difference in its electronic property. A fundamental structural property makes some of them metallic. For example, in an armchair will be non-metallic, this will be metallic, and so on. And these have been studied experimentally and theoretically, and very beautiful experiments have been done trying to understand electrodynamics or electron dynamics in these carbon nanotubes and wire. And there are attempts to make memory devices, transistors, single electron transistors, and a wide variety of things, all based on very simple tight binding model, that is electron hopping on a lattice. And nothing can be simpler than carbon system, because it's a monoelement system. There are not many different type of atoms, just carbon. That alone has so many rich variety of phenomena. Recently, we heard about twisted bilayer graphene and rhombohedral stack graphene. Wonderful developments are happening in just pure carbon system. So that's where emergence is. That is, if you look at carbon alone, you won't say that it will lead to carbon nanotube. Now put carbon together, you form C60 molecule, or you form carbon nanotube or graphene sheet, and many, many things continue to happen. Now, in the next 10 minutes, I will talk about my favorite subject, superconductivity. You all know what's a superconductor. Kamerlingh once, around 1910, discovered that if you take mercury and cool it down to low temperature, around 2 Kelvin, resistance drops to absolute zero, essentially. Now, later, very quickly, people said that this is a quantum mechanical phenomena, like it's a quantum mechanics on tabletop, because we say quantum mechanics is at work at the level of hydrogen atom or individual electron dynamics at short length scales and so on. Here, there is a macroscopic quantum phenomena happening in meters of wires. For example, if you take a current loop of superconducting mercury wire and inject a current, the current will be flowing for literally millions of years, because the decay time is so long. So if you think about classical electrical current, it will always dissipate energy and stop after microseconds or milliseconds, depending on the system. Here you have a long-lived thing. It can be only quantum phenomena. The same way you have stationary orbits around hydrogen atom. Here, there are stationary orbits of this macroscopic quantum wave around a wire. So there is quantum interference of matter wave, and all these things are at the heart of superconductivity. This was discovered. Now, there are immediately effects like Meissner effect, where it says that if you bring a piece of magnet close to a superconductor, the magnetic field will be expelled by a superconductor. Whereas if you take a metal like copper, the magnetic field will penetrate copper. Whereas in a superconductor, it will be completely expelled. That's called Meissner effect. So this can be made to our advantage. We have magnetic levitation and superconducting trains, and then there is a phenomena called the Josephson effect, which is a very non-trivial effect discovered by Josephson. That is, you bring in two superconductors, make them touch each other through an insulating layer, a thin insulating layer. What you find is a remarkable phenomena. Even without applying a battery, there is a current that flows between the two superconductors, which is determined by what is called a phase difference. I will not go into the detail. Similarly, if you take this Josephson junction and connect it to a battery, a DC battery, a AC current starts flowing. These are all pure quantum phenomena, which depends on fundamental quantities like charge and Planck's constant. And there is a phenomenon of quantized vortices. The same way electron angular momentum is quantized in a hydrogen atom, supercurrent is quantized around vortices, magnetic vortices in supercurrent. It's a quantum phenomena, Andreev reflection, and so on. So the variety of phenomena occurs in a very dirty lead or mercury at very low temperature. That's called superconductor phenomena. I encourage students to look at website or books. And also, I also wanted to tell you that whenever, suppose you are interested in theory of superconductivity, please go to the masters. Try to read the original article of Bodin, Cooper, and Schaefer. It's always a good idea to go to the masters because they tell you what is really going on without decoration. So you can read their mind and you can actually contribute. So it's very important. So please have a look at some of these original papers. Now, these are all the three great men. I have been fortunate to have met John Bodin twice. Once as a PhD student at IISc Bangalore. It was a very hilarious incident because John Bodin is a man of few words. So people keep talking to him, he won't answer, he will be just nodding his head. So the professors at IISc didn't know what to do. So they found me and they handed him over to me because my professors were away. So I was sitting alone with Bodin, the two-time Nobel laureate. So very soon I started telling all the things that I was doing at that time. And it became a very exciting conversation, which lasted for 1 hour. So it was very encouraging. So I was very happy. Then later in '87, I visited Urbana-Champaign to give a colloquium on resonating valence bond theory of superconductivity, and he was in the audience. And when the colloquium was over, people came and shook hands with me, and I thought I gave a good talk. He said, no, you didn't give a good talk. It was an okay talk, but you made John to ask 2 questions, which has never happened in the history of the colloquium, because he comes and sits and listens. He never asks questions. Then later I had a very delightful discussion with John Bodin. Then Bob Schrieffer, thanks to International Center for Theoretical Physics, I met him several times there. Remarkable individual, remarkable physicist. So they discovered, after nearly 50 years of discovery of theory, experimental discovery of superconductivity, they gave a theory of BCS theory of superconductivity, which is a very Nobel Prize winning work and very important. Now there was a revolutionary development in 1986, thanks to new materials like cuprate, thanks to Bednarz and Muller. They found that a very complex material, lanthanum copper oxide or mercury copper oxide, at low temperature became superconductor. It's a very bad metal. The conductivity is way less compared to copper or silver, which never become superconducting. Whereas these bad metals become superconducting with a TC, which went up from 30 to 40, 90, and 130. And so it was not clear what is going on, because it was very clear at that time, right at that time, that these systems are bad actors, that they don't obey the standard beautiful BCS theory. Something else is going on. And I was fortunate enough to be there in the right place at the right time with the right person, so I got involved. So before high temperature superconductivity came, the progress in transition temperature was very gradual, linear. So it started at 3 Kelvin with mercury. Then by the time we have 1986, it was 23 degree Kelvin at niobium germanium. Nearly 7 decades, very slow progress. Then came a revolutionary development in 1986 by Bednarz and Muller. The transition temperature jumped from 23 to 33 And in Bangalore, it jumped to 70 and then 90 and then nearly 180. This was a big jump in few years. So these are revolutionary development in the field of high temperature superconductivity. There are beautiful articles, review articles and books about this. Please have a look at them. Now, lately in the last 5 years, remarkable developments have taken place. I again urge those who are interested in superconductivity to have a look at these fascinating developments, which are just brewing. For example, Erametz, my friend from Germany, the Russian from Germany, he pressurized hydrogen sulfide, what we learn as stinking gas in our school chemistry. You liquefy it and solidify it and apply great pressure like 200 gigapascal. By the way, just to get a feel for the pressure, the center of the earth, the pressure is like 300 gigapascal. So you'll have to create such a large pressure in a tiny volume, and then it becomes superconductor at 200 Kelvin. Then Ranga Dayas from Sri Lanka, who is a professor at Rochester, just 2 years ago, he synthesized a carbonaceous material that is involved in carbon, hydrogen, sulfur. We still don't know the structure clearly, but remarkably at 260 gigapascals, it becomes a room temperature superconductor. So this holds the world record, but unfortunately, it's not at ambient condition. You have to apply pressure, and applying high pressure is a difficult phenomenon. You are sitting in, many of you are in Trichy. Professor Arumugam from Bharatdasan University is an expert on high pressure. You should visit his lab. He applies high pressures and make things, work remarkably well. Then just 2 years ago, there was a remarkable claim by Thapa and Pandey from Indians of Science, soon joined by Arindam Ghosh at IISc Bangalore, that it's like, more is different. Silver is not a superconductor, never. Gold is not a superconductor. But make nanoparticle of silver and embed in gold, they observed a signal for unstable superconductivity above room temperature. So it was laughed upon at the beginning. They said it should be some experimental error and so on. But these friends are pursuing it vigorously for the last 3 years, and they have not given up. Out of 200 samples, they see this phenomena in 20 samples, and then next day they don't see. So what is going on is there is some transient unstable superconductivity. It's definitely there, but we have no nanoscopic control to make them reproducible. But so a lot of effort is going on. So I encourage experimentalists to look at these papers. And of course, from my selfish point of view, I have a theory supporting some of these claims. You can look at it in the archive. Okay, so let's see. May I ask the organizers about the time? How am I doing with respect to time? How much time do I have? Hello?
Sir?
Hello, do you hear me?
Yes, sir.
How much time do I have?
20 minutes, sir.
20 minutes. Okay, I'll finish in 20 minutes. Thank you.
Okay, sir. Thank
So
you.
this field is growing, lots and lots of new developments, and this is a hero, P.W. Anderson. He got Nobel Prize in 1977, and he is responsible for several Nobel Prizes. I will tell that story next tomorrow. He coined the name condensed matter physics. And as I said, I was in ICTP in Trieste, Italy, in 1983, 84. So I happened to meet Phil Anderson during a colloquium, and we had a long discussion. Then 2 years later, I ended up being in Princeton in his group. Then this revolutionary development in high TC superconductivity took place. So I joined him in the game of resonating valence bond state theory, and which essentially is very simple if you think in terms of quantum chemistry. So you all know from your example of benzene that if you take a benzene molecule, there are 6 electrons in the p orbitals, one in each carbon atom. They form singlets and they dance around, they resonate. So what we said was that this kind of singlet resonance is taking place in cuprate, and when you dope it, you create empty sites. So this resonance leads to superconductivity, which is in some sense is related to BCS theory, but in a fundamental way different from BCS theory. So it's a profound modification of BCS theory into new realms and new scales. So that was the contribution. So we even coined a name called spin-on in our paper. And now maximum value of superconducting theory can be at room temperatures. So, okay. Now, then many systems join the game. Organic molecules, stack them together, C60 molecule, K3C60, they also became superconductor. So many materials become manifestly quantum, and lots of fascinating things are happening. And the whole field of strongly correlated system, heavy fermions, transition metal oxide, manganites, and so on, is very rich. So they are all ordinary looking materials, but rich physics. For example, if you take rust, when we leave things on the outside, a piece of iron, it gets rusted. You take a piece of rust and look at it very carefully, you will find that rust is a Mott insulator. Then if you look at even more carefully, you can find what is called skyrmions, and you can find what is very fashionable in the context of spintronic devices happening in a little piece of rust or in a piece of stone. So the materials that we see around us is profound. It's inexhaustibly complex. There are many things going on. Okay. So now I will just switch gear and talk about possibility of building quantum computers in a very sketchy way. Now, using the materials that we know. So we know laws of physics are different at atomic scale. That's what I have been saying. Newton's laws give over to laws of quantum mechanics. Then a material particle behaves as a wave when the de Broglie wavelength, which is defined as h cross by mv, is larger than particle size. Then quantum tunneling takes place, linear superposition becomes valid, and what is called quantum entanglement. Now, if you take a classical computer like your cell phone or my computer, there are switches which can be on or off. So they can be coded by binary variables, which are 0 or 1. So there are logical gates which change them. So there are AND gates, NAND gates, and so on. But in a quantum system, you have this possibility. This is supposed to be a ket, alpha 1 ket and beta 0 ket. Okay. So you can form linear superposition where alpha and beta are complex numbers, and there are infinitely large number of independent. So what was 2 independent states of a switch, now it's possible to have infinite states in a quantum switch. That leads to very profound implications. A classical computer can be in 2 to the power of n states. So for example, the first switch may be on, off, and so on. Whereas a quantum computer has completed the Hilbert space dimension explodes. So the 2 to the power of n quantum states become n qubits, and the Hilbert space explodes in dimensions. I will not go into the detail, but I will just want to sketch one thing. So a classical computer like cell phone or my computer tells you what you start with an initial state and give an algorithm, and it takes you along a unique path and gives you the final solution. It could be multiplication or it could be very complicated analysis, but there is a unique path which a programmer needs to know. Whereas in a quantum computer, because we use the laws of quantum mechanics, there is a vagueness or uncertainty. So the quantum computer explores simultaneously billions of possibilities. A classical computer at a given time explores only one possibility, maybe fast, but a quantum computer simultaneously explores many paths, and they quantum interfere and give you the right solution via quantum interference. Sorry, these are all words, but every one of them is meaningful. So please have a look at the website, and you can learn many of these things very easily. By the way, I tell you a secret, particularly to our Indian students. We think quantum mechanics is complicated. Actually, classical mechanics is more complicated. Chaos is more complicated. Nonlinear dynamics is more complicated. If you look at Schrodinger equation, it's linear. There is linear superposition, and you play with matrices and so on. So, in fact, people like P.W. Anderson, apparently during his college days, was getting good marks in quantum mechanics than in classical mechanics. So there is a simplicity in quantum mechanics, even though it has its own profound and counterintuitive character. So I encourage you to look at quantum mechanics. So this is what quantum computer essentially does. It does parallel processing by its very quantum nature, and solves very profound problems in short time. Like it is said that if you have a quantum computer with few thousand qubits, the power of it in terms of memory and the ability to do fast computation will overwhelm all the computers put together in the world now. So people worry about quantum supremacy. There is a fight between Google and Apple and IBM and so on. Incidentally, IBM has a quantum computer setup where anybody can register and use the quantum computer online and solve some problems and even write papers. I think you should talk to Shankar Narayanan at Trichy about it, or other colleagues who are working on quantum information in India. Okay, good. So the quantum materials I talked about provides you opportunity to have these quantum switches or qubits. So quantum dots, excitons, electron spins, nuclear spins, carbon nanotubes. I had some old idea about in terms of electron spins and carbon nanotubes, and topological excitations, spin-ons, holon, Majorana fermions, Cooper pair box spin. So there is a variety of condensed matter systems which is waiting to be explored and already explored. For example, a very popular one is something called Majorana fermion, which is a fascinating system. I have no time to go into it, but I'll encourage those of you who have time, just to do a Google search on Majorana fermion. Very dear models which exhibits Majorana fermion in a way that you will understand it. Just elementary quantum mechanics is sufficient to understand existence of Majorana fermion. So this is something that's already going on. Okay, now let me see. Now I talked about inanimate material. Now we are all living beings, and we understand life processes to some extent, thanks to people like lots of pioneers, people like Watson and Crick and Pauling. They said the life depends on these proteins. G.N. Ramachandran, of course, triple helix. So they have helical structures. There is hydrogen bond. There are covalent bonds. All kinds of things are there. And the regulations and biology. If you look at the biology textbook, it's fascinating. So many phenomenology happening simultaneously, even in a single cell bacteria. We don't understand bacteria yet, the life of a bacteria yet. There are still so many Nobel Prizes hiding, there to be explored. So as I said, a single life, namely a bacteria, is still not understood. There are many, many fascinating things. So when it comes to materials in biology, sky is the limit. You can talk about very simple biological material. People call it a soft condensed matter. For example, just the membrane. See, we know that every cell is made up of a membrane, and there are things inside, microtubules, cytoplasm, and all kinds of things, proteins, DNA. Then a lot of people my colleague, for example, Gautam Menon and colleagues at MathScience worry about the dynamics of proteins. That itself is fascinating. Nobel Prize winning works are yet to be done. So biological materials, sky is the limit. Now, what is remarkable is, in fact, in one of my articles, I wrote that the solid state physics we have done in the last 1 century is like a warm-up exercise to climb Mount Everest. Because when you touch biology, it is so profound and complex. You occasionally see glimpses of condensed matter phenomena in biology and much more. And even more exciting is people like Niels Bohr speculated, also Schrodinger speculated, that quantum mechanics should play some key role in biology, which we do not know. It is true that hydrogen bonding is quantum mechanical, or chemical bonding is quantum mechanical, but these individuals and recently many others are saying there is more profound role at a different level. So that's a whole field of quantum biology. Just to give you an example, we know that birds fly across big oceans and go from one continent to another continent. Who guides them to go in the right direction? People say magnetic field. How do they test magnetic field? How do they sense magnetic field? Because we don't have a squid in the brain. Because the magnetic field is just 1 Gauss, roughly. In terms of temperature or energy scale, it's 1 Kelvin. Whereas birds are at room temperature. So how do they sense it? They have found out that there are beautiful chemical reactions in which intermediate states are spin triplet and spin singlet. And there is an energy splitting between the two, which is sensed by some quantum phenomena involving nuclear spins and decoherence and so on, non-decoherence. So quantum biology is getting matured and surprises are happening. Similarly, in the, okay, I will come to it. For example, you look at this picture, you will wonder what it is. If you look at plant, this is called photosynthetic apparatus. There are protein molecules which support this kind of chromophore molecules which are organized in beautiful discs like this. And light gets absorbed by these molecules and creates what is called an exciton, an excited state. This exciton happily hops around and lives for a while. And then at the end, it jumps to the center called reaction center, and it initiates a chemical reaction, and there is a cascade of events. So people discovered this structure not long back, about 20 years ago. So that was a Nobel Prize winning work. So what is remarkable is that at room temperature, these excitons behave like a quantum particle. There are good evidences. So people never suspected it. So people are saying that linear superposition quantum entanglement that I briefly alluded to is at work. So how is it modifying biochemical phenomena? We do not know. So these are very wide open field. Of course, one should be very careful. There are people who do a lot of speculation, but there are people who do experiments and then develop theory along with. So this is a good field for young people, because this is also going to change the future of our energy crisis, because the standard solar power station involving silicon and so on will be replaced by organic based solar panels. So there are exciting things going on where there is basic quantum mechanics and applications and many things. And so I also want to tell that a new breed of physicists with condensed matter and sometimes physics background are emerging and making new inroads in biology in both experimental and theoretical fronts, and are making remarkable process, even to the satisfaction of conservative biology, because biologists are by very nature conservative. They don't believe immediately what the physicists say, but now they have started believing. Earlier examples are showed in your research. Now there are many, many happening. So in the next 5 minutes or so, I will wind up. And the picture that I show is DNA in our chromosome. Then DNA is wound on something called chromatin, and then they are in turn wound like this. They are in turn wound. So there is a hierarchy of organization. And simple physics that we have learned in solid state physics and some aggregation phenomena can explain this organization. Very profound things that go on in biology. Similarly, there are muscular system, skeletal system, nervous system, endocrines. That are so fascinating phenomena that we can use from our physics, including fascinating issues in vision. And let me, before I conclude, I'll just make a statement. It was discovered by people like Sir C.V. Raman and also earlier, I forget the name, that our eye is capable of detecting single photon. Please think about it and read it. See, because a lot of photons come and fall on, but if you are sitting in a dark, occasionally some light photon falls in your eye, and Raman realized that it's a single photon event. So he speculated and so on. Now it's a very active field. How single photons can be discovered by our eyes and what are the consequences and so on. So of course, brain is the ultimate thing. We may understand the universe, but till we understand our brain and what is consciousness and so on, we are far from understanding what is going on. So they are all profound things. So let me spend the last few minutes, because I may not have time tomorrow, some practical tips for studying physics and going into the depths of physics for young students. Think a lot about experimental results and phenomenology. That will give you how to go about. Read the archive regularly, about half an hour. So if you note down this website, this is what you will see, archive. See, it turns out people these days, when they write a paper, like people like Professor Lakshmanan or any of our colleagues, they first put it in the archive. They post it in the archive before they send it to the journal. For example, in the year 2020, the number of submission per year is 1 lakh, nearly 2 lakh papers. Almost all the papers that are published later are put in the archive. So they are available freely for you. You can search for them according to the topic: condensed matter physics, superconductivity, materials in strongly correlated system, or quantum physics. So I encourage young students to spend half an hour every day reading archive, because you will discover. Then the last thing is, you have NPTEL courses and outstanding resources at the internet. Above everything, regular group discussion is a key to success, because you students are not alone. You have your peers, your seniors, juniors, and friends. So let me finish with an example of Einstein. And I was fortunate enough to be at IAC, and Professor S.K. Rangarajan, late S.K. Rangarajan, inspired us by telling this example of Einstein and making us follow it to some extent. So what Einstein did was, when he joined his 5-year college course in ETH in Zurich, He formed a group from day number 1. They didn't watch the television in the evening. They didn't watch cell phone. They were discussing science, religion, philosophy for about 2 to 3 hours every day. At the end, this was about a group of 10 people. The end result was profound because during this process, they came across a book by Henry Poincaré, a famous mathematician, called Science and Hypothesis. This book profoundly impressed us and kept us breathless for weeks on end. And this book by a master who was an universalist, he was more than a mathematician, he said, he asked the question, why did ultraviolet light eject electron from a metal surface? What caused the endless zigzagging of pollen particles in liquid? How do you measure Earth's movement through universal ether? You will all recognize these 3 questions Einstein learned through the group discussion as a integrated BSc or MSc student. And then he gave answers to them and became what he was. So first is photoelectric effect, second is Brownian motion, third is special theory of relativity. So I always tell students to form group discussion because again, there is emergence because you are alone, you have some strength. When 2 of you join together, there's a new strength. When 3 of you, there's even more strength and fantastic things happen. So I think that's, yeah. With that, let me conclude my talk today. I'll be happy to answer questions if you have. Thank you.
Thank you,
I'm
sir.
sorry if I was fast and I was just rambling, but fortunately you will have the lecture available in YouTube. So please look at it carefully, slowly, and the hints that I gave you will be very valuable for you. Thank you.
Thank you, sir. The session is open for discussion. Participants are requested to post your questions in the chat box.
Chat box. Let me see. Where is my chat box? Yeah. Oh, chat box. Yeah. Well, I'm seeing the many questions. Okay. So I see lots of thanks. Thanks for your thanks. Okay. Thank you. Thank you. Thank you. Thank you. So which is a good book to read about the quantum mechanics of graphene, sir? Very good. So this is the one of the questions. So there are beautiful review articles, for example, reviews of modern physics. And also there is an article by me in one of the books edited by Professor Rao and Ajay Sood. It's called Quantum Complexity in Graphene and Quantum Fields in Graphene. There are 2 articles. You can do a Google search and freely download articles. So there are outstanding review articles available about graphene. And so that's more than a textbook. It gives you all the details. And also I can tell you, there are good NPTEL courses on 2-dimensional materials. You can listen to them. And again, thanks. Okay, so there was only one question. There are 3 new messages. Could you please say something about how you got into PhD in IASC from MKU? Oh, that's thanks for this question. See, okay, I studied MSc in Madurai American College. We had an outstanding teacher. It's a good time to pay homage to my teacher who is no more, Professor Rees. He was a phenomena. He was a scientist at Bell Telephone Laboratories. He decided to come to India for 1 year to teach. And then he fell in love with Madurai and he stayed for 35 years. So he was my teacher, very inspiring teacher, very selfless teacher. So one day he asked me, I was going to the college in the evening, asked me, what are your plans? I had no plans actually at that time because I'm from a poor family. I didn't know what to do. So I told him, sir, I want to become a demonstrator. He said, suppose you don't get it, what will you do? I scratched my head and said, I may become a research scholar in Madurai University because they pay 200 rupees scholarship. Suppose you don't get that, what will you do? I didn't know what to say. He said, do you know about Indian Sub-Science at Bangalore? I told him, no, sir, what it is. So he told me, do you read English paper? I said, no, sir. So please buy English paper for the next 2 months and read the papers. There will be advertisement for PhD program in Indian Sub-Science. Please apply for that. So my introduction to IASC is from Professor Richard P. Rees, my teacher at the American College. And that changed my career. So I have to thank him and remember him now. So I suppose that answers your question. Please repeat the article name again. The article, see, if you do a Google search, Bhaskaran graphene, the name of the articles will come. Okay. Okay. Is Meissner effect and zero resistance both are mandatory to define superconductivity, or any of them is? That's a very good question. It so happens for all the phenomena that we know that is associated with superconductivity, including flux quantization and Josephson effect, the two come together. So in principle, it's possible to imagine a zero resistance state without Meissner effect, but such states does not seem to exist in nature. You can make arbitrarily low resistance and without Meissner effect, but then it's not useful. It's not the superconductor that I love. Okay. Sir, what is the best way to conceptualize a tough concept or to remember a topic like tensor and visualize them mentally? A very hard question. See, I was reading a book, I forget the name. See, there are various ways of understanding. There are some people who take a book and read it line by line and systematically try to understand. And there are people who are like playboys. You take a book, browse through it, go to the end of the chapter, come big, look at the picture, this and that. Apparently, that's also a very good way of learning because it familiarizes you and at some deep level, you get some understanding. So there is no unique way, but the most important thing is to keep thinking about it. If you have a tough concept, as they say, sleep over it. Because according to a theory of creativity, we become very active during our sleep. Our subconscious mind works extremely well and you wake up with new discoveries. So please sleep over difficult concepts. Don't give up. Think about it. Think of similarities. Like things like, and also, of course, when it comes to mathematics, there is nothing like working out the problems. Work out simple problems. This is something that we never do. I never did during my studies, never did homework and so on. So nothing like doing homework and solving simple problems. That can take you a long, long way up. So thinking mentally and also working out problems are both important. Okay.
Thank you, sir.
Yeah, thank you very much. And I hope, so as Professor Lakshmanan said that, you can send me an email or you can, I'm not there to talk to you. So you can send me an email and we can discuss if you have serious questions.
Thank you, sir.
Yeah. So thanks once again. So we'll meet tomorrow. I will stop sharing the screen.
Okay, sir.
Have a good day. I will say good night.
Thank you, sir.
Thank you, sir. Thank you.
It's time for lunch break and we'll join the next session at 2 p.m. Thank you.
சார் வணக்கம்.
வணக்கம் ஜெகநாதன். ஜாயின் பண்ணிட்டீங்களா? அப்பதான் ஜாயின் பண்ணிங்களா?
இப்பதான் வந்தேங்க சார்.
ஓகே. So Dr. Ravichandran is here.
Hello, good afternoon, sir.
Sir, good evening, sir.
Hello.
Sir, we are ready to start the program, sir.
Okay, thanks.
Hello.
Good afternoon, everyone. I invite Ms. A. Shanti Devi, Assistant Professor, to introduce our speaker.
Hello. Good afternoon, all of you. Dr. Jagannathan is a distinguished professor at Bharathasan University, Trichy. He has 23 years of research experience. His research interest has spanned many areas over the years, including nanotechnology, nanowires, photovoltaic cells, drug deliveries, and SCRS detection of biomolecules, on which he has published more than 120 papers in reputed international journals. He has participated many national and international conferences, and also he conducted many conferences. He acted as a coordinator for Center for Nanoscience and Nanotechnology, and also he had as a coordinator for RUSA Screen. So far, he guided 6 PhD scholars, and 7 scholars are doing their PhD under his guidance. His cumulative impact factor is 397 and H index is 24, and his citation is 2002. He has successfully completed 7 major projects, and now he has 3 major projects, major ongoing projects. He has received many state awards, and also he has visited many countries. He is an active member of professional bodies, advisory boards, and academic bodies such as Board of Studies, etc. He is a professor with excellent academic record and proven leadership and administrative capabilities. With his small introduction, I would like to invite Dr. Jagannathan sir to deliver a talk. Sir, please.
Thank you, madam. So at this juncture, I would like to extend my sincere thanks to sincere thanks to Professor Lakshmanan sir and Dr. Ravichandran for having given me an opportunity to have a very brief interaction with young good students. So the title of my talk is on the physics of semiconductor nano structure. So in the next 1 hour, so I'm going to talk about the significance of the semiconductors. So the outline of my presentation will be I try to give the perspective of the semiconductors and its significance, and how these semiconductors playing a significant role in the device manufacturing. Well, so I extend a very warm and prosperous happy new year to every one of you in this difficult time. Well, can you see my slides?
Yes, sir.
Okay.
Yes, sir.
Okay, thank you. Yeah, so in the past 6 months, you would have seen in the newspaper, it's a global semiconductor manufacturers are facing a critical challenge in meeting the global demand for the chip supply. So that has relatively impacted on the car production in the entire world. And there was a news sometimes back, the car production was cut about 50% due to semiconductor chip shortage. As a result of this semiconductor chip shortage, the prices, so all the electronic gadgets, so wherever you can find the semiconductor chip, so the prices are rose up to 25 to 50% since last year. So the chip shortage is making it hard for the manufacturer to find the supplies they need to make the computer powered goods. The computer prices, the laptops, desktop, everything, they have gone, the prices of their systems have gone up to 25 to 50%. So for instance, so the automakers are also facing a critical problem. So they have already cut that production. It's about 25 to 50%. If you take any, it's automobiles, or particularly the car, the recent generation of car contains or requires, it's about thousands of chip in the car manufacturing process. So in particular, the electronic vehicle, so where the car operated by the batteries, requires more and more semiconductor chip to control the battery management and other important operation of the system. Well, so due to the pandemic, the most of the semiconductor companies were shut for the period of 6 months and more. As a result, their production was almost stopped. So this resulted in a demand in the chips. So as once the pandemic, so partly we revoked the entire globe for the operation. So as far as the semiconductor fab or so-called foundries are concerned, there are hundreds of companies are there around the world. So among them, the Taiwan Semiconductor Manufacturing Company is the world leader. So they met, it's about 50% of the global demand. So besides the other companies like Intel, AMD, Qualcomm, NVIDIA, there are Texas Instruments, there are several companies are there, but still among them, Taiwan Semiconductor Manufacturing Company is a contract manufacturing company, is the world leader. So they are meeting, it's about 50% of the global demand. As the company was shut for a brief period, so the demand has risen, and we are facing the shortage of chip. So the problem is a global issue, not only in India, but of course India does not have any semiconductor fab as of now. To meet the demand for the Indian car manufacturers, so the Tata Motors or the Tata Group had a plan to set up, it's about $300 billion semiconductor foundries in India, so on a wartime basis. So this was proposed a couple of months back to meet the demand, but now this announcement is likely to face some headwinds due to the absence of raw materials in our own country, and also the scarce availability of outside too. So India does not have any auxiliary industries to set up the semiconductor fab in India. So this is a major problem. So globally since the pandemic. So in the past, so India had failed to attract any chip makers. So hardly speaking, so India does not have any fab. In order to set up one semiconductor fab, so one has to invest at least $10 billion. It's about 1 lakh crore investment need to be done to have one excellent semiconductor fab in India. It's very huge investment. But however, in recent times, in the past couple of weeks, so our minister, Ashwin Vaishnav, as a telecom and IT minister, had unveiled a new semiconductor policy for in India. So India has a plan to invest, it's about a $10 billion as an incentive for the semiconductor manufacturers. So they are expecting to have 100 semiconductor fab in India, but I think it's very, very challenging, but unless our policy and also as we are able to provide the auxiliary support to such good industries. So though we have lost several semiconductor manufacturers in India. So hope this time India would be successful to have at least 1 or 2 fab in India. So the countries who have had invested large amount on the semiconductors. So for example, if you take Japan, Taiwan, South Korea, including China, Singapore, but Malaysia, they are extremely rich. So due to the huge investment in the semiconductor particular industries, this is one of the reason why they are rich. Okay. So with this very brief news media report in recent times, so now you can understand that the power of semiconductors, the need of semiconductor chip. So at this juncture, well, so we know well about the materials. So based on the resistivity of a material, so we distinguish them as the conductor, semiconductor, and insulator. The resistivity of a material whose faults lies between conductor and insulators are classified as the semiconductors. The resistivity whose range lies between 10 power -3 to somehow 10 power 7 ohm meter, so are the semiconductors. So as you look into the periodic table, group 4 element, so you have the elemental semiconductors such as silicon and germanium. So these are all very interesting and simple material. So this has revolutionized the entire semiconductor industries globally, in particularly silicon, because silicon has become the workhorse of the integrated chip. Even now, it's about 90% of the entire chip are being made only on the silicon based materials. Well, so obviously, from the physics point of view, so when you try to measure the resistivity at various temperature, from absolute temperature to room temperature, so for conductor, how the resistivity changes. So with the increase of temperature from absolute temperature, the resistivity linearly increases. But at the same time, if you look at the semiconductor, so with the increase of temperature from 0 Kelvin, the resistivity drops down, right? So the resistivity versus temperature curve for any typical semiconductor, you can notice that the decrease of resistivity with the increase of temperature. So this just opposite to the nature of a conductor, but the drop of the resistivity with the high temperature so cannot be explained by the free electron theory of metals. So we have to look into another theory, so where the band theory helps us to understand that, so how the semiconductor behaves, or how the semiconductor really gets the bands, right? So simply you take a 2 hydrogen atom, because hydrogen atom is the very simplest case. So where you have only one electron, so the electrons is residing in the oneness orbits. So when the two such hydrogen atoms are very far, nothing happens. So when you brought them very closer and closer, the oneness electron of each hydrogen atom start to overlap, and then interaction taking place. So as per the Pauli's exclusion principle, no two electrons can occupy the same states. So thus the overlapping causes to create the quantum energy states. It's a discretely this electron occupying different states. Well, so when you have more such either it's a 1s or 2s, 3s electrons, when more and more 3s electrons are coming together by forming a solid, I mean it's an atomic solid, right? So as due to the Pauli's exclusion principle, so each overlapping causes new discrete energy states. Those energy states are closely spaced with very small energy. So these states never overlap, but however these states are very discrete despite being closely spaced. So what happens, as I already told you that, so the electrons are having it's a wave function. When these wave functions are started to overlap, there are two different scenarios could exist, right? So one is that, so when the electrons and the nucleus of such orbits are interacted, so it goes to either it's a bonding orbital or anti-bonding orbitals. So in the case of symmetric, I mean it's a bonding orbitals, the summing up of the two wave function, it allows the electron to occupy very lowest ground state. So this is said to be very stable state of the quantum state of an electron. On the other hand, the antibonding orbitals are the high energy orbitals. So these are the electrons are available for the conductions. So when you have 3s and 3p orbits are getting overlap more and more, such orbits have got to overlap. So you can notice that at the equilibrium spacing, there is a gap exists between two continuous discrete state. So due to the symmetric cases or the bonding orbitals, so all the electrons are occupied in the valence band are considered to be a very stable, whereas the electrons occupy in the conduction band as a result of the anti-symmetric. So between these two bands, the valence, these two are called as the valence band and conduction band. So between these two bands at the equilibrium spacing, you can notice that a small energy gap. When you draw a vertical line, you can see that a small gap is existing. So this gap is primarily responsible for the conduction in the semiconductors. So here you can very clearly see that. So between the valence band, filled valence band and empty conduction band, here you have it's a small energy gap, right? So the formation of this energy gap, so in the overlapping of the different orbits is primarily responsible for the semiconducting behavior in some materials. Well, so now you have got that how the semiconductor gets the bands, right? And how it has the energy bands. So the materials, particularly like the silicon, germanium, but of course, in the periodic table, by combining two different elements, you can form the varieties of semiconductors. For instance, when group 3 elements are combined with the group 5, you can have the varieties of group 3-5 semiconductors. Either it's a gallium phosphide, gallium arsenide, indium phosphide, indium arsenide, and also you can alloy them, right, to have the alloy semiconductors. So numerous materials can be made out of interaction of the various metals in the periodic table. So every elements or every compound have their unique characteristics of the band gap. So for example, when you take silicon band gap is 1.1 electron per volt. Germanium has got around 0.7 electron volt, right? So now you can have the band diagram for the semiconductors. The valence band is completely filled, and then conduction band of the absolute temperature, right? It's a totally unoccupied. But thermal energy at room temperature is sufficient to excite some electron from the valence band to the conduction band. But those are the electrons available for the conduction in the semiconductors. But at the same time, as you have seen, the resistivity versus temperature curve at absolute temperature, the resistivity becomes very high as a result that all the electrons, so in the Fermi energy as well as in the conduction band, all being freezed within the valence band, no electrons are available for the conduction. Hence, the semiconductors would behave like a insulator at absolute temperature. But whereas the situation entirely different. So when the temperature rises to a room temperature, right? So you might be having some electrons in the conduction band. So these electron makes the material are very interesting, and also one can foresee the semiconducting out of semiconducting devices, so where you can control the flow of charges very precisely. But classically there is no thumb rule to define. So what should be the band gap range for the classification of semiconductors, right? So but we used to say that, right? So the band gaps, the gap between valence and conduction, so up to 3 electron volt, so are behave like a semiconductors, right? So but strictly this is not the it's not a thumb rule as I told you that. But now there are different materials are invented. So for example, so you have the zinc oxide. Most of you might know about the zinc oxide. It's a wide band gap oxide semiconductor whose band gap is 3.3 electron volt, but still it's a very good semiconducting it exhibits a very good semiconducting behavior. Now we have the families of wide bandgap semiconductors such as gallium arsenide, aluminum nitride, so whose band gaps are extremely very high. For example, aluminum nitride band gap is 6.2 electron volt, but still due to the defects and then point defects in the material, so it behaves like a semiconductors. On the other hand, so thermally you may not be able to excite the electron from the valence band to the conduction band are called to be the insulators. For example, you take a diamond, plastics, rubber, and so on. These are all insulating materials. So absolutely, it's not possible to excite the electrons from the ground state to the excited state. So with the thermal energy. So those are the insulators. So here our interest is on the semiconductors. As I start with the semiconductors promises. So at absolute temperature, you know, the semiconductor behaves like a insulators. So absolutely, it's not possible to excite the electrons or carriers from the ground state to the higher state because it requires a very high field strength. It's about 1000 volt per meter is required to move an electron from the valence band to the conduction band. But the simplest or easiest route to excite the charges or to place the carriers in the conduction band, just you can take the thermal excitation route, simply heat the material or leave it in the room temperature. So this thermal energy, it's about 25 milli electron volt, I think. So it's sufficient to kick out an electron from the valence band to the conduction band. So when you use the Fermi-Dirac distribution to find out that at room temperature, so how the distribution of electron or the charges from valence band to conduction band are taking place. So with this simple probability distribution equations, so you can understand it. Whereas as you take the intrinsic semiconductors, intrinsic means so it's undoped semiconductors. So when such undoped semiconductors are placed at absolute temperature, right? So the point at which it occupies the highest energy position, or the electrons occupies the highest energy position at absolute temperature, is described to be the Fermi level. That corresponding energy is the Fermi energy. So in intrinsic semiconductors, the Fermi level lies exactly at the center of the band gap, right? So, but actually this Fermi position of the Fermi level is tunable. So with respect to the type of carriers and then total density of the carrier concentrations. Well, so at above absolute temperature, right? So in intrinsic semiconductors, the Fermi level, if it lies exactly at the center, which means that the number of donors and the number of acceptors are equal. So the Fermi level is positioned at Eg by 2 level. So when you substitute this into the equation, you will get that the number of electrons promoted across the gap Ne is equal to the some constants that corresponds to again the number of electrons available in the top band. It's exponential minus Eg by 2kT. It's a Boltzmann, and then that the required at the given temperature. So this equation gives us a good quantitative description of the total number of carriers in the conduction band at absolute, I mean at greater than absolute temperature. Well, so when the semiconductors are not doped, right? Undoped semiconductors, so it does not have any great applications, right? The semiconductors get intriguing properties only when it has been appropriately doped with the impurities, because the doping in semiconductor allows you to control over the type of carriers and also the carrier density. So the total number of electrons or holes per centimeter cube. So these are the essential factors where you can tune the properties of the semiconductors, so which has the enormous application in the devices. Well, though as far as when you take a silicon, so silicon is a very simplest material. So silicon is a group 4 element having the valency of 4. So when silicon has been doped with the group 5 element, such as phosphorus, arsenic, antimony, and so on. So the doping of group 5 elements so provides an extra unbound electron. So this electron virtually becomes free, right? So you are having the excess carrier or excess electron as a result of doping. So this produces an energy level very near to the conduction band, right? So this called as either it's a donor level, or you can say the position of a Fermi level. So as a result of group 5 doping in silicon, so causes the material as a N type. So where the electrons are the majority carrier. On the other hand, if you have doped, if the semiconductor has been doped with the group 5 elements such as aluminum, gallium, and indium, so you are having an extra electron for bonding, which means that so the bonding leaves a hole in the silicon. So you are having the negative positively charged hole or the conduction. So thus you are having the energy level very near to the valence band. So where the holes are the majority carrier in the p type. So thus with the appropriate doping of the different valency material in semiconductors, particularly silicon, you can change the type of carrier, and also the carrier concentration can be manipulated with the appropriate amount of doping, right? So in N type, as I told you, that there is a donor level is formed very close to the conduction band, right? This is the Fermi position of a Fermi level. So as we have more carriers, electrons as the carriers, the electrons tend to occupy the highest energy position very close to the conduction band, even at absolute temperature, right? So because the ionization energy of the donor level is the fraction of the band gap energy. So here, as I told you, that the electrons in the conduction band are the majority carriers. So the number of holes here in this material is very, very small. So in N type semiconductors. Well, so on the other hand, so when you have a P type where the holes are the majority carriers, the Fermi levels are always aligned very close to the valence band, right? So even at absolute temperature, the holes are bound to the dopant atom. As when the temperature increases, obviously the holes gain thermal energy and break away from the dopant atom. So then these holes are available for the conductions. So here the holes are the majority carrier in P-type semiconductors. These are all, it's a known fact we have studied in the lower classes, right? So now we may be able to plot a band diagram for semiconductors and can be compared with the metals as well as insulators. So as you know, metals, whether you take it's the monovalent, divalent, or pentavalent. So there you can see some aspect. You can see the overlapping of the Fermi, overlapping of the conduction band within the valence band, which means that the valence conduction band has been enriched with the more number of carriers. So these free carriers making that the metals are highly conductors. Whereas on the semiconductors, so thus we understand from the band theory of semiconductors, a small energy gap exists. So this the electrons can be excited with the sufficient thermal energy from valence band to the conduction band. As you have the limited amount of carriers in the conduction band, you may able to control or manipulate the operation of your devices. But whereas in the insulators, absolutely it's not possible to excite by means of thermal energy. So thus they are the insulators. So having a semiconductors, so when the semiconductors have been contacted with the metal, so it gains the significant interest, right? So the semiconductors are useful only when you make contact with the metal for the transport of the charge carriers. The contact can be made either it's on N type or it's a P type material, and you have to appropriately choose a metal having a work function to behave it as either it's a Schottky contact or it's a ohmic contact. So obviously when you look into the transistor, you have the drain, source, and then gate. So these contacts have been made with only the appropriate metal contacts having the work function. Well, so let us take some of the simplest case. So when you are trying to make the Schottky contact on a semiconductor, so first you have to look into that in the case of ideal conditions of metal semiconductor junction, right? So the metal work function should be larger than the work function of a semiconductors, right? So the metals as well as semiconductors are characterized with that band structure, or it's a band theory model. So where you have the vacuum level, it's very interesting. So both the metal and semiconductors have the vacuum level. So where the energy of a free stationary electron, so which is available outside of the any material under a perfect vacuum. So the position from vacuum level to the Fermi level, so irrespective of whether it's a metal or semiconductor, does not matter. So the position from vacuum level to the Fermi level is the work function of a material. So the Einstein photoelectric effect gives a very good formulation about the work function, right? So the work function is nothing but the minimum amount of energy required to liberate an electron from the solid to point in the vacuum immediately outside the solid surface, right? So here, before making the metal contact with the semiconductor, so this has the intrinsic behavior, intrinsic position of work function, as well as the it's a electron affinity of the metal as well as semiconductors. So the metal having the work function greater than the semiconductor, or it's a contactor. So the high energy electron in the silicon try to move into the metal surfaces through the metal interfaces at the interface between metal and then semiconductors. So obviously at the interface, there is a built-in potential is formed as the barrier height electrons need to overcome. As you want to move an electron from either metal to semiconductor or semiconductor to metal, so here as the result of the upward bending of semiconductor, we adjust to the metal to see some barrier, right? So on either directions, the flow of electron faces a barrier, so that no electron can move once the bands are formed. But at the same time, in a moment when you contact these two materials, right? So the thumb rule is that, so the Fermi level of metal and then semiconductor should match. So whatever the material, you could interface it, right? So until then it could matches, some of the high energy electron and holes appropriately will move on the respective side until a thermal equilibrium is established in the given contact, right? So at the given thermal equilibrium, so the electrons and holes pass through the opposite directions at the interface, leaving no it's a carriers at the interface, thus forming a depletion region. So all the charge carriers are get depleted at the interface, and since there is a barrier, right? So there is a space charge region is created at the interface, right? So at the thermal equilibrium, no electron flows on the either side. But when you apply a forward bias to the metal semiconductor junction, with respect to the polarity of the potential, the work function of metal as well as semiconductor shifts accordingly. So here you can see that in the given condition, the forward bias, a positive potential to the metal, and then the semiconductor is grounded. So the metal work function is a position below to the, it's a Fermi level of the semiconductor, right? So that in the forward bias, right? So with the increase of the potential, so more and more electron diffuse, or it's a pass through the barrier, but of course the barriers are enriched with the more electrons. Thus allows the electron to get transported through that. The strength of the current passes through the interface, so will increase. So with the increase of the applied bias in the forward directions. But at the same time, simply if you reverse the polarity, so what happens that there is a change in the Fermi level position. The semiconductor Fermi level position is positioned just it's a below bottom of the Fermi level of the metal, right? So in the reverse bias, it sees a very huge barrier, because the depletion bit, the space charge region is grown very thick enough, right, under the reverse conditions, right? Even when you increase the strength of the potential in the reverse directions, So it does not allow the current to pass through that. Only a leakage current, a very weak current might to pass through that until a certain voltages, right? So in this graph, you can see that the IV characteristics of the Schottky junction. So where you can see that in the forward bias, there is a huge current is flows so with respect to voltage, whereas in the reverse bias, only a weak current or leakage current. So this phenomena of the current flow both in the forward as well as in the reverse direction is governed by the Shockley equations, right? So as resulted from the barrier height, and then it's a thermal energy. So now you can say that the Schottky barrier diode or the Schottky contacts are the rectifying contact. This allows the current to flow only in one direction, or that is the forward direction, and a very small little current flows in the reverse directions. Well, so then when you move to ohmic contact, right? So in the case of ohmic contact, you have to look for a metal. So having the work function smaller than the semiconductor, right? So in this circumstance, so when the metals are contacted with the semiconductor, so semiconductor sees a downward band bending to the metal band edges, right? To match the Fermi level of metal and then semiconductor, right? This is the scenario for the after contact, right? So here, so as you have the downward band bending, right? So there is no space charge region or the depletion layer will form at the interface, right? So this ohmic contact allows the current to flow in either directions, right? So when you measure the IV characteristics of the ohmic contact, so you have to look the metals are having a smaller work function, at the same time having a very small contact resistance. If these conditions are satisfied, so you can have a very linear IV characteristics, so where the current flows both the forward as well as in the reverse directions, right? So whereas in the Schottky diode, so only a small current flows in the reverse directions, very huge current in the forward directions. So this is a major difference between the ohmic contact and Schottky contact. So these ohmic and Schottky are very essential, are the fundamental to any semiconductor devices. But of course, so these ohmic and Schottky contacts with the various metal can be established both on the N-type as well as the P-type semiconductors. So, but the situation changes. You have to appropriately look into the metals work function with respect to semiconductor to satisfy either it's a rectifying contact or ohmic contact. This is a more fundamental and then essential one to achieve either it's a ohmic or Schottky contact on either it's a P-type or N-type semiconductors, right? So having understood the properties of a semiconductors, so prior to 1947, so a team led by William Shockley of two of his colleagues with the John Bardeen, so where Professor Bhaskaran sir was speaking this morning, where John Bardeen, where he met him at the IISc. So he had received 2 Nobel Prize in physics for the co-discovery of BCS theory along with the transistor, and then it's a Walter Brattain, right? So these 3 eminent personalities invented the transistor in 1947 at Bell Labs in Illusion Technologies using a germanium single crystals. On a germanium single crystal, they fabricated 3 leads with the gold layer with the gold wire. So obviously 2 are called as the emitter, collector, and the other one is the base. So when the potential was applied between the 2 terminals, so base and the collector, they found that the signal was amplified and also it's modulated between the other 2 terminals. So where the functionality of this semiconductor at the time was very similar to the vacuum tubes. So you might be wondering that the vacuum tubes were the only active device so during that period. So then they decided to replace the vacuum tubes with the semiconductors, but the problem was the size. So at the time, 1947, the transistor size was very big. Then they decided to go for the downsizing of the transistor or to reduce the size of the transistor. So thus the miniaturization of the devices have born in 1947 or 1950 itself. So for the discovery or the invention of a transistor in 1947 using the unusual property of a semiconductor, so not only propelled to award a Nobel Prize in physics in 1956, but more this invention has importantly accelerated everyone in the world as through the information age. So now we have been talking about the artificial intelligence, machine learning, right? And then it's a genome, sequences. In every parts of the advancement, the semiconductor, the invention of a transistor, so plays a significant role. Well, so without the transistors, in case that if the transistor was not invented, so I'm not sure that whether really we would have reached this technological advancement, right? So obviously, needless, I would say that the transistor was the first device for the development of information age. So this tiny invention has changed the many aspects of the human modern life, which drives the current socioeconomic lifestyle. So the transistor was the first tool in the several technological development around the globe. So really, what is there in the transistor, right? You know, the transistor is a very small device. As you take the field effect transistor, right, this has a 3 terminal, so which has the source, drain. These source and drain were made out of the ohmic contact. So where the gate electrode, right, where it's a short key, it's contacted onto a semiconductor with interfacing a very small dielectric layer. So when a metal and semiconductor are separated by a very thin dielectric layer, the capacitance is formed. The charge accumulation is taking place at the interface, right? So with the appropriate gate voltage, you can allow either the charges to build up or the charges to get depleted. So with respect to this charge accumulation and depletion, so the conductivity in this region changes, right? So when more charges are get accumulated, when you have more carriers here, this facilitates the flow of charge from source to the drain. So you are having a very huge drain current. At the same time, simply if you reverse the polarity, the situation becomes vice versa, so that no charge transport can occur. So obviously, so the on and off operation in the transistor can be performed very quickly. So the gate holds the key for the control of any devices, right? So obviously, Intel Titanium processor, this is a quite old processor of 9500 model, so has about 3 billion transistor in a single die. So the die is about, it's a thumb-sized processor. It's a central processing unit being housed in your computer, right? So that has about 3 billion transistor. All those, the tiny transistors are well integrated, right? And then it's connected to perform a simple binary operation, voltage high and then voltage low, because that is the need in the central processing unit for the operation of any devices. So the potential greater than 0 at the gate voltage, right, as all the carriers are depleted, because so these devices are made on a p-type silicon, so where the holes are the majority but the carriers. So when all the electrons are got depleted, the resistivity increases, the conductivity decreases, so that no charge can flow. At the same time, by reversing the polarity, by applying a less than 0 voltage, it's a negative voltage. So where you can see that the conductance between drain and source increases, there is a sea of electron flows from one terminal to the other terminal. So further, having a discrete transistor, no use at all. So the way back in 1958, so Jack Gilpy and then Robert Noyce, who are working in the two different semiconductor industries, has proposed or made a integrated circuits by connecting few transistors together, right? So thus become a silicon chip. So the integrated circuit, the silicon chip is the workhorse, as I already mentioned, that the workhorse of the entire semiconductor industries, right? So for this invention of the integrated circuit by interconnecting few transistors, so they were awarded the Nobel Prize in 2000. So along with the three more scientists who have had contributed enormously to the development of growing semiconductor heterostructures and also the development of semiconductor laser based on semi heterostructures, right? So, unfortunately, so Robert Noyce was not part of the, I mean, it's a Nobel Prize winning team. So because he was, he was expired before 2000 as per the Nobel Committee regulations. So he was not part of the Nobel Prize. Anyhow, this invention integrated the transistor as well as the integrated circuit has become very significant in every part of our life. So way back in 1965, so the Gordon Murray, along with two friends, Andrew Grew and Robert Noyce, they went on to found Intel corporations. So at the time, the Gordon Murray has proposed a classical rule, right? At how phase, right? The size of the transistor should shrink, and how the integrated, it's a chip density, right? Number of transistor in the chip should be accounted, right? So he has proposed a it's an empirical rule, so which hardly states that so for every 18 to 24 months, the number of transistor on the chip would continue to double, right? So this becomes a Moore's law later, and also this is the roadmap for all the semiconductor majors in the world, right? So this Moore's law has been kept that phase for over 50 years, but even now this continues to be a guiding principle for the entire semiconductor world. So every semiconductor majors in the world are following this Moore's law. So when you are having 1 lakh transistor this year, for example, per centimeter square, so the next year, so you have to ramp up to a 2 lakh transistor with the same area, right? So here you can see that. So these trio who founded the Intel Corporation are showcasing that 8080 microprocessor, right? So this 8080 microprocessor, contained only it's a 10,000 transistor at the time. Here you can see that this probably occupies so a quarter of any normal room, which means that the size is very, very big around that period, right? So when you try to understand the Moore's law, so Moore's law gives idea about the device downsizing as well as the chip density, right? They have started in several, centimeter of size in the year 1947. So then the device size, which means that the distance at the center of the gate to the drain or the source distance is normally considered to be the size of the transistor, right? The size has gone to the several tens of millimeter as of now. But the problem is that as you reduce the size smaller and smaller, there is a trade-off occur in the smaller devices because as they suffer from the larger leakage current and also a poor dissipation of heat, right? So that's why if you look into any processor in the computer, right? So you are having a very powerful coolant. So any heat occur from the device that has to be quickly dissipated. You have to took away all the heats, otherwise the device will fail. This is the one issue with the downsizing of the device. At the same time, as the transistor becomes very smaller and smaller, you can pack more number of transistor in the given area, right? So now we are having billions and billions of transistor in a tiny area, but all those, it's a very true, all those transistors are well integrated to perform the binary operations, as I said just before. So further, in order to illustrate that the power of the transistor, the number of transistors in the circuit, simply you assume that the transistors were the people, right? And then you look back the scenario of 1970s, so where 4004 Intel microprocessor so had only 2,300 transistors. So as we had assumed that the transistors are the people, right? So just you have that there's a music hall capacity which is designed to accommodate 2,300 people in 1970, right? But now, as the transistor has shrunk, you would be able to pack more and more transistors. But as of now, you would be able to put the entire people of China, the entire population of China or in India, because we are having more than 1.4 billion. All the people can be put into the small hall, which was originally designed to accommodate 2,300 people. Now probably you would understand that the power of transistor and then size, right? So that this is the scale of Moore's law. It's the easiest way to understand or describe Moore's law. So because of the advent in technology, and as the technology has penetrated into the rural folks of every nook and corner of the world, right? As a result, everybody in the world is afforded to, particularly in India, the technology has penetrated every corners. So every people are afford to own a mobile phone, or I would say even a smartphone, tablets, right? So laptop, every people are having these gadgets, and obviously this has become the part of our life, right? So just you look back, so how the dialed phones were invented, probably most of you would have seen, right? So then now we are having are living in the age of where we talk about iPhone, and then it's a revolutionary video platform of tube, right? Okay. So now let's see that. So what Einstein attended an invitations, right? So for the upliftment of the society, so scientists has to work together and bring and improve the I mean, it's a welfare of the people. So the same Einstein later, he said that I fear the day that the technology will surpass our human interactions. The world will have the generation of idiots. So indeed, this has become true, right? So even when you go and Google it, right? So when you check something after a few minutes, or even when you browse the next time, right? So whatever you browse it, it comes as the advertisement and being attracted by you, right? So because of the data mining, and then more and more technologies like artificial intelligence, machine languages are introduced into the software platform, right? So early days we ruled the technologies, right? We invent the technologies, but the technology started to rule us. So this is going to be really, it's very challenging, right? So when you take it on the negative side, and the worlds are having or seeing the generation of idiots, right? This word become really true. Well, so the transistor, right, has reached that the highest level due to miniaturization. So miniaturization does everything. As you make the device smaller and smaller, so you are seeing new technologies and the new quantum mechanical laws are enforced in the tiny devices, right? So obviously in the smaller dimension of devices, right, the smallest dimension, so when the interconnectors are made at the distance of the mean free path of the charge carriers, the electrons or the carriers are traveling at the high speed, or even at the Fermi velocity. So then they producing a novel quantum mechanical phenomena such as quantum interference, as well as the Coulomb blockade in the quantum dot, right? As far as the transistor is concerned, right? So the transistor size has almost shrunk to the theoretical limit. So as of now, no more reduction in the sizes are not possible, right? So in order to reduce the voltage level, the technologists are trying to reduce the thickness of the gate oxide or the dielectric layer, right? So this layer thickness has also reached around 1 nanometer or the 1.1 nanometer for 45 nanometer gate technology to node, right? So as you reduce to below this level, all the electrons will get depleted or the charges will tunnel. So no charge carriers are available for the transport from source to the drain. So definitely the Moore's law is facing a critical challenge as the dimension of the device reduces. So thus the Moore's law facing a red brick wall. So in order to keep going the convention or the space of the Moore's law, so we are looking into the low dimensional nanostructures or the low dimensional quantum structures. So where this Moore's law's phase can be met at least for next 25, 20 years. Well, so if you take any bulk material, the bulk material can be represented with the dimensions, or simply you can say it's a coordinates of x, y, and then z. So when any one of these dimensions, right, are reduced to below 100 nanometers, right, whether x, y, or z dimensions are being reduced to below 100 nanometers, right? So you are entering into a new world of materials, new regime. It's the nanostructures, right? So a structure with at least one of the dimension is less than 100 nanometers, or classically, if any one of the sizes lies between 1 and 100 nanometers, are classified as the nanostructures, right? So thus, depending upon the dimensionality reduction, you can have either it's the one-dimensional, two-dimensional, three-dimensional nano structures, right? So you can see the various examples for those low dimensional structures, right? So a structure having a sphere light are the nano particle. For example, the gold nanoparticles, buckyballs can made into this sphere light. The diameter of the size is below 100 nanometers. So you can simply call it a nanoparticles or the nano structures, right? So then as you make a thin flames or it's a any two-dimensional layers. So Professor Bhaskar spoke about the graphene and other two-dimensional material. So those two-dimensional material thicknesses are it's a below 100 nanometers, right? So obviously this has length and breadth are in considerable size. The thickness is only down to 100 nanometers. So this is the example for the two-dimensional materials or two-dimensional structures. So obviously you can make any materials into one-dimensional form. So the diameter is only below 100 nanometers, but the other and the length could be a meter or kilometer. I don't mind it. Such structures are called the one-dimensional. So by downsizing the bulk material appropriately, you can have one-dimensional, two-dimensional, three-dimensional nanostructures, right? The example for these materials are the unlimited, the limitless materials. Or example, you can cite it. Really what happens, right? You have it's a bulk material. So bulk materials are composed of n number of atoms. So where many of the atoms are reside in the bulk part of a matter. So, but when you reduce the size to 100 nanometer or it's below 100 nanometers, but more and more number of atoms are sharing on the outer world, right? So further the downsizing causes, right? So the entire atoms of the matter, right? So comes to the surface. So having either it's a few fraction of atoms or no atoms in the bulk part. So as all the electrons are available on the outer world, right? So the interaction of the electron, it changes, right? Thus it gives rise the new property. So because as you make the matter size is very small, right? The surface area has got increased while having it's a very low volume term, right? So the surface atoms have got its high energy. So all it's being combined together, the surface energy becomes very high for a nanoparticles or the smaller dimension of a matter, right? So thus the nanomaterials so acquire a new characteristics like the large surface to volume ratio as the result of a high percentage of atoms reside on the surface, right? So obviously, so you can downsize any materials, right? Whether it's a metal or semiconductors, but the metal and semiconductors have very distinct properties. For instance, so when you reduce the size of a metal to below certain nanometers, or classically it's a below 100 nanometers, right? So these nanoparticles experiences a new scattering phenomena, right? And thus exhibiting a surface plasmon or surface plasmon resonance, right? So whereas the semiconductors, in contrast to the metal nanoparticle, so semiconductors have a band gap. As you reduce the size of the semiconductor, and obviously the size of a semiconductor reaches to either it's a de Broglie wavelength or effective Bohr radii, right? So it gets the confined energy states in the electronic band structure. So the discreteness in the semiconductors as a result of the size down to the de Broglie and effective Bohr radii, the quantization or the confinement of the charge carrier occur in the semiconductors, right? In both the metal and semiconductor, you are having the size induced effect, the size induced optical effect, but these two phenomena are governed by the two different physical concepts, right? In metal, it's governed by the surface plasmon resonance, whereas in the semiconductor, it's the quantization. So besides these optical properties changes, so the materials at low dimension has or exhibits a unique chemical and physical properties, and also exhibit same size scale but has many biological structure, thus providing a very good platform to study the it's a quantum biology, how the materials interact with the biological world. So this this platform provides a new avenue of the quantum biology and also other new areas, right? So as far as the semiconductors are concerned, as I mentioned, that as the size has gone to the same order of either its exciton radius or effective Bohr radius or de Broglie, this is a classical description. So where in semiconductors you can see a quantum confinement effect as the size approaches to this level. So obviously these sizes are very small and supposed to be, it should have only few nanometers. Then you can experience or you can notice the quantum confinement effect in semiconductors. Actually, this quantum confinement or the quantum, this quantization phenomena, right? So mostly occurred in the semiconductors, right? So thus, depending upon the dimensionality reduction, right, as like in the nanoparticle, right? So as the dimension reaches or met these conditions of exciton Bohr radius or the de Broglie wavelength, depending upon the dimension of the confinement, right? So you can have either it's a, you can have it's a quantum, well, it's a two-dimensional quantum structure. Quantum wire, it's a one-dimensional quantum structure, and then it's a quantum dot, it's a zero-dimensional quantum structure. So these quantum wire and quantum dot is very interesting because this has very unique properties, very unique properties. So when you look into the density of states is one of the important property, so which holds the key for the control of optical and then electrical properties. When you look into the bulk matter, the bulk is made of n number of atoms, right? So atom has a free electrons. The free electrons in the matter, right? So moving very freely, and they are likely to interact with the electrons of another atom. So the electron interactions, right, or the collision of an electron causes the scattering, so that the electron cannot travel at its own velocity, right? The velocity has got reduced, thus the mobility is down. So obviously, when you measure the density of states, so which is nothing but the number of allowed energy levels per unit volume of energy with respect to density of states, you can see that in the bulk, so it changes linearly. So whereas in the two-dimensional quantum well structures, where the thickness is the order of de Broglie wavelength or effective Bohr radii, right? So here in this two-dimensional sheet of material, the quantum confinement occur in the one-dimensional, which means that so you have an electron which are there in the two-dimensionally. The electrons are free to move in other two dimensions, whereas the restriction is on only one side, right? The restricted movement of the charge in the material is called as the confinement, right? So here, so when you plot the density of states with respect to energy and then the DOS, here you can see that the energy acquires a step-like behavior. The energy has the step-like behavior, whereas in the quantum wire, right, you have it's a two, the charges are two-dimensionally confined. So where it has only 1 degrees of freedom. So this has a spike-like nature. Whereas in the tiny quantum dot, where all 3 dimension of a bulk has been gone to the de Broglie or effective Bohr radii, there you can see that 3-dimensional confinement, right? So because all 3 dimensions are restricted, no electron can move in either of the directions in principle, right? Because you have only a limited number of atom. This contributes only a few electron. The electrons are at the localized states in the ground state in a very stable state, right? But however, under some external conditions, the electrons can move in all 3 directions, but having no scattering at all. As the electrons are placing in the, are occupied at the discrete energy state, exhibiting a discrete energy level with respect to density of states, right? So this behavior, the electrons occupying the discrete energy state, is very analogous or very similar to an artificial, is a atom. So atom, you have the electrons occupy the different states in a discrete manner, right? So as the quantum dots can be called as an artificial atoms. Quantum dots are to be called as the artificial atoms, right? So this gives a recap. So as you do reduce the size of a semiconductor, right? In the bulk, you have a band gap, right? So the band gap is an intrinsic property of a material. Either by a doping or introducing stress and then strain, you cannot vary the band gap. The band gap remains as a band gap. It's a constant for any given bulk semiconductor. But in a moment, when you start to decrease the size of the matter, as it falls to the quantum regime, meeting the description of either the de Broglie wavelength or effective Bohr radii, right? The discreteness in the band structure increases, which means that the band gap increases with respect to the reduction of the size, right? So here, the change of the band gap is not phenomenal, but however, it's very small change occur, but still it's very a significant one as far as the semiconductors are concerned, right? So this happens due to the quantum phenomena. So thus it's possible to tune. It shows to the world that it's possible to tune the band gap in the quantum dot simply by varying the size of the matter, meeting the conditions, right? So on the other hand, you can form a quantum well structures, right? So when a low band gap semiconductor is sandwiched between a 2 higher band gap semiconductors, right? So this provides a scenario like particle in a box, right? So just you account only the conduction band edges, right? So this is a high barrier, this is a low channel, this is a high barrier, right? So this is a particle in a box, so where your carriers are put inside, and then edges is a infinite potential well, right? So here this quantum well structures can be formed. So when gallium arsenide is sandwiched between aluminum gallium arsenide, obviously aluminum gallium arsenide has a higher band energy than the gallium arsenide, right? So here the thickness of the layer is corresponds to the well width. If you reduce the thickness, the well width decreases. So obviously the energy of the electron in this box as well as the wave function so gets the different nature, right? So here, as a higher band gap comes into contact with the low band gap semiconducting material, the bands are bent appropriately at the interface. This forms a triangular like potential well. So all these carriers are being confined at this triangular potential well, having a behavior of 2-dimensional electron gas, right? So this very interesting electron gas confinement, right? So where you can use a particle in a 1-dimensional box, 2-dimensional box, it does not matter, right? So you can have the this simple approach, right? So you can define the different regions with the boundary conditions, right? So you have this particle in a box approach. You would be able to write the time independent Schrodinger wave equation with the given boundary conditions. You would be able to solve to find out the eigen energy and then eigen function, right? So here the eigen energy E is a function of L. It's a well width. As the well width decreases, right? This being in the denominator, the energy will increase. And also parallelly, you can see that the wave function, right? So the wave functions, okay, next slide you can see. here you can see that the wave function, when you reduce the length, the wave functions so becomes very tight because the interactions, the very strong interaction of the wave function is taking place. The confinement becomes very, very strong. Here you can see that the electrons occupy different quantum energy state with respect to well width. These energies change, right? But of course, you can also use the particle in a box three-dimensional particle in a three-dimensional box for the quantum dot approach. You can find out the energy confined in the quantum semiconductor quantum dot, right? So the semiconductors at the low dimensional quantum world, right? So provides a direct evidences, right, to validate the theoretically studied quantum mechanical approaches, right? So that as a result, right? So the confinement of the charge, right, gives us a power us to fabricate quantum devices, right, with very high functionality, right? So when you look into the comparison of the low dimensional structure with the bulk, right, the bulk has 0 degrees of confinement, but this has 3 degrees of freedom. So whereas in the quantum dot, just we compare the bulk with the quantum dot. So the quantum dot has 3-dimensional confinement where it does not have degrees of freedom, right? So always for the various dimensionality of the matter, right? So when you sum up the degrees of freedom and then degrees of confinement, this should always be 3. This is the total coordinates are the 3 dimensions of the matter, right? So we have the metals and semiconductors. So when the semiconductors are reduced to the either it's de Broglie or effective Bohr radii, semiconductor sees the quantum confinement, the quantization phenomena occur in the semiconductors, right? So here the size induced effect, the size induced optical effect in semiconductor occur as a result of the quantization phenomena. Whereas in the metals, as you reduce the size of a metal, right? So metal already has the high amount of free carriers in the conduction band, right? As you start to reduce the sizes smaller and smaller, as all the atoms in the metal are exposed to the surface, right? So each atom has a free electrons, the conduction band with the free electrons, right? So all the free electrons of an atom, right? So forms like an electronic cloud, right? All electronic cloud, and this form a dipole with respect to ionic core, right? So you are having the positive charge and negative charge, right? This is like a dipole. So the dipole always undergoes an oscillation, undergoes a natural oscillation. So the oscillation frequency corresponds to the size of a matter. So when you shine an electromagnetic wave, right? So the oscillation undergoes an extensive absorption as well as the scattering phenomena, right? So when there is a resonance in the oscillation with respect to the electromagnetic waves, right? You can see some the system acquires a specific color, right? The point at which where the resonance occur, we do call it as the surface plasmon resonance, right? So here being a metal, even when you downsize it, right? So there won't be any discreteness between the valence band and the conduction band. Obviously, when you keep downsizing the metal, it will approach to a molecular state rather than the quantization effect, right? Or rather than the discrete energy level as you've seen in the semiconductors, right? So the metals and semiconductors at the low dimensional world are very interesting because it gives rise the several new novel phenomena, right? So really the semiconductors are having very powerful at the low dimensional world, particularly the quantum regime world. So it augments our understanding and to study several new phenomena. I think that time is lapsed. So probably let me stop my presentation at this juncture. I will reserve few minutes for discussion, if any. So the next lecture, I will continue this talk, and also more I do concentrate on the applications perspective of low dimensional structures, in particular the nano wires, right? So thank you very much for your kind patience. So now it's open for discussion. If you have any questions, it's most welcome.
Thank you, sir. The session is open for discussion. Participants are requested to post their questions in the chat box.
Okay, so there is a question. So what are the experimental evidences and techniques to show the different dimensional quantum confinement exist? So fundamentally, to study the different dimensions of a matter, right? So you have to look into the microscopic instruments like a transmission electron microscope, or at least a scanning electron microscope, or the atomic force microscope. These are the tools directly illustrates, so whether you have it's a one-dimensional, two-dimensional, but a three-dimensional, right? And also these techniques allows you to measure the size of the matter, right? So from the dimensionality changes, right, you can see that, so what are the dimensions of the object? So then when you take the system for further studies, so for example, the optical studies, or I would say the photoluminescence or absorption studies, so which directly evidences so whether you are having a confinement or not. So for example, you take a gold, right, in the metal point of view, you take a gold. So gold having a very beautiful and then shiny yellowish color, right? So this has the intrinsic melting point. I think the gold melting point is around 1030 plus degree centigrade. So when the gold was reduced to it's a below 100 nanometers. So when you try to measure the melting point drops to around 750 or 800 degrees centigrade, right? At the same time, so at below 100 nanometers, when those nanoparticles are suspended, or you find a way to prepare the gold nanoparticle in the colloidal form, suspended in the aqueous state, when you do a light scattering measurements, then you can notice that the absorption peak changes with respect to the size of the matter, right? So as the absorption peak continuously changes, right, with respect to the gold nanoparticle size, you can see that the gold has the surface plasmon resonance. In the same way, semiconductors, you can do a photoluminescence measurements, right? Because photoluminescence directly provides or measures the band gap of a semiconductor. So by seeing a peak in the band-to-band recombination, you can see a band gap. So as the band gap increases with respect to size reduction, you can say that there is a quantum confinement, right? So by combining two different experimental approach like the morphological changes with respect to the photoluminescence evidence, you can say that the materials has the quantum confinement in experimentally. But of course, theoretically, there are various tools are there to study the quantum confinement phenomena. So the next question, so band gap calculated at bulk region or the surface region. Well, so the band gap is the intrinsic or the bulk property of a matter in principle, right? So as you take silicon, so silicon has the band gap of 1.1 electron volt. Of course, you know it's an indirect band gap semiconductors, right, in the bulk form. So, but when you reduce the size, when the size of a silicon reaches to de Broglie wavelength or effective Bohr radius, because I continue to repeat this term, so the silicon sees a quantization because the discreteness in the band structure increases, right? With respect to the size reduction, the band gap continued to increase, right? So obviously the band gap is a bulk property of a matter. So whereas as you're able to tune the band gap as a result of the quantization. Another question. Okay, I think these are the only few questions in the chat box I could read, and I hope I have answered all these two questions. So, are there... Yeah. So if there are any questions or if you're interested to know much more about these low dimensional structures, so you could write to me through good email, right? So probably in the first slide, you would have seen my good email. It's jagannathan@bdu.ac.in. So just you can write to me. I'm happy to share about the materials point of view. Thank you.
Thank you, sir. We'll start the next session. I invite Dr. M. Kumaresavanji, Assistant Professor, to introduce our speaker.
Yeah. So good afternoon to everyone. I am pleased to be the part of this event and to interact with the legends of theoretical physics. This session is going to be lectured by Dr. R. Sangaranarayanan, Associate Professor of Physics, NIT Trichy. He has completed his BSc from St. John's College, Tirunelveli, and MSc from MDT Hindu College, Tirunelveli. He obtained his PhD from Gujarat University, Ahmedabad. Then he worked as a postdoctoral fellow at two institutes, one at Physical Research Laboratory, Ahmedabad, and another one at Weizmann Institute of Science, Israel. Then he joined as a research associate and scientist at School of Physics, Bardhasan University, Trichy. Then he became the assistant professor of physics at NIT Trichy on 2006. His field of interest are Hamiltonian systems, chaotic quantum systems, quantum information, and statistical mechanics. He has guided two PhD students, and he has more than 35 research articles in reputed journals. And he has delivered more than 28 invited lectures in many colleges and conferences and seminars. With this introduction, I'm delighted to welcome, hand over the session to Dr. R. Sangaranarayanan to talk about thermodynamic entropy. So it is over to you, sir.
Hello, can you hear me?
Yes, sir.
Yeah. Yeah, thank you, Dr. Kumaresavanji, for a very generous introduction about me. I am supposed to start at 3:30. Am I on the time or before time?
Before time, sir, but you can start. Yes.
So no problem in continuing?
No problem, sir.
Okay.
Thank you.
Sorry. First of all, my sincere gratitude to Professor Sundar Raman, the principal of National College, and Professor Pari, the head of the Department of Physics, National College, for organizing such a nice lecture workshop, Academy sponsored lecture workshop. It's indeed a great opportunity for all the people, students and scholars and faculties to sit and interact and refresh quite a few things. I'm also very privileged for being a part of this activity. I must register my sincere thanks to Professor Lakshmanan, the convener of this program, and also my sincere heartfelt thanks to Professor Ravichandran for all the meticulous arrangement and everything. Thank you so much, sir, for your kind attention, for your kind arrangement and all the necessary background work done so meticulously. I'm indeed doubly honored to talk in these kind of workshops, so that I hope at the end of the day I will also learn something. So as Professor Bhaskaran was pointing out in the previous lecture, so the discussion is a very, very important component of any academic activity. I wish this platform is actually one such platform to extend our academic discussion in spite of all our routine activities. Let me try to share my screen. Is my screen visible, sir?
Yes, sir. Visible, sir.
Okay. Okay. So the topic which I have chosen for today's lecture is on thermodynamic entropy. I know it's not easy for the participants to lecture at the end of the day, sit and listen to the lecture at the end of the day after listening to a few nice lectures in the morning and afternoon. But still, I will try my level best so that we will have some interaction once my delivery is over. Of course, you can also interrupt me in between. Okay. So I am associated with Department of Physics, NIT Tiruchi, and the website is given over here to know more about our institute. And you can also note down my email ID for any future communication. Okay. So entropy has been a very enigmatic quantity in the physics community and other people, and particularly it is more enigmatic for the students and many other people. So I thought I should give some insight on the entropy so that our learning becomes more and more meaningful in the larger scheme of things. Okay, when I talk about entropy or thermodynamic entropy, essentially I'm going to talk about thermodynamics, and eventually, and I will close my lecture with some applications of entropy, what this entropy can do good for us to understand the scheme of things. So when any discussion starts on thermodynamics, I'm helpless to start with the quotation, the quote which is given over here. It says that thermodynamics has something to say about everything, but does not tell us everything about anything. So there is also interesting comment about thermodynamics by Arnold Sommerfeld. He says that thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it, except for one or two small points. The third time you go through it, you don't understand it. But by that time you are so used to it, it doesn't bother you anymore. Right. In spite of all these comments, of course, these comments are in fact inspirational for someone to read more on thermodynamics. Okay. Now, thermodynamics is like mechanics. It's a very, very old subject. It's it has been many hundreds of years since we started talking about formal development of thermodynamics and so on. And I will just give you a quick historical account of what has happened over the last few hundred years, so that we know what has happened. Right? It's very important to know how the subject has actually evolved over the years. Okay. We know that the mechanics actually, the formal mechanics or the Newtonian mechanics, the celebrated Newton's law and all the development happened. Before that, there is a gentleman called Galileo Galilei, whose contribution is very important, which led to the advent of Newton's law of motion. In a similar way, the subject of thermodynamics also starts with the advent of water thermometer developed by Galileo Galilei. Right, there are very many people contributed over the centuries. I just list out only some people, and I also highlight few people whose photograph I will just share it. So 1593 Galileo Galilei, 1662 Robert Boyle, and 1798 Benjamin Thomson. He gave the mechanical equivalent of heat, and we have the famous Avogadro number, which came out in 1811. We have a Joseph Fourier in 1822, Sadi Carnot in 1824, Robert von Meyer in 42, and Helmholtz in 1847, William Thomson or Lord Kelvin in 1848. You can see the work done by them. I just mentioned it. Then James Prescott Joule in 54, Rudolf Clausius. So the Rudolf Clausius is the one who introduced the notion of entropy. In fact, that is going to be a central topic of today's discussion. 1865, James Clerk Maxwell. 1870s, Maxwell and Ludwig Boltzmann. 1873, Van der Waals, and 1889, Josiah Willard Gibbs, who gave the foundation of modern statistical mechanics. So the people, the name the list of names I read now, they have been shown here, starting from Galileo Galilei here, Robert Boyle here, Avogadro, Sadiq Carnot, Clausius, Boltzmann, Maxwell, and Gibbs. Okay. Okay, so let's get back. I have planned this lecture as a more of an extension of classroom teaching, so that there's going to be a some discussion, and so that we should have some takeaway at the end of the lecture. Okay, right. When we talk about the phenomena which is happening around us and in the large scheme of things, and if you want to understand the secret of all the things happening or secret of universe, one has to think in terms of energy. When you say energy, energy actually has been broadly classified into two forms. One is mechanical, which is what we call it work. Another one is called the non-mechanical, which we call it as a heat. So thermodynamics is a subject which deals with both the energies. That's a very important thing. Okay. So because we include heat, things become more and more tricky. Okay. Right. So the subject of thermodynamics starts with this kind of simple picture. You have a system, and everything around the system you call it as the environment. And the system and environment is separate. The system and environment are being separated by a boundary. That boundary tells the domain of the system, right? And the nature of the boundary classifies different kinds of systems. So here I just mentioned three types of systems. The one is called the thermally isolated. In the thermally isolated system, there is no exchange of energy between system and environment. And another type is called the closed system, where we permit energy to exchange between system and environment. And the final one is the most complicated one, which is the open system, where we permit the system to exchange energy and matter. So since we have three kinds of systems, the simplest one is the thermally isolated. So to accommodate these three kinds of system, in the statistical mechanics, we develop what is called the ensemble theory. So we develop three kinds of ensembles, as you know, microcanonical, canonical, and grand canonical, associated to all these three types of systems. Well, coming back to thermodynamics, we having defined the system and environment, we do not really care about the environment, which is very, very large in size compared to the size of the system. So we are interested only in a system which typically is composed of a large number of particles of the order of 10 power 23. The particles, when I say particle, I call any system as a system of n particles. The particles, when I say, it could be atoms or molecules or ions. I don't care what these particles are. It depends. It varies from situation to situation. Okay, thermodynamics is not interested in what these individual particles are doing. Rather, it is concerned about the bulk properties of the system or macroscopic properties. So the relevant macroscopic properties are being described by variables called pressure, volume, and temperature. These quantities are sometimes called as the thermodynamic variables, which I will qualify later. So suppose you have a system having different pressure, volume, and temperature. You intuitively expect that there could be some relation among them. So relation should be of this form: some function of PVT equal to 0, right? So this is what you start with. So such kind of relation, if it exists, we call it as the equation of state. It's a different matter whether you are able to discover such kind of relation, but for any system, such a relation exists. It is up to you to figure out the equation of state. But nevertheless, let's assume that there exists an equation of state for a given system, right? If you have f of PVT equal to 0, you can always write one variable in terms of other two variables, right? You can write P as a function of V comma T and so on. So if you write, you can also do V as a function of P comma T or T as a function of P comma V, right? So when I do so, if I write T as a function of P comma V, what I assume is that P and V are the independent variables and T is a dependent variable, right? So this relation comes from this equation of state. So if I have an equation of state, I can always write one variable as a function of other two variables. So if T is a function of P comma V, P and V are independent variables and T is a dependent variable. So I have to bother only about the independent variable, because if I know P and V, I can always find out T from this relation. So that's the point, right? So if PV are the independent variables, then we can write down a state of a system at some time t by a point in this PV diagram, in this PV axis, right? This is a state. Now this state will change with time, right? The system will evolve with time. So when it evolves, the pressure changes, the volume changes, or temperature changes, right? Many things can happen. So if the system evolves, that evolution of a system is what we call as a process or thermodynamic process. So essentially, the process is being represented by a trajectory in this PV diagram until the system reaches to some other state, right? So it starts from some initial state, it will go on, it will keep changing, and it will settle down to another state. So this curve or trajectory in this PV diagram we call it as a process. This is one way of representing the thermodynamic process. Okay, right. So the moment we write down this process in the form of trajectory in the PV diagram, we can classify this process into two types. One type is called the ideal process, where the initial and final states are I and F in this diagram. And in the ideal process, we know exactly the path. If you know exactly the path by which the system transforms from I to F, then such a process we call it as an ideal process or reversible process. Why reversible process? If I know exactly the path, I can always run backward. So you can proceed in the forward as well as backward direction. Such process we call it as a reversible one. But this is the ideal one. So in reality, none of the processes are of this kind. So all the processes are irreversible, which is being represented by a dotted line like this. So all the processes which take place in the nature are irreversible. This is a very crucial point which we have to recognize. One can also define what is called a cyclic process, wherein the initial and final states are same. So if the initial state is A, suppose the system takes to B by the path 1, then again comes back to A by path 2. So if the initial and final states are same, then such a process we call it as the cyclic process. So this cyclic process you can call it as a reversible cyclic process. It may also happen that you can have an irreversible cyclic process. Irreversible means one segment A to B is irreversible in the sense which I mentioned over here, and B to A is a reversible one. So that this cycle is an irreversible cyclic process. Okay. So having defined the process in the PV diagram, we have to do a bit of differentials in mathematics to appreciate further developments in thermodynamics. So let us. So here I have been mentioning about t as a function of p comma v. So essentially there is a function. It's a function of two variables, right? So I want to understand this kind of functions. Function of two variables. What will happen? So in order to understand a function of two variable, first let me start with a function of one variable. If f of x is a single valued continuous and differentiable, then the infinitesimal change in f, which I call it as the exact differential, and if that is the case, I can write the infinitesimal change df as df by dx into dx. So I can write this as long as f is a continuous, single valued and differentiable. Then only I can write down this df by dx. Right, if that is the case, I can ask the question, what is the change in f when I move from x1 to x2, right? So the change in f is what I call it as a delta f, which is nothing but the integration of df from x1 to x2. So since df is of this kind, which I call it as exact differential, so this integration is nothing but f of x2 minus f of x1. So what it means that the change in f, when I move from x1 to x2, the change in f, it depends only on the difference in the function at x2 and x1. You can call it as f2 or an f1, right? So just the difference in the value of the function at x2 and x1. You can extend this notion to a function of two variables, f of x comma y. Then you can ask about what is the infinitesimal change in the f, which I call it as exact differential. And this df can be written down as dou f by dou x dx plus dou f by dou y dy. Here we have the partial derivative. Please understand that. So this I can write it only if the function f is single valued, continuous and differentiable. So if you have a df written in this form, so what it says that the change in f, the change in x and change in y affects the change in f in this fashion. Okay. Now you can ask a question, if I go from a point x1, y1 to x2, y2 in this diagram, this is my state space, x and y. Okay. Something like your PV diagram, right? So I have x here, I have y here. So suppose I have the system is in the initial state 1 and it is going to the another state 2. So this state is represented by x1 comma y1 and this state is represented by x2 comma y2. So if the system goes from this state to this state, what is the change in this quantity f? So the change in f for a system to go from state 1 to state 2 is just integration of df from point 1 to point 2. That is delta f. So which is nothing but f of x2 comma y2 minus f of x1 comma y1. Or you just say f2 minus f1. So what this says that the change in the function f, it is just the difference in the value of the function at x2, y2 and value of the function at x1, y1. That's it. So what it says that the change in f does not depend on which path you go from state 1 to state 2. I can go from 1 to 2 in this path, or I can go from 1 to 2 in this path. In fact, you have infinite number of possible paths you have from point 1 to point 2. So this function, the change in f, it depends only on the value of the function at 2 and the value of the function at 1. That's all. It is so the change in f is independent of the path. Right? This quantity is independent of the path we move from 1 to 2 in xy plane. Right. So if that is the case, one can ask what is the change in f for a cyclic path. What do you mean by cyclic path? I start from 1, I go to 2, then from 2 to 1, I come back by some other path. So if it is a cyclic path, I just have to add 2, right? Integral df, first part is 1 to 2 plus integral df, second part is 2 to 1. So I know that this quantity and this quantity when I add, it is just going to be 0, right? The first term is actually f2 minus f1, second term is F1 minus F2, so it will be 0. So for a cyclic path, there is no change, right? Mathematically, it also implies that dou by dou f, dou by dou y of dou f by dou x equal to dou by dou x of dou f by dou y. So it doesn't matter which order you are differentiating. You differentiate f with respect to x first, then with respect to y is same as differentiating f with respect to y first and then with x. So the order of differentiation is immaterial as long as the function is of this kind. Okay, right. So such kind of differential, we call it as the exact differential. Okay, for exact differential, the change depends only on the endpoints. It does not depend on the path. So that's the important point we have to remember. Right. Now, as I mentioned earlier, we have two forms of energy, work and heat, right? So for simplicity, we can take a system of gas. Okay. Of course, thermodynamics does not deal only with gas, but we'll just initiate the discussion for gas. Then we can generalize it, depends on our situation. So if you have a infinitesimal work done by the gas is expanding, can say, then the infinitesimal work done, which I call it as delta W, is PdV. P is the pressure and dV is the change in the volume. So delta W is PdV. With this, the total work done by the gas in the expansion is integral PdV from initial volume VA to final volume VF, as shown in the diagram. So this quantity is nothing but the area under this curve, right? Initial state to final state, the system takes there is a process which goes in this way. Then the work done in this case is nothing but the area under this curve, that is W. So obviously the area under this curve depends on the nature of this curve or the nature of your integration. So in that sense, you can say that work is a path dependent quantity, right? On the other hand, we have a heat, which is a non-mechanical energy. When you supply a heat to a system, what actually happens is the temperature increases, right? So temperature changes. So the amount of heat absorbed in the system is proportional to the change in temperature and the mass. So larger the mass, you have to supply more heat, right? So delta Q is proportional to m times dt, right? Then for a process where the system goes from initial state I to final state F, you can just integrate this quantity del Q, which is the Q. That Q is the total heat absorbed in a given process. So this heat is also a path dependent quantity. So in our notation, we say that if Q is the heat absorbed, if Q1 is the heat absorbed, and if Q2 is the heat released, we denote it by minus sign. Okay. In a process, suppose certain amount of heat is absorbed, which I call it as Q1. Certain amount of heat Q2 is released, which I call it as minus Q2. So the total or net heat absorbed is Q1 minus Q2. This is a convention we follow. So the point is that both the work and the heat, the mechanical and non-mechanical energy, both are path dependent. Okay. So now we are in a position to appreciate the first law of thermodynamics. So heat absorbed is nothing but the gain of energy, which is path dependent quantity. Work done by the system is a loss of energy, right? So this is a convention I follow. Work done is a loss of energy because work is done by the system. So you can ask the question: if you have a system having certain energy, it absorbs certain amount of heat and it does certain amount of work. So the total change in energy during a process is Q minus W, which I call it as delta U. So this is the statement of first law. So this statement says that energy is conserved, right? Energy will be conserved. Okay. Now this statement, which is a very simple looking statement, has a lot of consequences. Okay. Now, this first law can also be written down in an infinitesimal form, which I write it as du is equal to delta q minus delta w. The same thing I am writing in the infinitesimal form. Now, delta q is path dependent. Sorry, q is path dependent, I told you, and w is also path dependent. So in that sense, since these quantities are path dependent, the infinitesimal change in these quantities are these differentials. In some sense, you can call it as the inexact differential. On the other hand, the del q minus del w turns out to be an exact differential. Okay, that's the interesting part of this first law. So delta q and delta w are not exact differentials, but delta u or du, which is dq delta q minus delta w, is an exact differential, which means that the change in the energy u, it depends on the it depends only on the endpoints. It does not depend on which path it takes. Okay, so this quantity u we call it as the internal energy, which is also nothing but the sum of energies of all the constituent particles, right? Suppose you have a system which is initially in a state A, there is a process taking place, and at the end of the process, the system goes to B, right? There are infinite number of paths from point A to point B, right? Now you can ask the question, what is the change in the internal energy? And it turns out that this internal energy, since du is an exact differential, the delta u, which is the change in the energy for a system to go from state A to state B, is just ub minus ua. What is ub? Ub is the energy at B, and ua is the energy at A. It just depends on the endpoints A and B. It does not depend which path you really take, because the point is that, as I told you earlier, all the real processes, we do not know the exact path. So we are essentially looking for quantities which depends only on the endpoints, not the path. Okay. So now we got one such quantity called internal energy from the first law of thermodynamics. Okay. Right. So in that sense, U is called as a thermodynamic variable. Okay. A thermodynamic variable is the one which depends only on the endpoints. The change depends only on the endpoints. Okay. Of course, I mean, here I am just proving that U is an exact differential. Okay. I'm not going to the details of it. You can see it in other places. Okay. So having got this U, now we have got 4 thermodynamic variables, P, V, T, and U. Right? Now we can assume that the energy or internal energy or energy, it depends on P, V, and T. Right? It's natural to assume that U is a function of P, V, and T. So if U is a function of P, V, and T, we already mentioned that T can be written as a function of other 2 variables, right? So in that sense, U is a function of, P is a function of V comma T, or you can write this U as some function of V comma T. So essentially U is some function of 2 variables V and T. Okay, like f of x comma T, f of x comma y, right? This is like x, this is y, and U is your f. Okay, right. Since U is a path independent quantity, and so du is an exact differential, right? We can write expression like this for U, right? I'm writing du as dou u by dou v dv plus dou u by dou t dt, right? So with these differentials, we can rewrite the first law, and you can just substitute this. You can do all that. With this relation, you can if you combine the first law, you can have a relation something like this. Cp is a heat capacity at constant pressure, and Cv is a heat capacity at constant volume. So you got some this kind of differential relation. It's a very general relation for a gaseous system. Of course, for the gaseous system. So why gaseous system? Here dW is the work done by the system. So I take a gaseous system, for example. So in which case dW is PdV. Of course, I can write this kind of expression for any system. Only thing is, I just have to write down the dW appropriately. For a gaseous system, dW is PdV. So this you have this combination of two variables, P and V. So here, this P is sometimes called as the intensive variable, and V is called as the extensive variable. You might have come across this definition. So depends on the system, you just have to change this term, and you will get a similar relation for any system, right? So here I'm just writing down a set of systems for a fluids, gas or liquid. The intensive parameter is P and extensive parameter is V, and the work done is delta W is PdV. For a stretched wire, you have minus FdL. For surface, you have minus sigma dA. For electrochemical cell, it is minus E dq, and for dielectric slab, it is minus E dot dp. And for paramagnetic rod, we have minus mu naught H dot dm. So depends on the system you are considering. You just have to plug these terms for the work done. Okay, right. So you can do thermodynamics for the system of your interest, not necessarily for a gaseous system. Okay. Of course, we are coming back to the gaseous system because that is the simplest system which you can think of. We also know that this so-called ideal gas law, which is, as I said earlier, for ideal gas, we have an equation of state f of PVT equal to 0, which is PV, which is not, this function is nothing but PV minus nRT, right? Equal to 0, where n is the number of moles and Na is the Avogadro number, R is the gas, universal gas constant. And it is important to realize that in this ideal gas law, the temperature T is measured in Kelvin. Okay, right. You can also define the Boltzmann constant as R by Na. So in terms of this, you can write down this equation as PV equal to NKT. So what it says that whatever be the gas, for sufficiently low pressure and high temperature, all the gases obey this equation, this relation. So you calculate pressure, volume, and temperature, and the temperature should be measured in Kelvin. Then this law is being obeyed by this gas under this condition, low pressure and high temperature. So these conditions imply that under low pressure and high temperature, the molecules are fairly separated well, right? They move randomly and they don't interact with each other. So essentially, ideal gas is nothing but a system of particles which are non-interacting. Okay, so we have an equation of state for a system of non-interacting particles. Okay, which is PV equal to NKT. Right. If you take one. Hello, are you following? Hello, can I move on? Hello, can I move on further?
Yes, sir.
Okay, thank you. There was a small interruption. Okay. Well, now, so for such an ideal gas, we can calculate the internal energy U, which I just mentioned it, right? So you see that this I say that U, in general, U is a function of V comma T, right? But for the ideal gas, U is a function of T alone. We know that U of T is equal to 3 by 2 RT, and you can calculate this heat capacity relation Cp minus Cv equal to R, and the adiabatic index is gamma, which is greater than 1. Okay. So we know all that for the ideal gas. Okay. Now we can also think of some simple processes which may be useful for the further development. So we have a process called isobaric process where there is no change in pressure. So such a process is just described by a straight line in the PV diagram. The straight line is parallel to the V axis, right? And B to C can be thought of as a isochoric process where there is no change in volume. So these are all, reversible process in some sense, because we can go forward, we can come backward kind of. In addition, we also have isothermal and adiabatic process. In isothermal process, there is no change in temperature throughout the process. In the adiabatic process, there is no heat transfer. Okay, the heat transfer is prohibited. So with this one, we can represent these two processes also in this PV diagram. So this process is the isothermal process, and this process is the adiabatic process. So all the four processes are reversible processes. So you can go in forward direction or you can go in backward direction. Okay. Now, if you have any irreversible process or real process from A to C, for example, you can reach from A to B by imagining a set of reversible process. So for example, I can go from A to B and B to C like that. A sequence of isobaric and isochoric process by which I can go from A to C, right? So the point is, any irreversible process can also be, can also be obtained with a sequence of reversible process. Okay, right. Now these adiabatic and isothermal processes are extremely useful in the discussion which comes further. Now we are in a position to describe the second law of thermodynamics. What second law says? The first law says that both Q and W are path dependent, but U, which is delta U, which is Q minus W, is path independent, right? So U is a thermodynamic variable, and Q and W are not. Okay. In the first law is all about the conservation of energy, and second law is all about conversion of one form to other form. Conversion of energy of one form to other form. How to transform heat, non-mechanical or heat energy to mechanical form. So there are Clausius and Kelvin statements you might be familiar with. So one is asking a question: can we have a device which converts the heat to work repeatedly so that we can extract meaningful work from a heat? So such kind of device is called the heat engine, and this heat engine is being theorized, theoretically hypothesized in the form of cyclic thermodynamic process of an ideal gas by Sadiq Carnot in as early as 1824, which is in fact the true beginning of the entire advancement of human civilization in some sense. Right, for a cyclic process, we know that delta U is equal to 0 because you're coming back to the initial and final states are same. So delta U is equal to 0. In which case, since delta U is equal to 0, you apply the first law, which means Q is equal to W. So if Q1 is a heat absorbed in a system in a process, and Q2 is the heat released in a process, in the same process, Q1 minus Q2, which is Q, is equal to W. Then one can also think of a cyclic process by constructing this set of a pair of adiabatic and isothermal process like this. So you have an isothermal process at T1 and another process at T2, and if you start from A to B, B to C, C to D, and D to A. So this can be thought of as a cyclic process. And if an ideal gas undergoes this cyclic process, this process is useful to convert the a part of the heat to work. Okay, right. Then one can ask the question: what is the efficiency of conversion, which can be defined by the efficiency parameter, which is work output by heat input, which is W by Q1, which is 1 minus Q2 by Q1. Now, so this relation, this equation 1 minus Q2 by Q1 one can show that it is equal to 1 minus T2 by T1, where T1 is the higher temperature isothermal process, T2 is the lower temperature isothermal process. T1 is greater than T2. So this final step, you are getting it because of the relation Q2 by Q1 is equal to T2 by T1. This relation one can get easily when you apply ideal gas for the cyclic process. So this relation is very, very fundamental. Okay. As I told you earlier, PV equal to RT, where T is the temperature measured in Kelvin. So here you see that the ratio of the heat is proportional to the ratio of temperature. So in that sense, the Kelvin temperature directly measures the heat. So in that sense, this temperature, this Kelvin temperature is also called as the absolute scale of temperature or thermodynamic scale of temperature. Right. So this is the basic idea of your heat engine, and based on this heat engine, we are going to develop the second law of thermodynamics. Okay. So I'm not going to the detail of what Clausius has done, but essentially Clausius made use of this relation to develop the heat to work further. Okay. So he made use of this Q2 by Q1 equal to T2 by T1. And here the discussion is on a cyclic reversible process. So he extended this idea for a general cycle, which is what is discussed over here. I'm not going into the detail of it. And finally, so here you can see that this relation of this kind is being used by Clausius. Okay, I will go to the final result of what Clausius has given. So Clausius says that if you have any cyclic process, when I say any cyclic process, the process could be reversible cycle or irreversible cycle. Okay. So for any cyclic process, integral delta Q by T is always less than or equal to 0, with equality holds for reversible cycle. This is called the Clausius inequality. Now I take this inequality, I take this law or equation, and I'm going to apply it for a reversible cycle. So if I apply this equation for a reversible cycle, I should write integral delta Q by T equal to 0, because I'm going to consider a reversible cycle as shown in the diagram. A1, B2A, A1, B2A. I consider a reversible cycle for which this quantity is exactly equal to 0, right? Now, this can be written down as integral A to B delta Q by T via 1 plus the same quantity via path 2 equal to 0. So I can write down this as integral A to B delta Q by T 1 is equal to integral A to B delta Q by T 2. So what this equation means, the term on the left hand side and the term on the right hand side are same, but the term on the left hand side is along the path 1 and the term on the right hand side is along the path 2. Right? The same quantity is calculated for path 1 and path 2, which means integral A to B delta Q by T is independent of the path. In other words, I can call this quantity, the integrand, as an exact differential. So that integrand, I call it as ds. ds is, which is defined as delta Q by T, is an exact differential. So yeah, for exact differential, I use D. For inexact differential, I put delta. So delta Q is not exact differential, but delta Q by T is an exact differential. So what is delta Q and T? Delta Q is a infinitesimal heat supplied to the system, and T is the temperature of the source from which the heat is being absorbed. Okay. Right. So delta Q is not exact, but delta Q by T is exact differential, which I call it as ds. So if ds is exact differential, S is a qualified thermodynamic variable. Okay, this quantity we call it as an entropy. Okay, right? So S is a valid thermodynamic variable, like your pressure, volume, temperature, and internal energy. So first law gives you thermodynamic variable U, and the second law gives you the thermodynamic variable S, the entropy. Okay, so with this one can define the entropy for a given state. So suppose I take an arbitrary state as a reference state, and for this state and this state, I can define entropy. So entropy at A, I call it as SA, which is just dq by delta q by T integral 0 to A. So I go from here to here. That is what this quantity is. I compute this quantity from 0 to A. That is SA. Similarly for SB, right? Then with this definition, I can calculate delta Q by T from A to B. Suppose I go from A to B by some path, okay? Initial and final states are A and B. Then I can calculate this quantity, and this quantity is nothing but SB minus SA. So what you see is that this quantity depends only on the state at B and A, right? So it does not depend on the path. So this quantity I call it as the change in entropy. The change in entropy depends only on A and B. It doesn't depend on the path. So this is the change in entropy for any process from A to B. Please remember that. For any process from A to B, this is the change in entropy. Suppose I have a process, A to B via path 3, which is a irreversible or real process. I do not know the path, but I only know the initial and final state. Then I can always calculate delta S, right? I can always calculate delta S by constructing an equivalent reversible path from A to B. I construct an equivalent reversible path from A to B. If I construct an equivalent reversible path, for that path I can always calculate this quantity, right? So the point is, for any process one can calculate the change in entropy, be it reversible or irreversible. You can always calculate the change in entropy because it depends only on the endpoints. Okay, right. Now, as a consequence of this inequality, we are going to apply this inequality now for a general cycle. Here we applied for a reversible cycle, and now I am going to apply for a general cycle, which is given over here. A to B by a reversible path from B to A by a reversible path. So I'm going to apply this for this. I'm going to apply this inequality for this path, the general inequality. So A to B via path I and plus B to A by the path R. So the summation is always less than or equal to 0 according to Clausius inequality. So which means this, right? I can write this expression from the previous one. Integral A to B delta Q by T I is always less than or equal to integral A to B delta Q by T along the path R. R stands for reversible, I stands for irreversible. Okay. Now, what it says that, as I mentioned earlier, I am defining this quantity from the reversible cycle. So that means this quantity I can calculate only for the reversible cycle. Okay. So this quantity I can calculate, which is nothing but delta S, right? And left hand side is a irreversible process from A to B. So this inequality says that for any process from A to B, integral delta Q by T is always less than or equal to delta S. And this is in fact another statement of second law written down in terms of entropy. Okay, right. So one can also write this inequality if no heat is permitted to the system. If delta Q is 0, we can say that delta S is always greater than or equal to 0. With equality holds for reversible process. So what it says that in thermal isolation, entropy always increases. If you have a process, if you have any process Either the entropy will keep increasing or it will not increase. Okay, that's what it means, right? Either entropy will keep increasing or it will not increase for a typical system in thermal isolation. Okay, so you have to read this statement along with the caveat, right? This is for the system in thermal isolation. That's the important thing. Okay. Entropy always increases for a system in thermal isolation. If the system reaches an equilibrium state, there is no change in entropy. Okay, right. So here we have the standard example of the process of conduction and friction, which is taking place commonly around us. So one can show that for a conduction process, the change in entropy is positive. Similarly, for the friction process, the change in entropy is again positive. Okay, so I'm not going into detail of it. Okay, so with the notion of entropy, we can now understand the irreversible process in a better way. So what the second law says that in thermal isolation, a process which decreases the entropy is prohibited, right? Or in other words, we can say that entropy is maximum at equilibrium. Entropy is maximum at equilibrium. So you can also look at the entropy S as a function of T. So what happens is that entropy will keep increasing in the process. Then once it reaches some equilibrium state A, there is no change in entropy. The entropy remains constant. Delta S is 0. Then after some time, something else happens. Some other disturbance happens. So the system changes its state such that the entropy keeps increasing. It reaches another equilibrium state B. It remains in the B for quite some time. Then again it keeps increasing. So this is a typical change in entropy as a function of time. Now this time tau A and tau B are sometimes referred as the relaxation time taken to reach an equilibrium state. Right. So yeah. So you can see very many processes in the real world. All the processes are actually happening in such a way that entropy always increases. Right. So this quantity always either it doesn't change or it keeps increasing. Right. So any quantities in the physics we come across very many quantities, right? Energy, mass, energy, position, momentum, you have pressure, volume, all kinds of quantities. So all these quantities will increase or decrease, but this quantity called entropy, which doesn't decrease, okay, which always increases. So the examples of irreversible processes are fresh tomato gets rotten, fresh tomatoes get rotten, green leaves get dry, aging of a living species, wear and tear of machinery, tire, etc. Glass bowl slips off and breaks into pieces, diffusion of a drop of ink in the water. So all these processes are irreversible processes. You never see, a rotten tomato becomes a fresh tomato, right? You never get younger. You always go older, right? So this is essentially is what the entropy actually implies. A process takes place in an irreversible manner such that the entropy always increases. In some sense, entropy can be thought of as a time arrow. Okay, so now I just come to the further development of the thermodynamics. So which is actually here I'm going to write down a more general form of first law. So first law says that du is equal to delta Q minus delta W. So this term is a thermal. This is thermal energy. This is mechanical energy. And now I add one more term, which is called the chemical energy, delta C. So this is the most general form of the first law. And so we have the three types of equilibrium: thermal, mechanical, and chemical equilibrium. Okay. Right. Now for a gaseous system, we can always write down du as TdS minus PdV. That's what I wrote earlier, right? Okay. Why TdS? Delta Q by T is ds, right? That's what we have seen. So delta Q by T is ds. So I can write delta Q as TDS. So for a gaseous system, delta W is equal to PdV. Now I add this quantity called mu dn for this term. So I add this term, and this term is responsible for what is called the open system, wherein the n is actually the number of particles and dn is the change in the particle. As I told you in the beginning, if the system exchanges particles, then it's called an open system. So that has to be accounted over here by adding this extra term, and this mu is sometimes called as the chemical potential. So essentially we have many variables in thermodynamics: pressure, volume, temperature, and U is coming from first law, and internal energy U is coming from first law, and entropy S is coming from second law, and we also add mu and n. Mu is the chemical potential and n is the number of particles. So with this I can write down the same equation. I can rewrite like this: ds is equal to 1 by T du plus P by T dV minus mu by T dn. This implies that the entropy S is a function of U, V, and N, right? U, V, and N. And at equilibrium, this ds is equal to 0, which means the entropy S is maximum. Okay. So since S is a thermodynamic variable, ds is an exact differential. We can write down ds as dou S by dou U plus dou S by dou V. So dou S by dou U du plus dou S by dou V dV plus dou S by dou N dN. Of course, you have to differentiate partially by keeping the other two variables constant, right? Now, if you compare this expression with this one, you see that 1 by T is nothing but dou S by dou U, P by T is nothing but dou S by dou V, and mu by T is nothing but minus dou S by dou N. So in some sense, this relation is also considered as a definition of the temperature. Okay, and this relation is important to bring out the significance of entropy in what is called the in the subject of thermodynamics. In the subject of statistical mechanics. The statistical mechanics, on the other hand, unlike thermodynamics, it is bothering about what these particles are doing, how these particles and their properties, reflect on the macroscopic behavior. Is it possible to understand the bulk properties in terms of the what particles are doing, right? So one is interested to find out macroscopic behavior of a system in terms of microscopic principle. That is the objective of statistical mechanics, right? So the connection from thermodynamics to statistical mechanics is mainly through the entropy, which I am going to show it now. So in the statistical mechanics, I slightly change my notation. Instead of U, I consider E. Okay, S is a function of EVN, and in statistical mechanics, we say that this entropy S is directly proportional to logarithm of omega prime of EVN. What is this quantity omega prime? It is referred as the number of possible microstates for a given macrostate EVN. Okay, these are all macroscopic quantities: total energy, total volume, and total number of particles. Okay, so microstate means the microscopic configurations. Okay, how many number of ways you can put these particles together so that you have the same macroscopic quantities EVN, something like that. So one can write this proportionality with a constant C as S is equal to C logarithm of omega prime. So S is actually the thermodynamic variable, and omega is actually it's the number of possible microstates. So this is the connection between entropy and microstates. Okay, so this connection is crucial for the development of statistical mechanics. Okay, at equilibrium, we know that ds is equal to 0, which means if I differentiated differential of logarithm of omega prime equal to 0. So if I differentiated, what happens? You differentiated and equal to 0. Essentially, this will correspond to a maximum value of omega prime, which I call it as the omega. Okay, so omega is the maximum value of omega prime. So this is the value you get This is the number of possible microstates when the system is in equilibrium. Okay, this is what we are going to, we'll be calculating in statistical mechanics. For a simple, collection of n non-interacting identical particles, like when I say non-interacting, essentially you're talking about ideal gas. You have a set of particles in a box having total energy E and volume V and number of particles n. So this particle is non-interacting. That means the total energy is nothing but the sum of kinetic energy of individual particles, right? Right. For such a system, one can calculate this omega prime, which is proportional to V to the power n. Okay. So with this, one can I can make use of the earlier relation. P by T is equal to dou S by dou V, and I get this one. I get this kind of relation, which means PV equal to some constant times NT, where this constant is nothing but the same constant which is sitting over here, the constant of proportionality. Now, what you got is PV equal to CNT, which is same as the PV equal to NKT. We essentially got the ideal gas. So which means this constant C, the proportionality constant C, is nothing but the Boltzmann's constant. Okay. So this is how you see the connection. This is how you see the connection between entropy and the total number of possible microstates. Okay, which is crucial for the statistical mechanics. Right. Now, I want to calculate this quantity omega, right, at equilibrium. So in order to calculate this omega, here, since I am talking about a system of non-interacting system, if you think of each particle having set of discrete energy levels, those energy levels are going to be same for all the system, right? So you just look at the energy levels of a single particle, which is E1, E2, E3, and so on. And I just put many number of states. Okay, E1 has 4 states, E2 has 2 states, and so on. So basically, I have a set of boxes. It's something like your shelf in your kitchen. Okay, you have a shelf and you have many boxes. Now you are going to fill these particles in these boxes. So here, EI is the ith energy level of one particle, and GI is the number of states with energy EI, and NI is the number of particles in energy EI. So this NI, we want to find out these numbers, N1, N2, N3, and so on. These are the number of particles at different energy levels. We want to find out this NI at equilibrium. These NI are the number of particles at equilibrium. We want to find out these numbers, what this NI is. Okay, right. Now, I say that the total number of particles are sum over Ni, right? I have a large number of particles N, which is nothing but sum over Ni. And this N is fixed. Okay. To begin with, we will just consider the simple situation that the total number of particles is fixed, right? So that Dn is 0, and total energy is also fixed. So if I put certain number of particles here, now Ni is the number of particles having energy Ei, right? Then the total energy E, that say this is not that E is nothing but this one. This total energy E is sum over I Ni Ei. Right? Now, since total energy is constant, I say that D is equal to 0. Okay. Now, I can put these particles in different ways. So, it depends on the way I am putting particle. We emerge out to have two kinds of statistics. The first one is called the Bose-Einstein statistics, wherein you can put any number of particles in each box. Okay. A state Gi can have any number of particles. Here, in this example, G1 is equal to 4, G2 equal to 2, and so on. So you can also put particles in another way by restricting that a box can have only one particle maximum. So you can have two kinds of statistics. The second one is called as the Fermi-Dirac statistics. In the first case, you have this kind of number, omega BE equal to this thing, and second case omega FD is equal to this thing. Okay, now you take these numbers and then you have to, with these numbers, you have to maximize the entropy at equilibrium. You want to find out this Ni at equilibrium, right? So to find out the Ni at equilibrium, you calculate this quantity, then you take this logarithm of omega, right? And you take a differential of it equal to 0, isn't it? So this corresponds to the equilibrium condition. So if you do so, you will get the equilibrium values of this omega. So I will come to that. Before that, I just want to demonstrate this particular thing with a simple example. Suppose I have a 10 particles and total energy is 20 E. So I have to put these 10 particles in this. Imagine you have a system having only 3 energy levels, E, 2E, and 3E. And I have 10 particles. So how many different ways I can put these particles in these levels so that N is 10 and total energy is 20E, right? So one possibility is that I put no particle in the first level, and I put all the 10 particles in the second level and no particle in the third level, right? So if you put 10 particle in the second level, each particle having energy 2E. So total energy is 20E. Right? So this is one possible configuration. Another possibility is 181. So first one is 1 particle with E and 8 particles with energy 2E. That means 8 into 2, 16E. So 16E plus 1E is 17E. And 1 particle in the top level 3E. So 17 plus 3, 20E. So these are different configurations you can have, right? So you get this configuration by keeping the total energy constant and total number of particles fixed, right? Now, among these possibilities, among the different possibilities for N1, N2, N3, what is the actual configuration when the system is in equilibrium? It turned out that this configuration will be equilibrium when these numbers are maximum. When these numbers are maximum, according to this. So I calculate this omega BE and omega FD and see what happens. So for different configuration, I have calculated this omega BE and omega FD. So you can see that in this case, 92,000 something. Here you have 6 lakh something. Here I have 11 lakhs 26,125 thing, and so on. So this means I have 92,378 configurations or 92,378 microstates in this thing. Here I have 6,07,750 microstates. In this case, I have 11,26,125 microstates. So this is how you get that. And similarly for FD statistics, if you follow the FD statistics, you have these kind of microstates. So among these things, the system chooses the microstates such that this omega is maximum. So at equilibrium, you have omega is actually maximum here and maximum here. So this is the most probable configuration at equilibrium. So for this simple example, at equilibrium, this is the possible configuration: 2 particle with energy E and 6 particle with energy 2E and 2 particles with energy 3E. So this is how I can fill the particles. Okay, so this is what the meaning of this entire discussion is. Okay, now I have to integrate, I have to solve this equation along with the condition that dn equals 0 and d equals 0, right? That's what I do here. So you just multiply dn with some constant and d with some constant, doesn't matter because dn is 0, d is 0. I just put the 3 equations into a single equation, and these alpha and beta are arbitrary constants, which are sometimes called as the Lagrange's multiplier. Okay, multipliers. By solving this equation, you get the Ni. Okay, and this Ni is supposed to represent the distribution of particles among the energy levels at equilibrium. So the first one corresponds to BE statistics and second one corresponds to FD statistics, where here mu play a crucial role. Mu is, I already mentioned to you that mu is the chemical potential and T is the temperature of the system at equilibrium, and Kb is the Boltzmann's constant. Right? So essentially you have two kinds of statistics. So these are the particles are being distributed at equilibrium, but one should know which statistics should be applied under which condition. Okay. So without going into detail, broadly we came to two classes of statistics. One is called the Bose-Einstein and another one is called the Fermi-Dirac. So the particles which follow Bose-Einstein are called bosons. The examples are photons, phonons, and helium atoms. And the fermions, examples of electrons, protons, neutrons, and quarks. Okay, so all the particles are classified into only two types. Okay, so some of the particles are also called as the field particles, like photons and phonons. Okay, they are massless particles. So these statistics includes both massive and massless particles. Okay, that's the interesting part of this statistics. Okay. Okay, now I just want to, before closing it, I just want to see how this statistics works to explain the bulk property in terms of microscopic properties. So here we have a theory of paramagnetism, which is being explained beautifully from an experiment which is reported in 1952, where this paramagnetic, you have a set of dipoles, right? So these dipoles actually, in the paramagnetic system, typically a magnetic system is paramagnetic at high temperature, right? So they follow, by the way, these two statistics actually obey Maxwell-Boltzmann statistics at certain condition, in which case temperature is high. Okay, so they follow the Maxwell-Boltzmann statistics, and you have the beautiful theoretical curve which is matching with the experimental observation, and that's how we understand the paramagnetism very clearly. We also have the Planck's law of radiation given by Max Planck, and this Planck's law of radiation, which now we know that they obey the Bose-Einstein statistics, right? The photons, they obey the Bose-Einstein statistics. So the yellow region is actually the radiation from the sun, and the curve is actually the Planck's law for a temperature 5250 degrees Celsius, which is typically the surface temperature of the sun. And we also have the heat capacity of solids like silver. The heat capacity of solid obey the cubic law. The heat capacity at constant volume, they obey the so-called cubic law, which is given by the device theory. So this is because we apply the phonon, the BE statistics for the phonons. Phonons are nothing but the lattice vibrations of this lattice vibrations in the solids. Okay, right. So this is coming from the Bose-Einstein statistics applying to solids. And you also have potassium chloride. The heat capacity as a function of temperature is being explained clearly. So the data points are the experimental one, and these curves, this straight line is actually the T cube law, which is obtained by applying the Bose-Einstein statistics. Okay. Yeah. So in fact, very many materials, the heat capacity of very many solids, they obey the device law. Okay, which is an outcome of applying the Bose-Einstein statistics for the lattice vibrations. The lattice vibration can be thought of as a phonon gas. Okay. Now for metals, you have the T cubes law. You have a slightly different. There are deviations from the T cube law. If you look at the heat capacity for the metal, in the case of copper, this is actually this straight line. You see the T cube law, which is valid for which is matching for the silicon, but in the case of copper, well, there is a deviation. So this deviation is coming from the fact that the heat capacity of a solid, in the case of metals, in addition to the lattice atoms, the electrons are also contributing to some extent for the heat capacity. So the electronic contribution is being explained by this term. This term is actually device term, the phonon contribution, and the first term is actually the electron contribution. The electrons, they obey the Fermi-Dirac statistics. This term is essentially due to Sommerfeld. So this kind of theory explains the experiments so beautifully. Okay. Now finally, I have thermionic emission, where now when you take a tungsten filament and if you heat it very high temperature, essentially the electrons actually comes out. So you can calculate the density of electrons which comes out. So if you apply the Fermi-Dirac statistics for these escaping electrons, the theory gives that the current density is given by this. Or in other words, logarithm of J by T square is equal to A minus 5 by K by T. Here you can see that this phi is sometimes called as the work function. Epsilon 0 is the depth of the well, and this is C of electron. Okay, so the electron escapes, you have emission, thermionic emission. So this is the theory. Now, if you plot logarithm of J by T square on x-axis and 1 by KT on the y-axis, you will get a straight line with a negative slope. That's what you see here in the observation, right? Log J by T square on y-axis and 1 by T on the x-axis, you get a straight line with a negative slope. So by fitting this data to a appropriate straight line, you can calculate this epsilon 0, epsilon F. So which is calculate all these quantities very precisely. Essentially, all these things happen because of these statistics. Okay. So with this, I wind up my lecture by summarizing that in this lecture we saw that we have two forms of energy, which is which are heat and work, and all the process in the real world, are irreversible, whose path is unknown. Because the path is unknown, we look for quantities which does not depend on the path. So first law gives you the internal energy U, which is and second law gives you the quantity called entropy, and this quantity is maximum when the system is in equilibrium. And this entropy, in fact, opens the door of statistical mechanics. Based on this understanding of statistical mechanics, we have two types of particles called bosons and fermions. They obey essentially two statistics, Bose-Einstein and Fermi-Dirac statistics. So this is how, with this, we are able to explain various properties of solids from the microscopic perspective. So with that, I am closing my lecture, and there are good references over here. You have very many good books on statistical mechanics. You can just go through this, and I close the lecture with the final word. What we learn to do, we learn by doing, by Aristotle. And thank you so much for your attention. I'm happy to answer a few questions if you have.
Thank you, sir. The session is open for discussion. Participants are requested to post your questions in the chat box.
So there are questions over here. Let me just check it out. Oh, somebody asked what is entropy. Yeah. Okay, so entropy is definitely an enigmatic quantity, which is mathematically we define it as delta Q by T, right? This quantity can also be thought of as in some sense we can think of as a measure of disorder or something. Okay, there are different ways of looking at the entropy. So essentially, the system is more disordered from the microscopic perspective when it is in equilibrium. Okay. Of course, the entropy has a far-reaching consequences because the entropy is also used in different in the context of information theory and so on. Okay. The application of entropy is enormous. Now, the next question is okay. Yeah, sir, can you just again show the book name slides? Okay, I'll show you this books again. Okay, so please look at it. Okay, so people have given, thank you, sir. Thank you, sir. Anything else? Any other questions? If you have, you can just post it over here. Okay, there is a response from Yash. Thank you, sir. I really enjoyed your lecture. I have a question that why do we deal with ideal situation if we know that we can never really achieve ideal condition? Oh, that's a fantastic question. Yeah, that's a very good question, actually. Yeah. So why at all we should look at the ideal kind of process or ideal gas or something, right? See, essentially, we want to understand the more complicated thing. Before we understand the complicated thing, we need to understand the simple situation, right? So what you see here is that even this starting from ideal gas, we are able to understand quite a few things, right? Non-interacting system. So even though it's a non-interacting system, but these non-interacting systems are good approximations in certain conditions. For example, in the metals, you have electrons, right? So the metal, you have a lot of free electrons. When you say free, they are non-interacting. So this the collection of electrons can be thought of as an electron gas, right? So in some sense, you can apply this ideal gas for this electrons in the metals. So ideal systems and ideal gas are extremely useful to begin with. Then we slowly develop the situation of more complicated things, like what if you have a system of interacting system, right? So interacting systems are more complicated to study. Let me go through a few more. There are more questions. Yeah, I hope I'm done with the questions. So any other questions? Yeah, we study the ideal condition for the sake of simplicity. We start from simple system, right? In any mechanical system, we start with the harmonic oscillator, right? So if you understand the harmonic oscillator, you can understand quite a few things in certain approximation. Okay, so that's why we always study the simple situation so that we can get into the real system with a little extra effort. Yeah. Okay, so
there is another one question in the chat box.
Yeah, let me just, the chat box is not moving for me. Okay, one. Oh, sir, how can we explain the increase of entropy qualitatively? Oh, how can we explain qualitatively? It is actually one kind of measure to tell that how the system is actually approaching to the equilibrium. We can put it that way. So what I'm saying is that when the system approaches the equilibrium, what happens to the entropy? I say that according to the second law, the entropy is getting maximum. So by calculating entropy, and if it reaches maximum, you know that the system is reaching entropy. How do you know that system is reaching to entropy? Reaching to equilibrium. By calculating entropy, and if it reaches maximum, you say that it is reaching to equilibrium. Of course, in reality, we do not calculate entropy. See, many of the chemical reactions which happens in chemical reactions, a reaction takes place and it stops after some point. So the reaction stops means the reaction reached the equilibrium condition. So no chemist actually calculate the entropy. Rather, they calculate other quantities like for Helmholtz free energy or Gibbs free energy. So those quantities will be minimum. So one can write down the second law in terms of entropy or in terms of free energy. At equilibrium, the entropy is maximum. It is equivalent to saying that the free energy, the Helmholtz free energy or Gibbs free energy will be minimum. So chemists actually calculate the free energy and they see when it is going minimum. So if it reaches minimum, you say that the reaction reaches an equilibrium condition. So entropy is always a tricky quantity to, calculate or make use of it. But using that quantity only, we do all these statistics and everything. Yeah. Okay, I hope I answered some of the questions. Okay, if there are no more questions, I sincerely thank all the participants for patient hearing at the end of the day. And I also thank the organizers for giving me such an wonderful opportunity to share a few things with the participants. And thank you once again for giving me the opportunity. Thank you so much.
Thank you, sir. I request the participants to kindly fill the feedback form. Tomorrow's first session will start at 10 a.m. Thank you.